All right, good morning, everyone, and welcome to Managed Programming Languages and Runtimes 2023. I'm Elliot Moss, your program chair, and Rodrigo Bruno, our general chair and local arrangements person you can find over there if you need to talk with him about anything. Quick review of our schedule. We've got 4 sessions. I'll be chairing this one, and the others are listed here. Also, if you go to the program of this track on Splash, you'll find the detailed schedule of which paper is coming up when. So after this brief report, we'll have a keynote talk. It's 45 minutes plus some time for question and answer. And then we'll have 2 work-in-progress papers. The WIP papers are allotted 15 minutes. And to try to allow plenty of time for questions for those papers, we've asked the presenters to stick to 10 minutes or so. Now, our schedule follows that of Splash. So our break is 10:30 to 11, and then our lunch break from 12:30 to 2. That's Splash-provided lunch. And then we have another afternoon break from 3:30 to 4, and we wind up at 5:30. Now, the regular papers are allotted 22 minutes. I've asked the speakers to limit themselves to no more than 20 minutes so we have room for at least a couple of questions at the end. The posters, we believe, will be presented with the Splash posters in room 3. We're in room 2, so room 3 can't be too far away, right? And there are 2 poster times. Poster presenters are invited to present both times. One is this afternoon, evening, 5:30 to 7:30, and the other is Tuesday at the same time. And Rodrigo has kindly organized a reservation. If you already submitted by our survey to that, you don't need to tell him more. But if you didn't and want to join the dinner, please let him know. And it's about a 15 or 20-minute walk. I'll have a map in a moment. I want to thank all the members of our program committee. They did their reviews on time. I believe the reviews were well done and offered authors useful comments. This lists our steering committee. All of this information is available in the report that will be part of the proceedings. The proceedings should be accessible through the Splash and MPLR website. And I did insert this last week, links to preprints of all the papers. And I note that MPLR 2024 is in the works. I believe a general chair and program chair have been identified, a location, etc. Now, just for the record, we received 19 full paper submissions and 17 work in process submissions. Our reviewing was double blind. There was an opportunity for authors to respond to reviews before decisions. Each paper received at least 3 reviews. In the end, we accepted 10 full and 5 work in process submissions that said received, were accepted. Several authors will also be presenting their papers as posters. Since the papers are already accepted, we decided not to review those posters and just accepted them. There were 2 additional poster submissions, one of which was accepted. And that is my report. But before we get to the keynote, let me show you the map of how to get to the restaurant. Got it here. I have to skip back out. Okay. So we are here at the Hotel Miragem, and you see, you walk basically along the waterfront down to here, and the restaurant is, I'll get this pronunciation approximate anyway, Baia do Peixe. The rather bland English translation is something like Fish Bay, or Bay of Fish. Anyway, so that's where the dinner will be. And of course, if you're not up for walking, you can Uber or something like that. Right, now back, sorry, over here, and back to there. So Andreas Rosberg will present our keynote talk, Is WASM Becoming Garbage? Andreas did his PhD work at Saarland, I believe, and postdoc at the Max Planck Institute for Software Systems. After that, he was employed as software engineer by Google, working with the V8 team. They produce the JavaScript/WASM virtual machine engine. And since then, he's been an independent implementer, researcher, et cetera.
Not quite.
Not quite? Okay, well, I'll let you introduce more. So without further ado, we welcome Andreas.
For the nice introduction and for having me. So yeah, the only thing that wasn't quite right, there was another, like I was at a startup in between before, like after Google, but that's okay. Okay, let's see how this works. Okay, yeah, again, thanks for having me. I'm talking about WebAssembly, as Elliot already said, and especially about the new feature we have there, one of the new features we have there, which I'm excited about, which is garbage collection, so which is the fit for this conference, right? So WebAssembly, I don't know, who in the room is actually familiar to some degree with WebAssembly? So, okay, most people have seen it, I guess. Nevertheless, let me start with getting out of the way one or two misconceptions about WebAssembly. The first one being, it's a web technology. It's actually not a web technology. And I mean, it's easy to take it as that, given the name and its history, but we actually made very sure when we designed it, so WebAssembly grew out of the frustration of various JavaScript implementers with like wasting their life on this kind of thing. They wanted to do something more meaningful. So it's more like a historical accident that we called it WebAssembly. That, from my perspective, that was a way to convince management to adopt it, because to management at the time, the web was the only thing that mattered, right? So that's why we christened it that way, one of the reasons anyway. But really, the whole design was, from the get-go on, intended to be much more than just the web, really like not specific to the web at all. And we anticipated that it will be used in all sorts of contexts, and we are amazed to see that that actually happens. So it's now running in basically every kind of ecosystem you can think of, including things like embedded, and which is like the opposite end of the spectrum. And that is why I personally prefer to not emphasize the web aspect too much and just call it WASM, which is the short form, which, by the way, you spell this way, not in all caps, because it's not an acronym, so no reason to shout it. But with that out of the way, let me actually explain what it is. So WebAssembly, maybe the best way to think about it's a virtual machine. But it's a low-level virtual machine, like unlike other mainstream VMs you're probably familiar with as well. It's also designed to be language independent, right? So there's no language that has any particular privilege on this platform. It's also platform independent, meaning that it's designed to be embeddable anywhere, right? So the browser is just one example, but really it's you can embed it anywhere, and there are actually dozens of different implementations of WebAssembly, a dozen different implementations now, I lost count to be honest, which kind of are designed for different spaces, like very tiny ones for embedded, for example, and so on. Part of the design is that it's the language, it's kind of a language obviously, so it's designed to be very portable, deterministic, up to some minor quibbles, and sandboxing is also an important factor in its design. And finally, the specification is an open standard, so, what happened? Wait, see. Meaning that it's happening under the roof of the W3C, but everything, the entire process is totally in the open. All the discussions about proposals and stuff are on GitHub. We have bi-weekly meetings on Zoom where everybody can participate, essentially. It's completely open. Everybody can vote as well. And yeah, and there are various other subgroup meetings. You could just show up if you wanted to. All you have to do is register with your email, I think, for legal reasons or something. Right, okay, so the first item I say there is low level, and I want to stress on that a little bit because that's maybe relevant to my talk. So what do I mean by low level here? Well, there are various ways you can various characteristics you can use to describe this, but the slogan I'm using, or the general idea perhaps, is this one, right? So unlike other mainstream VMs, WASM really is an abstraction of the hardware below. It's not an abstraction of some programming language. So for example, compare that with the JVM, which is really more or less in the first approximation abstract syntax for Java, right? And .NET is similar. WASM is not that, and which means that really all the languages you could possibly implement on it are equal citizens. There's no language that has any particular privilege here. And as far as I'm concerned, if you want to have a language-neutral VM, that's the only way to do it. It has to be a low-level VM. Everything else will inevitably get you into some rabbit hole with language-specific features, which we try to avoid. So more concretely, it's essentially an ISA, a virtual ISA, so an instruction set that is inspired by what actual CPUs offer. So it's really in the intersection of what modern CPUs have, at least like the initial design. So almost every instruction has a one-to-one mapping to popular CPUs. Another part of it is that the cost model we have for WebAssembly is supposed to be very transparent and explicit, right? So with every instruction, you should be able to tell how it's compiled down by the engine to native code and what it does. So there are supposedly no hidden branches, no hidden allocations or things like that. If you have to do any of these, that should be explicit in the code, at least in the first approximation. And the goal there is that performance is really predictable, right? So you know what you're going to get. Another part of it is that there's no such thing as an object model, right? That just doesn't exist. You have memory, at least for now, and you do with it what you want. In particular, WebAssembly is designed to not require GC. And finally, another aspect of this low-level nature is that we assume that most interesting optimizations are actually done by the producer of WebAssembly, so a compiler targeting it, not by a consumer, which is the engine. So the engine can be relatively dumb. They just translate the WASM code to the native code they're running on, and they could be simple and fast. And in particular, they could work ahead of time. So we also don't want like any super fancy dynamic mechanisms in there idly. So that's the ideal as anyway. Of course, in practice, it doesn't quite work out like that. So you may ask the question, how low can we actually go, right? And the reality of things is that we are working in this triangle of conflicting goals, design goals, that we have to maneuver somehow. And actually, it's not just a triangle, it's a tetraeder, because one of the constraints we absolutely cannot compromise on is safety, right? It absolutely has to be safe. So we need to balance these constraints, and sometimes balancing these constraints means that we have to raise the abstraction level somehow. So the slogan I've been using, and which also was the title of another recent talk of mine, is that, yeah, it should be as low as possible, right, but no lower. And to give you a concrete example of how this already materialized in the initial design of WebAssembly 1.0 is consider like functions, how functions work in WebAssembly. So in WebAssembly, all code is organized into functions, right? They are a primitive notion. You declare their parameters, you have dedicated instructions for invoking them and so on. And that obviously is something that does not exist on CPUs, right? They don't have that. You just have code and you jump around. But that's not what we did, and there are several reasons to it. One is safety. So we don't want to expose the stack, right? Because they're like, it's a very beloved attack vector, among other things. And also we need to be type safe and things, which is difficult if you expose the stack in a primitive way. Another reason is that the producer, so the compiler that generates WebAssembly, doesn't know what actual physical hardware it's running on. So it's difficult for it to optimize like its code gen, like in terms of register allocation and things like that, parameter passing conventions and so on. But the engine knows what it's running on, so the engine can do a much better job of that, right? So this is like motivation for raising the abstraction level a little bit. We also don't expose code pointers, physical code addresses. Instead, we have this notion of tables. I don't want to dwell too much on that. But again, this has to do with safety and not wanting to expose certain low-level things that might be problematic. But even though we're raising the abstraction level a little bit here, it's still the case that functions are just code, right? If you have a reference to a function, it's really a code pointer. And we don't have anything like closures in there or, God forbid, methods, anything like that, right? That's not in the language. That's something you have to implement on top. Okay, and why am I telling you all this? Well, if you now hear I'm talking about garbage collection WebAssembly, that seems to kind of like run against everything I just said, right? So how does that fit in there? And before I explain that a little bit, let me just briefly say what the current state of this proposal is. It's actually done. So last month we voted it into the standard. After 6-7 years it was in the making. It probably was the most complicated proposal we had so far. And it's already targeted by various compilers. So for example, a Java compiler, Dart, Kotlin, there's work in progress on OCaml and Scheme, and probably many others I'm not even aware of. And this is not just work in progress, at least not all of it. It's actually already used in production. So for example, the Java compiler is used by the Google Sheets team. Google Sheets is written in Java, and it used to compile to JavaScript. Now they are ramping up the transition to WebAssembly, which means if you run the latest Chrome and open Google Sheets, there's like a 1% chance it's already running the GC proposal right now. Okay, but again, garbage collection in WebAssembly. The question you should be asking is why? Why do we need that? Or why do we want that? And WebAssembly has this notion of linear memory, so just a linear address space, that's all yours. You can do with it what you want, so can't you just roll your own GC in that, right? And yes, you can, and various languages have done that, and various languages will continue to do that. It's not a bad thing to do, and there are all sorts of reasons why you may want to do that, but there's a cost to it. And the cost has to do with the abstraction levels that we have in WebAssembly. So for example, you don't have access to the stack, as I said. You don't have access to registers. So this makes things like traversing, like walking the stack in the GC a bit difficult. You have to do workarounds like shadow stacks and stuff, which make it more costly. You also have the issue that production GC is really like, it's quite big, right? So if you, say on the web, want to ship a GC with every web page, that's kind of annoying. So if I remember correctly, so there's a monoport to WebAssembly that has existed for quite some time, and if I remember correctly, the runtime is pretty big, and it's just the GC alone is like 0.5 megabyte of code or something like that, or even more than that. Another issue is that, again, take the web as an example, you may want to access the host environment. So on the web, that would be JavaScript and the DOM, and be able to have reference to DOM objects, for example, and pass them around your WebAssembly code. And if there is like no coordination between the two worlds, then that is very difficult to do. And that's what currently languages do, but it's really hard to have a safe memory management story there. And then you have the general problem, of course, that if you have multiple runtimes running, say, in a web page, then you have this common problem of competing heaps, competing GCs, and that's, again, like a performance problem. And, of course, finally, at least on the web, we already have these industrial strength GCs right at our fingertips, right? They are there. There are like dozens or even hundreds of man-years went into the engineering of these things. They're probably the most advanced GCs out there. So it would be sad if we could not take advantage of that. So all these are reasons. There are some more. There are also a couple of non-reasons I should mention, non-goals of this proposal. And one is that we somehow magically achieve language interoperability between different languages compiling to WebAssembly. That in general has never been a goal for WebAssembly, and very intentionally so, because it never works, right? So this is like a separable problem from our perspective. So if you need interoperability between multiple compilers compiling to WebAssembly, well, you can do that. You have to define an ABI, the same thing you do in native code, right? You have to agree upon what your compilation scheme is and stick to that. But that is something you can define on top of WebAssembly. It doesn't have to be built in. And that carries over to GC as well. And as far as I'm concerned, this is like key to WASM's success as a language-neutral technology. Okay, so what we instead want to do is really we want to provide GC, but stripped down to the bare basics. So no complex type system. It should be like the types in it should be very simple to produce and to consume. And the basic idea is we just describe memory layout. We just tell the GC how we want to lay out our data in memory and let the GC figure out how to manage it. It's not like something that is directly related to source level types like objects or something. So that means if you have a high-level language with some Rube Goldberg type system, you must lower it to WebAssembly, like you lower code as well. You have to lower your types as well, right, to whatever simple thing WebAssembly actually provides. And the key takeaway here really is you have to do it more or less the same way you do on native code. That's what I mean by garbage collection actually being low level as well in our proposal. And another part of it is that the whole design of this extension is supposed to be pay-as-you-go. So again, there should not be any hidden costs. All allocations are explicit. And also, if you don't use any of the GC-related instructions or features, you should not pay anything. Yeah, and as part of that, we wanted to avoid all sorts of old problems, like language-specific constructs, heavyweight object systems or types. Things like reified generics are certainly not something we want to adopt. Sorry, Andrew. Or unsound type systems like arguably in Java, where you can have method or attribute access failures at runtime. And also we want a modular semantics, so WebAssembly has a module system, a very strong one, which full encapsulation, and you want to be able to lower, like when you do separate compilation in the source language, you want to lower the modular structure to WebAssembly. And which means that things like nominal typing, for example, on the low level would be problematic because if your source language is structurally typed, then there's no way to maintain your modular structure if you have to lower it to a nominal system. Okay, so what is it that we have? We really stick to a couple of very simple primitives. First one just being tuples. It's one thing you can allocate, and they're like this heterogeneous thing that you can statically index, and then kind of the opposite are arrays, which are homogeneous, but in exchange you get the ability to dynamically index into them. And this distinction all has to do with typing, right? So I'm gonna get back to types in a minute. And then the third thing we have is scalars. So most managed languages actually use some kind of tag pointers so that they can unbox integers, and we want to make that available as well, right, as part of our low-level story. So that is another feature we directly provide. You can use unboxed integers in the pointer space. And the last bit is just functions, which are essentially just code pointers. So again, no closures, just code pointers. And just briefly mentioning, there's one fifth thing there, which is like external pointers. So you can embed pointers to host objects as well if you need to, but I'm not going to talk about that here. So these are our primitives. That's all the GC proposal provides. And everything else has to build by you on top of that, right? So the GC knows how to manage these things, but that's all it knows. So more concretely, in terms of WebAssembly syntax, we have these new forms of type definitions for structs and arrays now. And on the right-hand side, you have new forms of value types, is what they're called. So these are the types of locals or parameters or something, where previously you only had like I32, F64 and stuff. You now have these reference types, which are reference to a specific type. And there's a flag on them as well that tells whether this can be a null or not. So we distinguish nullable and non-nullable for performance. And yeah, the third thing is this scalar kind of thing that's modeled as a reference to an I31. Why I31? Well, we have to be portable, and we want to have predictable performance. So the largest type we can guarantee across all relevant platforms to be actually unboxed is like a word size of 32-bit. We need 1 tag bit, so that's how you get to 31, right? It may seem a bit odd at first, but that's the situation we have to maneuver. Yeah, and so these are the types, and then you have the kind of canonical instructions for dealing with them, so for allocating stuff and for accessing them. And there are a bunch more instructions, but really this is the core set, and the others are more like convenience. A couple of side notes here. So first of all, the allocation of these things happens on the GC heap, which is completely disjoint from the WASM linear memory. There's no interaction whatsoever. And this heap also is not exposed to programs at all, right? You get these references, but that's all you have. And these references are completely opaque as well, so you cannot observe what address is underlying them as a representation. So programs cannot observe that, and again, the reason is safety, right? We don't want native pointers to leak into the program space. So you can't store them in memory either, because that would like break this abstraction, violate this abstractions. But instead, we repurposed this notion of tables that already existed in WebAssembly for functions and indirect functions, and generalized them to arbitrary reference types. So that is your storage for references. You can now define tables, multiple tables, and store references in them. And that gives you a numeric index, which you could store in memory, for example. Okay, so type system, I kind of glossed over that so far, references are strongly typed, right? And the motivation here is that we want to avoid any overhead whatsoever in accessing heap allocated objects. So there should be no runtime check, no matter what you do. Like, again, unlike the JVM, for example, where semantically there is a runtime check for every access. VMs often can do dynamic optimizations and stuff to get around that, but that's not what we want to have in WebAssembly. So for example, if I have like a type declaration for a point, like a tuple of 3 fields, and I could implement like a little function that just accesses the first thing there, the first component, and this struct get is just a simple load, right? That's all it does. It's a load, indirect load through a pointer, and it can never fail. There's no check involved whatsoever. And you also know that what you get back is actually an F64. So this is all validated by the type system. And this typing is deep, right? So it's not just we know that this has fields of F64. You could, for example, say I define an array type of reference over points, then you know like all the way down what you get. Like when you do multiple indirections, you already know what you get. So all this typing is deep, like you really expect from a proper programming language. Yeah.
So prior to GC, to generate this kind of code, you wouldn't have structs, or you've done your own indexing, so on and so on?
Prior to GC, yeah, you would have to lay out all this in memory, essentially. Yeah, that's yeah, and this is a completely different way of doing that. So. There's also subtyping, because often you want to compile a language, source language that has subtyping, and ideally, whenever you use subsumption in the source language, you don't want to have like a conversion in the target language in WebAssembly. So we try to make the subtyping permissive enough that most of the time you can get away without doing something. So you have the usual width and depth subtyping on structs and arrays, but it's actually sound, so on mutable fields, it's invariant. So we just, only for that reason, we actually have to distinguish mutable and immutable fields just to have more permissive subtyping while keeping soundness. And again, soundness is crucial, right? Because otherwise this whole strategy of no runtime checks would fail. On functions, you have the usual thing, contra-covariant subtyping, and that, yeah, means that in many cases, at least, source level subsumption will just work when you lower, after you've lowered your types. But of course, that doesn't always work, right? And it can't always work. It's basically impossible to have a type system in WebAssembly that can subsume all source level type systems in the world, right? That will never fly, especially when you have this constraint that the WASM type system should be simple and fast to validate, right? So we can't afford anything super complicated. So there are certainly limitations to that. Sometimes it won't work out and you need a workaround. So we need some kind of escape hatch. And the obvious escape hatch is casts. So the other thing we have as part of the GC proposal, it introduces the notion of runtime casts. So for example, an instruction that's just a downcast and traps when it fails. So this is where the producing compiler knows by construction that it can't fail. It would use this instruction, but it can also use a branching cast where you can make a binary decision on a type. This is a type dispatch if you want. So this is really just an escape hatch for the low-level type system. It's not primarily intended to implement source-level casts, right? So you will also probably use it when you compile source-level casts, like casts in Java, instance of checks or something like that, but it may not be sufficient for that. For the same reason as before, we can never subsume all the source languages dynamic type systems either, right? So again, you need to do something in addition, and that is, in general, you have to implement your custom type representation if you have more complex runtime typing semantics in your source language. You have to implement that yourself, and at some point it will probably go down to WebAssembly casts, but that is just one part of the building blocks. Okay, so for the rest of my talk, I just want to run through a few examples of common things you implement for managed languages and how they would map to this thing. And basically, the whole idea is that none of that should be surprising. You basically should do the same that you do in the native code compiler, right? So this might just all be totally boring because I'm just showing you things you already know, but you just use them in WebAssembly as well. Before I do that, a very quick recap of some of the things about WebAssembly for those who haven't seen it perhaps. So WebAssembly is a stack machine, so you have instructions like this. So this would be an addition of two constants, right? And that could be reduced to this one constant. And that's actually how the execution of WebAssembly is specified formally by a reduction semantic. So it literally says something like this as a reduction rule. Instructions are also typed, so that's what we get validation out. And since these are stack instructions, they all have a sort of function type, the left-hand side saying what you pop off the stack and the right-hand side saying what you push back to the stack. Like you see with the add instruction, it's like the obvious thing. And the main reason I'm showing you this is, so this is the WebAssembly text format. And one feature it has on top of this stack-like language is what we call the folded syntax. So you can actually write this sequence of instructions this way as well. So as if they were in expressions, right? This is really just syntactic sugar. It has no semantic meaning whatsoever. It's really desugared into the same thing, but it makes code much more readable because you see how things are grouped together. And that's why I'm showing that here, because I'm going to use that in some of my examples to make them a bit more readable. So when you see this, basically you can completely forget that there's a stack machine underneath. Just read it as a very verbose expression syntax, right? There's also structured control flow. I think I'm going to skip over that because it's not actually relevant to anything in my talk. So let's jump to examples. The most obvious one you want to see probably is how to compile classes, right? That's the ubiquitous thing in the object-oriented world. Let's take a simple example in some pseudocode language. I'm not picking any specific language here, but I guess this is something you can do write in a language like Java and others. So it's just a class with one instance variable, 2 methods. And let's say there's another class which is a subclass of that, which adds another method and another instance variable. And as most of you, I'm sure, know, is the standard way of compiling this is so an instance of C would be represented as a block of memory, which has all the instance fields, so A in this example, but the first thing is a method table pointer, or vtable as the C++ folks call it. So this vtable points to another heap or memory allocated data structure, which is just a vector of all the methods of that class. And this one is shared between all the instances of that class. And similarly for D, you just add the additional fields, but the structure is the same. So this is the kind of thing we actually need to lay out or emulate when we compile to WebAssembly as well, right? We have to implement that ourselves. At the same time, so D is supposed to be a subtype of C. So ideally, we want to define types in WebAssembly that preserve the subtyping relation, so that the layout for D, so a reference to D is actually a subtype for a reference to C. And that implies also that we have to have the corresponding subtyping between the method tables, so that the width subtyping works out. Okay, let's see how we do that. So first we want to lower the class C into type definitions. So we introduce one for instance, and that should just match exactly like this box I show you on the bottom. Unfortunately, my pointer isn't working here, so I can't really point at things, but you see what I mean, I hope. So it has this one instance field, which is the I64, and the first field is the method table pointer. And that again is just a struct of 2 reference to containing function pointers, which we also have to define as types. By the way, I'm using somewhat more pseudo syntax here for the type definitions. That is not really WebAssembly syntax, but that might be a bit more readable. I hope you appreciate that. So the function pointers we also have to declare as types, and you do it as you usually do when you compile these things. You have functions that take the appropriate arguments, but as a first argument, they always take a pointer to the instance itself, right? So this should all be very unsurprising. And similarly, we lower class C. Now the structs correspond to the boxes on the right, and they have these additional fields there. Otherwise, they are the same. And we have this one extra function, and that takes as a parameter a reference to a D, because it's a method introduced in class D. So far everything is great. This actually works out with respect to WebAssembly subtyping. The type D is a subtype of C, and so are the vtable types. All great. One more thing just for completeness. Let me also show how some of the code would translate. So say the function, the method f there, we lower that to a WebAssembly function on the bottom that takes the parameters as defined by the type there. So an instance pointer, this pointer, and the actual parameter. And then we just do an addition on that, and the struct get there extracts the instance field from the instance, right? So this is just the struct get1 extracts the A field from type C. And for completeness, let's also look at an elimination side. So say we have some variable D, which is an object of type D, and we invoke the inherited method f on that. So that lowers into something like a call ref. So call ref is an instruction for calling a function reference, so an indirect call. And what reference are we calling? Well, the thing we have to call is the method f. So we have to, the only thing we have is a D, which is the instance. So we first have to get to the method table. That would be the struct get 0, the first struct get 0. And then we have the method table, and from that we have to extract the pointer to f itself, which is the second struct get. So this gives us a pointer to f. We call that, and in addition we have to pass the appropriate arguments, the first one being this argument, which is D itself, and the constant, right? So again, I hope this is not surprising at all. I'm just showing you the obvious. Okay, so far so good. Now let's slightly modify the example such that D overrides F. This is where it gets a bit more interesting. So lowering of C doesn't change. For D, we now lower as before, except that here we now have, in the method table for D, we have D.F. But one thing you see here is I wrote C there. Why did I do that? Well, and that is exactly where we run into one of the limitations of the WebAssembly type system, and this is obviously, of course, a well-known problem that the this argument is covariant in these object encodings, but that doesn't work with contravariant sound function subtyping, right? So the WebAssembly type system isn't strong enough to know that the covariant subtyping would be sound here, so we can't use it. We actually have to use C there as well. So the type for DF has to be the same as for CF. Otherwise, the subtyping wouldn't work out on the WebAssembly level. If we do it that way, then it works out. But of course, that also has some implications for how we actually implement a method override. So just as a reminder, this is how CF looked, same as on the slide before. But for DF, the problem now is that we get as a parameter a reference to C, not D, right? So the first thing we have to do is we have to downcast it to an actual C, an actual D. And the producer, so the generating compiler, of course, knows by construction that this will always work out fine unless the compiler has a bug. But the engine, the WebAssembly engine, can't know that, right? It can't prove that. So that's why you have to do a cast there. Yeah, and then you do the addition as before. Okay, so this is one point where we run into limitations, and one of the things we maybe can lift to some extent in the future, but in general, there will always be limitations like that. You will always have to use cast somewhere. So a related example is closures. I actually might want to skip over that because it's very similar. So this would be in a functional language where you implement closures. But if you know that closures are really, you can view closures as a degenerate case of a class that has just a single method, right? Which means that you can flatten the vtable into the object itself. That's how they are compiled. That's also how Java, for example, models closures within our classes. So the point being that you run into exactly the same problem here. So you define a specific closure type that is a subtype of the general closure type for a given function, and you have to do at the call side the same kind of downcast of the closure environment to the function's own environment type. And the same type system extension that would fix the thing for classes would also fix this thing for closures. So that's something I eventually want to get here. Another example, what do you do with generics? Well, we don't have generics in the language, so you do the obvious thing, you do erasure, right? So as a stupid, simple example, let's say we have a generic pair of two-dimensional vector, if you want, over T, and we define two generic functions to just do the projections. Boring example, but fits on the slide. So because you can't do generics, well, you have to use the top type. The top type in WebAssembly is called any, so this is an any ref. I just declare the pair as a struct of two any refs. And then the functions, they just work out because they also just return any refs. There's nothing I have to do here, but I have to do something when I want to invoke these, right? So let's say I want to interpret this as a two-dimensional vector and want to compute its its absolute value. So I have something like this function, which takes the square root of, oh, there are some invocations of square missing there, I just noted. Right, so there should be, both components should be squared, of course, for this formula to be correct. But despite my bad math here, this would be lowered somehow into WebAssembly, and my animation was somehow broken as well. So first of all, one thing we have to do is we have to define a type for boxed floats, right? Because we need something we can pass to this pair function that has to be a reference, so we have to box up floats. So that would just be a singleton structure that contains an F64. And then the function apps itself, well, what does it do? What you would expect, it has the two calls, and because they return any ref, it now has to downcast to the float type, the box float type, before it can access them. So that is another place where we have to insert casts, but this is really like how Java also does it officially, right? Okay, so let's switch again to the functional world a little bit and talk about algebraic data types or variant types. As an example for that, let's assume we are in a nice functional language and want to write an interpreter for WebAssembly itself. So we need to define some data type that represents the WebAssembly instruction set, right? So just showing a bunch here like knob and drop instructions and branches and blocks. So we need to lower this as well, of course. And the idea here is we want to do what functional compilers also do, which is unbox the nullary constructors. You don't want to heap allocate them because you really just want to represent them as an integer. They're really just like an index representing the constructor. So the type itself we want to represent as type any, which is kind of the union of all reference types. And then there are two concrete cases. One is I31, which is the unboxed nullary constructor case. And then the box case is going to be a supertype of all concrete constructors that are not nullary. So concretely, we have one type for each of the constructors that has parameters, which is a struct of the respective thing. But the first element of this struct is an index telling you what case you're in. And if you just have the supertype, you can use that to do your dispatch. So let's look at an example of how you would use this in practice or compile this in practice. So let's say we want to write an evaluator for WebAssembly. So part of that might be a stepping function, which takes a stack and a single instruction and returns the modified stack and possibly some kind of list of continuation instructions. And the way to implement that in a functional language is through pattern matching, obviously. Ignore all the right-hand sides, they don't really matter here, but what matters is that we do this pattern matching on the left, right? So we dispatch on the constructor of the data type. So how do we lower this? Well, we have a function that takes the respective parameters, so a stack and an instruction reference, and now we have to implement this dispatch. So the first thing we do is we look which case we are in. Is it a nullary constructor or not? So we do a branch on cast with the box type. We could also do it the other way around, but here I use the box type. And this cast, if it succeeds, this instruction would branch to some label L, which would be lower down in the function. I'm not showing that yet. And if the cast fails, it will just fall through, and the next instruction is executed. So in that case, we actually know, again, the producer knows by construction it has to be an I31 then, so it can just unconditionally cast that down to I31, the instruction, and then it can get the index out of that, so that would tell us what constructor we have, and then we do a BR table, which is dispatching on that number and jumping to some labels, one for each of the instructions we need to implement, and they would be somewhere further down in this function. And the other case is if we took the branch to L, so if we are in the non-nullary case, then we somehow get here, and there we can, one thing, it's a bit difficult to see here, but one thing that the branch instruction does is that the label actually receives the reference on the stack as well, but with a refined type. So when we arrive at L, we have on the top of our operand stack actually a reference not to the instruction type, but to the instruction end type. So we already know it's one of these things. So we can just get the index field there, And here's where the kind of function expression notation breaks down a little bit, because the operand to the struct get is already on the stack implicitly. We can't really write it here, but just assume that it's coming from the jump. So again, we just do a dispatch, a table jump on that index, and then the rest of the function just implements all these cases we have to jump to, right? That's all you do. Okay. And my final example is something called uniform representation. So that appears when you have a language that is highly polymorphic. So functional languages would be an obvious example where you have type inference, and many types you infer are polymorphic actually, and you want it that way. The extreme example of that is, if you want, is actually untyped languages or dynamic languages, where everything is polymorphic, basically, right? And the thing is with these languages, so people who have not seen implementations of functional languages often assume when you have polymorphisms with generics, right? You can always just statically type specialize them. But that doesn't work in these languages because their type system is actually much too powerful for that. So they have things like first-class polymorphism, polymorphic recursion, other things that make it impossible to statically know all the instantiations that occur during execution of a program. This is related to what you also have in OO languages if you have virtual methods, as they would call them in C++. So generic methods, right? In C++, they are not allowed, and the reason is exactly that. It doesn't work with static type specialization. So for functional languages, this is like not an option at all, because polymorphism is everywhere and it's typically first class and other features. So you can't do that. So, but also polymorphism is everywhere, so you're crossing the boundaries between monomorphic and polymorphic code all the time, and you don't want to do boxing, unboxing translation, conversions all the time either, because that would be very costly as well. So what typically these implementations do then is that they represent all values uniformly, so that you don't have to convert them. You all represent them as references in WebAssembly speak under the type any, right? And then only when you need to access a value concretely, you have some elimination form, then you can't, like, cast it down or extract the correct type. So I implemented a whole like ML compiler on top of that as kind of a proof of concept thing. And I'm going to show you what kind of representation that used. But this roughly is what also the OCaml compilers would be using, or the Scheme compiler is using something very similar. So for example, the ML type has a type bool, which in this uniform representation you just represent as a I31 reference. There might be places where you can unbox it locally when you use an I8 or something, but in the general place you will always represent as an I31. And similar with characters, which are a bit larger than a bool but still fit in an I31, so you can use that for that. Actual integer types, well, that might depend on what value range you want to have. So you could either use I31 as well, or you have to box it up into a struct, maybe even a struct with an I64 in it. You can also have a mixed representation, right, which would be, for example, what Scheme would be doing with its numeric tower, where you allow both these things and then convert as necessary. Floats you have to box up because they can't be stuffed into a reference. And then strings, well, just an array, like say an UTF-8 encoded array of bytes. Tuples, you already saw that with the pair example. That would be a struct of any refs now, right? Because the thing being with polymorphism, you can abstract the component types after the fact, so, and you never know beforehand when you have a tuple what context you're passing it into. So you can't assume beforehand that it will not be polymorphic some way. So you also have to use a uniform representation there. And I already showed you how well, I skipped over that, but I sketched how closures work. And data types I showed you on the last slide. ML also has a very advanced module system, which is higher order and everything, so that also would lower to structs and functions. But the point being here that, yeah, I31 is relatively important here so that you can have all these unboxed representations. Okay, those were all the examples I wanted to show, just like as my last slide, essentially, a number of limitations. So the one you already saw, of course, is that we have to do casts in a number of times. And some preliminary numbers reported by us, by the compiler writers, was that they saw like 2 to 4% overhead in that. So V8 has an option to turn off the runtime checks for casts. So you can measure that quite easily, what the cost of the actual casts is. I also said that there's no automatic interop between languages, so you need to define your own APIs. And then maybe more interesting thing is that, well, this is of course a feature that has to cover certain use cases, but there will always be use cases that can't cover. So there are languages that have very particular needs for their GC. So one example would be Go, which made this interesting design choice to allow interior pointers into objects, which we can't directly represent because we don't want to burden every WebAssembly engine with implementing this mechanism because it's quite horrible. Then there are languages like Prolog or Haskell, which have things like logic variables or lazy thungs, which once they get bound can produce chains of indirections that usually their garbage collectors want to shorten and eliminate. Maybe there's a way to get an abstraction for that, but right now they wouldn't be able to use this optimization. And the biggest one is where we're still kind of like have no good ideas what to do about weak reference finalization, right? There are so many different semantics for that out there. Every language has its own. They all are incompatible with each other. Some even have 3 different versions of it. So what is the right abstraction for this kind of thing? That doesn't mean that we're adding all of them. And also what does maintain all the good properties we want to have. And a final thing I need to mention is one of the drawbacks of having this typed assembly language is, of course, that a compiler targeting this language has to produce this type information. And that could be problematic if you have a legacy compiler which throws away its type information too early in some of the representations, then it might not have enough information in the backend to generate this, right? So if you have a compiler and you want to write a new backend that targets the WebAssembly GC extension, then this might be a problem for you and you might have to do some extra work. Okay, that's basically what I had. Yeah, the main takeaway I wanted to bring across is that this is, although it's GC, it's low-level GC, and you still have to do everything you have to do on native, more or less, minus implementing the actual GC. That's the only thing this extension gives you. And this is like a version 1.0 feature, so there definitely is much room for improvement, and we will, based on feedback on what we get from clients, I'm sure we will add more stuff to that over time. Okay, that's all I had. Just a reminder. And I'm happy to take questions.
We have time for a couple of quick questions. Anyone wants to come to the mic?
So I imagine that there will be some runtimes that choose not to implement the GC proposal for one reason or another. One, I guess, is that permitted? And even if it's not permitted, they're going to do it anyway. So what effect do we think that would have on the ecosystem? Would it bifurcate the ecosystem into WASM modules that run on those runtimes and WASM modules that do not?
Yeah, that's an excellent question, and there's an ongoing discussion about that, introducing some notion of profiles into WebAssembly. I think this is absolutely essential. GC is not the only feature that some ecosystems might not be able to implement, like threads is another, continuations is another, SIMD is something that is super large and like an embedded platform might not care about or not get any benefit out. So what I have proposed is that we introduce like a general framework for defining profiles, which define very precisely certain language subsets. And then these environments can pick whatever subset they can handle, right? And GC should definitely be like a profile or GC less. Determinism is another important one, by the way, for blockchains. They absolutely need a deterministic semantic, so there's going to be a profile for that.
You didn't actually talk about GC itself.
Right.
I'm curious, one thing is, does it have to use the static type information?
What?
So the sort of static type information, does it need like metadata associated with variables and so on to trace the references?
Of course, the specification doesn't say anything about the GC, right? You just like, just works. But there are some implicit assumptions, of course, about the performance of a GC. Like, since you can do rather fine-grained allocations, a GC should be able to handle frequent and fine-grained allocations. Other than that, it's completely up to the engine and probably the environment it's running in, right, which is the best implementation technique for that. We don't prescribe anything in particular. That's left for quality of implementation issue and depending on ecosystem, hardware, whatever, right?
Other than it has to be type safe.
Yeah, but that is validation, right? Like that is not, the GC itself doesn't, I mean, operationally, this whole feature is actually quite straightforward. There isn't anything fancy happening here. It's all that we have to validate it so that we know that nothing bad can happen when you access GC objects.
I guess I'm missing something there, because I mean, I'm familiar with the C#, the .NET GC, and it actually has to look at type information so it knows object layout and so on. But you've got
right.
that implicitly in the objects.
Yeah, you need to have some minimal type information, of course, so you need to be able to distinguish these four kind of reference I showed you, right? But that is much simpler type information than the actual WebAssembly type system, right?
Okay, thank you very much. Let's switch to the next speaker.
So you should be able to see my screen. Perfect. So welcome to my talk on the applicability of annotation-based source code modification in Kotlin. My name is Markus Wenninger. I did this work together with my bachelor student Daniel. And first of all, please let me give a motivating example. So imagine we have a bank account where we have a current balance, how much money is on the account, and we can withdraw money from that. And what we mean with annotation-based source code modification is we would like to be able to add annotations to, for example, fields, properties, or parameters of our methods. And then, during compilation or at runtime, certain checks, for example, could be added. So when we create a new account, that the balance should be positive or 0, or that when we withdraw a certain amount, that the balance is still positive. And this should be checked in every function that works with such an annotated property. So this is what we understand as annotation-based source code modification. And we have a look at that in Kotlin. So how can we achieve that in Kotlin? How does compilation work in Kotlin? So we have Kotlin source code, and typically we get Java bytecode out of it. But Kotlin is multi-platform, so we can also get JavaScript code from Kotlin or iOS code and some other compilation targets. Kotlin inside uses an intermediate representation to generate all these target codes. And now the big question is, when we see an annotation, how can we react to that annotation to modify the source code? And in the best case, not only for one specific target, but for all our targets. So which ways exist in Kotlin to process annotations and to modify the code? Generally, there are 4 different ways how we can do that. The first one is how we can process annotations. There is cupt. which is the Kotlin annotation processing tool. This was the first tool introduced to work with annotations in Kotlin. Then there is KSP, which is the Kotlin symbolic processing. There is our custom compiler plugins. They're extremely versatile and can attach to various phases in the compilation process. And then there are load time approaches that do not work during compilation, but when the program is run. For example, we could use a custom class loader or Java agents, which most of you are probably familiar with. I will not talk about Cupt because Cupt is already in maintenance mode, so no new features will be added. They try to keep it working, but they will not do much more there at JetBrains. So I would start with KSP, Kotlin symbolic processing, where the basic idea is that we iterate over symbols. We do not have the complete us there, and we generate new code. So I brought an example with me. What we have to do is that we have to inherit from symbol processor, and we have a process method where we have a resolver. This resolver is there so that we can find things. We can, for example, use the resolver to find all symbols that are annotated with a certain annotation. But we could also say we want to find all files, we want to find a function by its name, and so on. KSP revolves heavily around the visitor pattern, so we can write our own visitor where we can visit about 25 different things, properties, functions, classes, and so on. And these visitors typically have the code generator passed into them, so we can create and write to new files. And then we apply our visitor, for example, on all our annotated entities and generate something out of those annotated entities. What is the big problem with KSP? Because the code that we can write is quite straightforward. The big limitation is we only have code generation, no code modification. So we cannot modify the program we are looking at. We can just create new files. And there is no analysis on expression level. We have no information about the statements of a function. We know which parameters go in, we know which types go out, and stuff like that, but we have no information about the content of the statements. So that's where custom compiler plugins come into play. They are great. They are super because they can provide additional operations, including modifications, in various compiler phases. So Kotlin's compiler is split up into multiple phases. You do not have to look at the whole picture. I will guide you through the most important parts. On the front end, first we have the lexical analysis and the syntax analysis, so we get a typical AST. Then this AST is enriched with semantic information, so we have a front-end intermediate representation where we perform the code analysis on, or where Kotlin performs the code analysis on. And then, independent on which language we compile to, JVM, iOS, or the web, we have a common backend where optimizations are performed on an intermediate representation. And then only after these optimizations have been performed, there is a last target-specific backend, for example, a JVM backend or the JavaScript backend, where the final translation is performed. And the cool thing about this compiler structure is that we have different points where we can attach to and add our own plugins to modify what is happening during compilation. So there we have at least 5 points, and for those 2 points, so in the common backend, we wrote an example which is hosted on GitHub because there are really nearly no examples out there, and I want to guide you shortly through this little example. So we have, again, a visitor pattern, and we are currently in the method visit function new, so we visit the function for the first time. And we can get the body of that function. If you remember the example from the first slide, what we want to do in the function is, if a parameter is annotated, we want to generate verification code that the parameter is in the correct state. So what we do is, and we can do this very easily, we generate a new block, a code block that was not there before in the source code, by having an IR builder. So we build intermediate representation blocks. And then we can just iterate over every parameter of our function. Then we can check the parameter if it has a certain annotation. So we check, is the parameter annotated? And then we can generate IR nodes, which is hidden in this generate verification function call method that we have written. And with this little plus in front there, we can add this IR node to the block that we just generated. So we can add completely new code independent of the target language. And then when we have generated all verification codes, we have this one block of code, which we then say, this should be the first statement in our function. And that's all we have to do to have new code in the existing code. What is the main limitation here? There is nearly no documentation. Compiler plugins are typically used internally at JetBrains to develop stuff, but you can do your own. And so our references out there on GitHub, you will have a QR code in the end if you want to have a look at it. And just for the sake of completeness, I also want to talk about load time approaches, which are approaches that intercept classes when they are loaded. So typically, we have some class that is stored in a class file. When it is loaded, we want to instrument it, or we want to weave code into it. This is often supported by libraries such as JavaSys or ASM. So first of all, we have to find the location where we want to add bytecode to. Then we have to generate that bytecode. With JavaSys, this is really easy because you can provide the code that you want to add as a string, and the bytecode is automatically generated for you. And then we just have to insert it, which is also a one-liner with JavaSys. So this is really easy, and that there are a lot of examples out there. But the limitations here are this slows down application start because the code is modified on every program run, not only once during compilation. And this only works for JVM, so there is no automatic multi-platform, which is a big minus if you want to go multi-platform. So to summarize the advantages and disadvantages of the 4 different approaches, CUPT, KSP, custom compiler plugins, and load time approaches, is CUPT has its advantages. You can reuse annotation processors that you have already written for Java. CUPT is, you can imagine it as a wrapper around the original Java annotation processing tool. KSP is Kotlin idiomatic. That means it knows about Kotlin-specific things like initializer blocks, data classes, properties, and so on. Things that did not exist back then in Java. It is faster than CUPT, nearly double the speed, and it is multi-platform. Custom compiler plugins have the same advantages as KSP, but are still more versatile. And and load time approaches are easy to implement, have good tool support, many tutorials out there, but we also have disadvantages. CUPT has a lot of them. It is slow, no multi-platform, does not know about Kotlin-specific things, and code modification, the thing that we focused on, is nearly impossible, but it is possible with a lot of hacky and tricky, dirty hackarounds and workarounds. KSP has no code modification at all, only new code generation, and no analysis on expression level. Custom compiler plugins are very complex and really lack documentation. I really hope that there is something happening in the future now that K2, the new compiler by JetBrains, is introduced. And load time approaches slow down the startup, are not multi-platform, but JVM specific, for example, and also do not know about Kotlin specific stuff, but Java agents have been written for Java, but can be used with Kotlin. Yeah? So the main takeaways, I tried to make it as fast as possible since we're a work-in-progress paper. We have 3 different compile time approaches, CUPT, which you should not officially use anymore, KSP and compiler plugins. You have load time approaches like custom class loaders or agents. They perform transformation on the JVM level, on the bytecode level. Compiler plugins are really cool, extremely versatile, but really complex. JetBrains, if you hear this talk, please provide documentation there. And for future work, we have planned to study more how Kotlin annotations are currently used. So a GitHub study, how annotations are used there. And what would be really nice is to have a library somehow similar to JavaSys to provide source code as a string and get IR nodes in the compiler plugin that you can plug into your existing code. So code string to IR. So my name is Markus Weninger, and there is a link to our repository where we have a reference implementation for the compiler plugin and a Java agent that can modify existing source code. Thank you.
Thank you, Markus. Now, part of our goal with the work in process papers is not only for you to ask questions, but if you have feedback or ideas to offer the work in progress, feel free to do that as well. So we have time for a couple of people to query or comment.
Questions from my side to the audience. What would you probably use? Do you have ideas where you could use compiler plugins in your work? Do you have ideas? What could you modify at compilation time that you would like to have automatically in your source code? Do you have any ideas? Do you see applicable fields where you could use source code modification in your work?
Well, I have certainly used approaches like this to try to add hooks for, say, transaction-oriented processing, or for persistence, or for distributed system calls, that sort of thing. So a kind of extension of the semantics of the underlying thing by rewriting.
That's true. We are thinking about performance monitoring, for example. So you could add certain code and hopefully hot paths to see what happens. Any more input from the audience? I saw some more hands on the right-hand side, I think.
Try to use the mic so that the folks at home can hear. This is being streamed.
So anything related to, for example, allocation of objects, tracking lifetimes, an extension of what Elliot said, like calling, for example, native code. This is all very interesting points that we really need to sometimes dig into the compiler to actually inject phases into compiler to add nodes that will basically call our profilers. Having like a tool that allows us to do that without having to dig into the compiler would be amazing.
So a tool that can summarize what is happening in your program without having to look at it yourself.
Sometimes you use JavaSys or even ASM, but sometimes you actually need deeper information of what's happening inside the runtime, and sometimes it's easier to express that using IR nodes.
Yeah, so I can discuss this with a bachelor student who will also do a master thesis, so probably he will listen to this talk and take in some of your advices or suggestions. Thanks.
Okay, thank you very much, Marcus. And the last speaker for this session, he's coming up right now.
So, hello everyone, my name is Serhiy. Today I'm going to present you CloudJet, our just-in-time function as a service optimizer. This is work in progress effort. I would like to start with introduction into function as a service. So function as a service, or FaaS, is a novel cloud computing model for fine-grained computations. In FaaS, applications are designed to be composed of slim functions, and there's an important bit, around half of all functions, according to Microsoft Azure Function Study, they execute under 1 second, which means they are very short-lived. And around 70% of all functions, they are called at most every 20 minutes, or less frequent than that, which means they are called very infrequently. In function as a service, you don't have a server that is constantly running your application, your functions. Therefore, resources are allocated on demand, which means that if there is an invocation to some function, but there is no available function worker for that invocation, then a call start happens. Also, in function as a service, it is the responsibility of cloud service providers to provide computing infrastructure for running functions, which not only makes it easier for cloud customers to deploy their applications, but also provides cloud service providers with a more substantial amount of control over computational resources, and it allows cloud service providers to employ some optimizations. So functions are mostly written in high-level languages, according to another study. These languages execute atop a managed runtime, and managed runtimes are usually heavyweight processes which leave a significant memory footprint, ranging from tens to even hundreds of megabytes. They take some time to load and initialize before they become actually available to run the actual code. It can take tens of milliseconds, and if a managed runtime features a just-in-time compiler, then it is also subject to warm-up. And therefore, traditional language runtimes, they were designed and they fit for long-running applications such as servers. However, we claim that for us is not the case for it. So here we can see a structure of a call start. At first, we need to initialize a function worker, which can be a VM or a container. Then we need to download the code inside this worker. Then we initialize the language runtime, run the function initializer. These are all parts of a call start, which can take up to several seconds. And only after that, we actually start executing the actual function code, which, as we saw before, usually takes less than 1 second on average. Therefore, we claim that frequent and slow call starts can take up a significant fraction of the overall execution time. And in our project, we are mainly focusing on improving these parts of the call start that relate to language runtimes. So, a possible solution to fight slow call starts is to employ an ahead-of-time compilation. With AOT, all code is compiled into standalone native binaries beforehand, before execution. No interpreter nor JIT is needed, just a slim runtime that doesn't pay a price for the features it is not going to use. And no profiling and just-in-time compilation is involved. And all this in combination results in faster startup, lower memory footprint, and immediate peak performance. Also, such ahead-of-time compilers as, for example, GraalVM native image, they also run static initializers for classes during compile time, so they are not always executed at the beginning. We executed a couple of micro benchmarks based on 3 Java applications written in popular microservice frameworks. On the left plot, we can see the improvements in the footprint, and on the right plot, we can see more substantial improvements in startup latency. We used GraalVM native image to ahead-of-time compile our applications, and we compare it against traditional JVM. So another good thing about GraalVM native image is that it's a trending technology, which is being widely adopted in production. As we can see from these tweets, it improves execution performance. It makes it easier to compile Spring Boot applications. Another example of production adoption of GraalVM and integration of GraalVM into Spring Boot. However, ahead-of-time compilation comes at a price. Ahead-of-time compilation itself is a very resource-consuming task that can take up to several minutes even for simpler applications, and it imposes high CPU and memory utilization. Also, ahead-of-time compilers, they usually operate under closed-world assumption, which means that only those components that are known at compile time will be included in a final image. Therefore, only those components will be available at runtime, which limits use of some of the dynamic features, such as, for example, reflection or serialization in Java. So we claim that ahead of time applying ahead of time compilation to blindly compile all the functions is not a solution. Coming back to function as a service, again, the same study from Azure Functions. We highlighted some functions on the left plot. Left plot shows us how many functions are actually being executed at each point of time. And on the right, we can see how many call starts happen. So we can see the highlighted, or as we mark them, optimized functions. There is a minority of these functions, but they generate a vast majority of all call starts. So having this in mind, we introduced CloudJIT. CloudJIT is a function as a service platform that features a just-in-time optimizer. As its name suggests, it is inspired by traditional JIT compilers. Traditional JIT compilers aim at compiling methods or other code snippets. CloudJIT compiles entire fast functions. JIT compilers, traditional JIT compilers, they do not aim to actually compile all the functions, all the methods or code snippets. They identify hot paths, hot methods that are executed frequently. It means that they're going to benefit from it the most. So does the CloudJIT. It identifies popular functions that experience the most call starts and compiles only this selection of functions. So ahead-of-time compilation in CloudJIT is performed by GraalVM native image, but it is only applied to a limited subset of functions, as we discussed. And the key component of CloudJIT is an optimizing pipeline. So here is how it looks like. The first stage is a hotspot with an agent. So this is traditional JVM that features a native image agent. This agent is needed to collect agent configuration to enable use of some of the dynamic features, such as reflection. Then the next stage is just a traditional JVM. If the function never gets picked up for compilation, for optimization, then it's going to be the final state of this function. Otherwise, if the function gets picked up for compilation, then a parallel process called native image builder is being spawned for this function, which results in a standalone native image binary. And then the function goes to the final state, which is a native image. In case the function cannot fulfill some request due to, again, closed world assumption limitation, it was not configured properly, then it comes back to the first stage, and the entire pipeline is repeated for that function. So we ran an execution evaluation on the same trace as we saw before, but we downscaled this trace to accommodate its load in a single cluster node. And the results show that we compiled 27% of the functions, and it resulted in 30% on average of call starts optimized, and also memory utilization got reduced by 30% due to ahead-of-time compilation. So the bottom line is we propose using ahead-of-time compilation only for some functions in function as a service model. We propose a platform, CloudJIT, that prioritizes certain functions and selects them for ahead-of-time compilation. And we demonstrate the feasibility of such an approach in a realistic function as a service environment. For the future work, we plan to incorporate profile-guided optimizations for native binaries to improve peak throughput so that the compiler would be able to feature more aggressive optimizations. And we plan to incorporate checkpointed execution based on snapshots to further improve call starts. So that's it. Thank you very much for attention, and see you at the poster session.
Good questions or observations from the audience gathered? I come with one. So if you could flip back to your previous statistics, it had about 30% improvement.
Yes.
So I was a little surprised there in a way, because often we see things where you optimize, say, about a third of things. You get about 2/3 of the performance benefit. So do you have any insight into why this was more just 1/3 and 1/3 instead of 1/3 optimized and 2/3 of the benefit?
Yeah, the problem with this particular execution evaluation is that CloudJIT is still a prototype. It's still a work in progress effort. And we only were able to execute the workload on a single cluster node. And therefore, we had to accommodate the trace to be able to run it in a single cluster node. Therefore, we had to downscale the trace, and therefore, the invocation patterns for many functions, they got simply lost, which means most of the call starts, they were erased by this downscale process. So in this case, we have just a localized view of a single cluster node. But in the future, we plan to run a bigger evaluation.
Right, so in essence, you believe you weren't able to gather enough statistics to drive the optimization in the way that would be most effective.
Yes, it's not only about statistics, but also about the nature of a function as a service itself, as we can see on these plots. So from here, we see that also by optimizing like just a small, this is a simulation, by optimizing a small selection of functions, we can get like a vast majority of call starts optimized. Therefore, it's not only about the platform, but also about the nature of fast invocations. So I know that it's still a prototype, but how easy would it be to incorporate your tool into my existing functions as a service? Because often it is very important to make things easy to use. So what would I have to do to use your optimization technique with my functions? So basically, as I said, the main component of CloudJIT is this pipeline, which means when you so you can keep your original JVM execution environment, and just when you'll have to incorporate some type of heuristics to be able to obtain this selection of functions that are worthy of compilation. And you'll have to basically put this native image builder intermediate process and then you'll just replacing the runtime for your function from JVM to this native image.
Okay, thank you very much. Would Matthew Parkinson identify himself for our next session speakers? There he is. Okay, so you can find Matthew. He's your session chair for the next session, which will begin at 11. Let's thank our speakers again.
Where's the camera?
It's pointed.
Yeah. Okay, so ready to start the next session. So the next talk is going to be on evaluating YJIT, and Maxine's going to give it. Thank you.
All right, hi everybody. So today I'll be telling you about our paper, evaluating YJIT's performance in a production context, a pragmatic approach. So YJIT is a project to build a new JIT compiler for Ruby built inside CRuby. We started this project in 2020 at Shopify, but it is fully open source with significant contributions from people at GitHub. And we try to take a data-driven approach to optimization where we have a large, diverse set of benchmarks. We benchmark often, and we gather detailed metrics to inform our optimization decisions. YJIT is a team effort. It would not be possible without my amazing colleagues at Shopify and GitHub. The team is not that big, but we had several contributors over the years. The goals of the YJIT project are to be able to run any Ruby codes, to be 100% compatible with what we run in production at Shopify, to be able to produce double-digit speedups on real-world Ruby software with a focus on web workloads in particular. And as much as possible, never slow Ruby code down. So worst case, no speed up, but no slowdown either, which is not always trivial. And of course, it must be well-tested and stable. We're seeing increased adoption. YJIT has been included as part of Ruby 3.1, 3.2, this year, version 3.3. We've already deployed it in production at Shopify on multiple internal services, including also public-facing services like Storefront Renderer. And it's been deployed on a few websites that you may know about, some that you probably don't know about. And there's also some internal testing at GitHub, so possibly eventually GitHub is going to run on YJIT. Why did we create YJIT? There's been many projects in the past to create Ruby JITs, including JRuby, Truffle Ruby, and MJIT. But none of these ever really gained much traction, in large part due to practical obstacles. So Truffle Ruby boasts the fastest peak performance, but in many ways it's still a research project. The initial focus was entirely on peak performance, and it is my personal view that they did not sufficiently anticipate or adapt to the needs of the industry, at least not yet. There's also some alternate implementation challenges in there. That is, if you create an alternate implementation of a language and you can't guarantee that you're 100% compatible with the mainstream implementation, people will hesitate to adopt your system. This is not just something that applies to Truffle. It's also been true for PyPy and LuaJIT. People have a lot of respect for the work that Mike Powell did on LuaJIT, but Lua keeps adding new features with new versions, and that makes users hesitate to adopt it, unfortunately. YJIT is based on a technique called lazy basic block versioning, which is something that I developed during my PhD at the University of Montreal. We've published 2 papers about it at UPSLA. It's a technique that tries to achieve type specialization without traditional type analysis. So traditional type analysis can be surprisingly expensive. It can consume a lot of memory and time. And you can also use what's known as a hybrid type analysis, but that requires de-optimization, which can also be expensive and unpredictable sometimes. So the question I sought to ask during my PhD is, can we do type specialization without traditional type analysis? The way that it works, I won't go into all the details, but it does lazy tail duplication or tail splitting, and it uses this as a device to propagate type information. So it's a little bit like lazy evaluation for code, where we generate code as late as possible to try to capture as much context to specialize the code as possible. And the goal is not to create multiple versions of code. It's really to use this as a device to extract type information from the running program. Compared to the work that I did in my PhD, the JavaScript JIT that I had built at the time was a pure JIT system. YJIT uses the CRuby interpreter as a baseline. It also has a multi-platform backend that supports both ARM64 and x86-64. It does runtime value promotion. It makes systematic use of speculation and code invalidation. And we also pay special attention to the memory footprint and gather detailed metrics. So JIT compilers are not just ahead-of-time compilers that run late. They have to juggle multiple trade-offs. There's the performance of the generated code, but there's also warm-up time, how long the JIT compiler takes to generate the code, the amount of memory that the JIT compiler itself uses. So you have to invest time and memory to generate optimized code, but the JIT compiler also has to pay for itself. But in return for all these trade-offs, we also get access to privileged information because we can observe the program while it's running. Many JIT compilers papers in the past have focused exclusively on peak performance, and they tend to completely ignore memory usage. The issue of warm-up time is sometimes swept under the rug a little bit, but the reality is that most people can't really ignore warm-up time. So often the warm-up criteria is just to iterate for as long as needed on benchmarks until peak performance is reached, and it doesn't matter if this takes several minutes, but this is not really a practical approach. So in this paper, we look at multiple metrics that we use to optimize YJIT with production in mind, and one of the twists, if you will, is that we use the C-Ruby interpreter as a baseline for both speed and memory usage, and we also look at warm-up time as how long until we can outperform the interpreter. The reason we do this is that the C-Ruby interpreter is the default implementation of Ruby, and we have to convince people to use our JIT compiler. So we have to be able to reliably outperform the C-Ruby interpreter if we want people to use YJIT. So YJIT warms up rapidly and predictably. The reason why this is important is that slowdowns are generally bad. People expect us to perform at least as well as the interpreter, but also sudden drops in performance can be really problematic, as bad as an embarrassing pause in a garbage compiler. Because if you think Shopify is running, for example, a lot of stores where people buy things, if you have a sudden slowdown and pages start timing out, not only is this bad user experience, but it also translates into a loss of revenue. Your website doesn't work correctly. So the JIT compiler must pay for itself. We have to be able to minimize completion time. We have to amortize completion time. One of the things that we do is we just use a really simple heuristic, which is we only compile a function once it's been called n times. It's really simple, but it also works surprisingly well. It has deterministic behavior. And we also took some steps to make sure that YJIT generates code as fast as possible, where we minimize the number of passes, we avoid dynamic allocations in the backend, et cetera. JIT compilers add memory overhead. Some of this is the machine code that you generate, but the bulk of the memory usage of YJIT is actually metadata that we store, so like type information, de-optimization information, et cetera. One of the biggest optimizations that we've done to reduce memory usage is just to allocate. We used to allocate a large chunk of executable memory when the JIT starts, and then start to fill it up. But my colleague Alan Wood just implemented a technique where we lazily allocate this memory as needed instead, and that translates into a huge drop in memory usage just from this. We've also taken steps to optimize the memory used by YJIT's metadata. So YJIT uses a lot of context object to track type information at various points in the program, and we have antagonistic goals with this, where we want the context objects to be as small as possible, but over time we also want to store more and more information into these objects, so we have to represent this information compactly. The context object in YJIT is a flat object with no pointers, and we do some amount of bitwise arithmetic to say like we have 16 possible types, so we only need like 4 bits per type. We use only 8 bits to track register allocation information, et cetera, et cetera. So in this, I think it's useful sometimes to work backwards to say, I have a budget of n bytes for my context object. How can I use those n bytes as efficiently as possible? So benchmarks, traditionally the Ruby community before YJIT had a heavy focus on micro benchmarks, and there was one benchmark in particular that the Ruby community loves, which is called UpCarriage, which is an NES emulator. It's a cool benchmark, but one of the problems is it's not representative of the code that people use in practice. It does bitwise arithmetic. It has these nice big functions that are easy to optimize. It's also like heavily monomorphic, no polymorphism. So those micro benchmarks test the easy case, for example, where you have no inline cache misses, but you also need to care and practice about how it performs when you do have inline cache misses. So before building Widget, we started curating our own suite of benchmarks with the goal that every person who works on Widget should be able, with just one command, to gather benchmark data very easily and efficiently, make it as foolproof and as easy as possible. We have 3 categories of benchmarks. What we focus on in this paper is what we call headline benchmarks. They're based on real-world Ruby gems with an emphasis on web workloads and things that we use at Shopify. We also have some synthetic benchmarks, like opcaret and the language shootout benchmarks, and some micro benchmarks. I think it's useful to have all 3 kinds because they all provide interesting data points, as long as you don't focus on things like micro benchmarks. These are the 11 benchmarks that we focused on in the paper. Again, all based on things that we think are realistic workloads. The biggest one that we had in the paper had over 3,000 methods compiled. And without further ado, this is the performance in terms of time taken relative to the CRB interpreter for all of the systems, the Ruby widgets that we looked at. And we see that, generally speaking, Truffle Ruby has the best peak performance, although this is not the case on every benchmark. Widget is able to outperform the interpreter by a pretty big margin on every benchmark. And also, Widget performs very competitively when compared to JRuby. This graph, I think, is one of the most interesting ones in the paper. It's our measurement of the memory overhead for all of these implementations. So our production engineers often came to us and they complained because Widget has memory overhead that used to be about 10 or 20% extra memory on top of CRuby. And our production engineers would tell us that's problematic, that's too much. But you can see that the memory usage of JRuby and Truffle Ruby just dwarfs the memory overhead of Widget by 1 order of magnitude, sometimes 2. And this is very problematic. This is part of what makes Truffle Ruby completely unusable at this time in a production context, at least for our needs. We've also looked at warm-up time. This is a graph of the time per iteration of each runtime versus the total time spent benchmarking. And what's nice about this is you can visualize how long it takes for each implementation to outperform the CRuby interpreter. Importantly, you can see that Widget outperforms the CRuby interpreter almost instantly. The other runtimes take a bit longer, with Truffle Ruby taking somewhere around 2 minutes, which again, in a production context, can be problematic because it can translate into drop requests, etc. One of the comments we have from the reviewers is that on benchmarks, we have speedups of sometime around 30% and 50% end-to-end speedups in production, and that this is maybe not that impressive when you compare it to some of the JIT compiler work that's been done for JavaScript VMs, for example. So some acknowledgments. So Widget is a relatively simple JIT built by a small team. It's also a retrofit into an existing VM with a 28-year-old C code base. So that comes with its own set of trade-offs, and there's a lot of room for improvement. But at the same time, I think Ruby and JavaScript are not exactly the same game. JavaScript is a much simpler and smaller language. I know because I implemented a JavaScript JIT during my PhD. The semantics of Ruby are more dynamic and more complex, more difficult to optimize. But there's also a difference where JavaScript is browser-based code, whereas we focus on what runs in the server backend. And so some of our benchmarks do database requests, for example, which we can't optimize. But we don't shim our benchmarks. Like in our benchmarks, that we really do make those database requests. So that's time that we can't shave off. But out of curiosity, I was curious, like, what do people use these days to benchmark JavaScript? I found a website where they talk about like the Jetstream suite of benchmarks. And as part of this, there's benchmarks like this, which is like a poker game benchmark. And this benchmark is 100% monomorphic. It's easily inlineable. It does a lot of bitwise arithmetic, which is not something that typical web applications will do. and it uses almost no external data. So conceivably, you could port this benchmark to run on an Atari 2600 with 128 bytes of RAM. So of course, you're going to get a 20x speed up on this benchmark. Also, my colleague Takashi Kokubun has been working on profiling how much time we spend in a JIT versus the rest of the code. And what we can see is that on Rails Bench, one of our biggest benchmarks, the time spent in JIT compiled code is only 12.7% of the total execution. So we've succeeded at making a JIT that generates code that is like several times faster than a CRB interpreter. But the problem is now that time is being dwarfed by time spent in external C calls and external libraries. So we're getting to a point where it's going to be an advantage to rewrite codes, rewrite code in Ruby if you want to get better performance. So now into our production deployments. Shopify Storefront Render is the infrastructure that renders all the Shopify stores. It's mostly written in Ruby. It runs over 4.5 million e-commerce sites. I can't publicly state how many servers that is, but it is able to serve over 1.27 million requests per second. So one of the challenges that we had in benchmarking SFR is that traffic varies based on time of day, region of the world, and world events. So people in different countries will shop at different stores, and also the traffic varies based on promotions that people do on social media. So you can't, like something that people do sometimes when they benchmark production deployments is they'll benchmark their servers before and then they turn on YJIT and they look at the time after. But that's not a fair comparison. To do a fair comparison, you really have to run both at the same time. So in every cluster across the world, we have machines that run YJIT, and we also have a control that runs the CRB interpreter, and we also have stats machine that gather statistics without disrupting the total execution time. This is the performance on SFR in terms of response time versus the CRB interpreter. We have like about a 15% speed up on average, but also very importantly, even on the slow SP99 requests, YJIT performs better, which really shows that we've done a lot to make it so that YJIT can compile fast. This is a graph of the speed up over time during the 48-hour window that we examined. And again, we're never slower than the CRB interpreter, even on a P99 slowest request. We've also measured the amount of memory overhead that YJIT takes, and interestingly, you can see the metadata actually takes up more space than machine code. I guess I should note we've also made some steps to reduce the memory overhead of the metadata since this paper was published. And also, nowadays we're actually up to something like 25% speed up on our deployment. So some key takeaways: YJIT is fully compatible with existing Ruby code. In terms of peak performance, it's also very competitive with JRuby. YJIT has the fastest, most predictable warm-up. YJIT has the least memory overhead, and sometimes by a really long shot. This is crucial for our production deployments, and it's something that if Truffle and Graal cannot solve the problem of memory overhead, they can't compete, even though they have the fastest peak performance. And also, YJIT has gotten even better since this paper has been accepted, so we have higher peak performance, less memory usage, and faster compilation times. Thank you for listening.
Okay, we have a couple of moments, one or two questions.
Hey, as somebody who's also worked on JavaScript and Ruby compilation, congrats. Those are great results. Your reviewer is comparing apples and oranges, so good job on rebutting that. I guess the one question I have is, with a lot of Ruby's core being written in C, do you see that changing over time as YJIT gets stronger? Like, is it going to be something that you're going to have to do a lot more, writing Ruby itself in Ruby?
We hope so. Something that we want to look at as Ruby 3.4 is like giving people more tools to be able to do things like byte manipulation so that they might be able to write some of the things that they wrote in C extensions in pure Ruby code.
Okay, cool.
Cool. Okay, let's thank Maxine for a great talk.
Thank you.
It did work before. Oh, okay. I just unplugged it to. Okay.
It says no signal. Do you need to? You don't need to.
Well, now we don't have internet.
That looks like something.
I mean, that's my background. And now Google Slides has decided to be like, I don't care. All right, well, this is why I downloaded backup slides.
We promised that we did actually test this beforehand.
They did, I watched them.
Sorry, I can't see.
Is it?
It's okay, it's just put the presentation there and it's fine.
No, like it wouldn't load the actual presentation anymore because I don't have Wi-Fi anymore. So 1 second. It's gonna look funky, but it'll work. There. You see that?
Yes.
Okay, cool. All right, sorry.
Okay, so our next talk's on Cache IR, and we have 2 speakers. So Matthew and Ian are going to give a talk.
Yeah. All right, I promise I'll go fast. So, this talk we're going to talk a little bit about inline caching in a JavaScript engine, a little bit about how it tends to be presented, how it actually sort of works in one specific engine, and why we built an intermediate representation for our inline caches, and then some cool advantages that that brings. So, inline caches tend to be talked about pretty simply. So there's a model that, you know, when you are teaching an undergrad course or something that you're going to talk about where it's like, well, in the code itself, you'll put, you know, often it's taught in the context of small talk. So for example, you'll have a method send, and you'll say, I have a receiver, and if I see an object with the same receiver type, again, I can go and I will use that, the discovered target method, and we'll save that right there, and we'll use it over and over again. And then there's the follow-on work, which is, hey, some things are polymorphic, so why don't we store multiple in there? The problem with this presentation is that it tends to limit people's view on like what actually you can use inline caching for and how powerful of a technique it can be. And so one of the reasons I wanted us to write this paper was to just try to actually make that clear, that inline caching is a super powerful technique and that we can do a lot more with it than maybe is being taught. So, inline caches aren't really just caches. And even if you go back to the paper that introduced this from Deutsch and Schiffman, they kind of allude to it, but it's not being made very clear. So we adopt the approach inside of SpiderMonkey that essentially any behavior that can be specialized based on something about the input types can get an inline cache. And so this includes things like property access. This includes things like calls. This includes things like arithmetic operations. And in calls, we can even do things like a simple form of inlining. Now, we're going to talk a little bit about the inline cache architecture inside of SpiderMonkey. So SpiderMonkey, like a lot of language VMs, compiles source text into bytecode. Our bytecode any bytecode that is eligible for an inline cache will start in this unlinked state where you have a pointer to a fallback stub. So the fallback stub is written in C++, and its job is to always be able to provide an answer. It's always able to resolve the input. When you do that, though, we can attach a stub. So you've seen, for example, the addition of an integer to an integer. Well, this is a point at which you would say, let's add a stub. So the stubs form a linked list, and so we'll have stub 1, stub 2, stub 3, stub 4, and each of these will point to native code that actually implements the operation. And the chain will always end in the fallback stub, so you can always handle every single case. In SpiderMonkey, we create stubs using cache.ir. So cache.ir is a simple typed bytecode specialized for the case of inline caches. It's linear. We only have two control flow operations. We have guards, where we're asserting some property is true, and if it's not true, we just give up and jump to the next stub. And we have return. So you have succeeded in running this inline cache. Let's return the value and get out. Immediates are stored inside of stub fields, which you can sort of think of as constant pools if you've used a language with constant pools. And so in this example, we have guard to object, which you can't see my cursor. So you have guard to object. This is converting an input, which could be any type, and saying, if it is an object, then return a new operand ID of type object. It's guard type shape, so make sure that that object has a specified known shape. If it does, then we're going to load a fixed slot result, and we're going to say, get the result out of a particular slot in the object and put it into the result register. And now, once that happens, we're done. So we return. One of the things to note here is that all of the dynamic information is stored separately because we want to be able to actually recycle these stubs. There's lots and lots of them in an actual production compiler, so we don't want to be compiling a new one for every instance. So we generate these stubs in the fallback cache path, and the model kind of looks like this. So we generate cache.ir, and we hand it off and say, for the baseline compiler, we'll go and we'll check a pre-existing cache. The nice thing about cache.ir is that it acts as a perfect cache key to say whether or not we can recycle the native code. Because we load everything out of the stub fields or the constant pool, the native code will work for multiple stubs with different shapes. Our Ion cache.ir compiler works a little bit differently because it interacts with our register allocator. So currently we don't do any sharing for Ion cache ICs, but we're talking about it. So why add an intermediate representation? Well, we're compiler people, and intermediate representations are neat. They're lots of fun. Why wouldn't we? Really, though, I mean, it's a lot of the traditional reasons why you actually add an intermediate representation. So it's separation of concerns, separating the ability to reason about your inline caches from how they're actually implemented and executed. The other advantage here is that it provides a shared representation throughout the engine. This deduplicates effort. It replaces a system where we could get into situations where we would have inline caches that worked only for our baseline compiler and not for our top-tier compiler. And yeah, I already mentioned the baseline code sharing made robust using the inline cache representation as the key. At this point, I will hand it off to Ian.
Hi, so I'm going to talk a little bit about Warp Builder, which is the JIT that we built on top of cache.ir. So after we'd used cache.ir to unify how we implement baseline ICs and Ion ICs, we turned our attention to our optimizing JIT, and the result was Warp Builder. It is the new-ish front end. We actually shipped it a few years ago, but we're just talking about this now, for Ion, which is our highest tier. And while querying inline caches to get information for your optimizing compiler is nothing new, in this case, we really leaned into it. And so cache.ir allows us to treat the process of looking at what our ICs have done as a lowering step rather than as a querying step. So as an example of how this works in practice, if we have some very simple source code that's just a function that's adding two numbers together, This will have some bytecode. It gets the arguments, it adds them, it returns them. This is a stack-based machine. And then we have cache IR for this that will guard each of these values, add them together, and then return the result. And now what Warp Builder will see is it will start walking through the bytecode. It will see we get an argument, we get another argument, and then when it gets to the add, the important thing to realize is that Warp Builder actually knows absolutely nothing about addition. Instead, all it knows is, well, there's an IC for this. Let me go check the ICs. And it will see, I have a monomorphic case where we have done a guard to an int and another guard to an int and then added them together. And so it will take those guards and it will lower those to a fallible unbox where in the generated top-tier code, we will say, we expect this to be a 32-bit integer. We will unbox it. If it isn't, then we will bail out and learn more and then recompile again later potentially. And then we return back to the bytecode, we continue generating it. If the IC chain is polymorphic, then we just create an IC and ion, and we get all the benefits of ICs there. And if the IC chain is empty, then we can just create an unconditional bailout, which allows us to do branch pruning of purportedly dead code that has never been reached before. So briefly comparing this to what it was replacing, we used to have Ion Builder, which you can see on Matt's shirt, and because this was back when we made posters for our projects. It was a dynamic type inference. It did a whole program analysis where we partitioned objects into groups and tracked properties per object. And it was all very, very clever, and you can go read the paper about it. But fundamentally, it was very big and complicated and brittle. And so the advantages of Warp Builder are, first of all, that it is a single source of truth. That it is a single place where every speculative optimization that we do is implemented in one place where we say, if I have seen two integers, I know what to do. If I have seen a call to this particular built-in, I know what sort of code to generate there. And it exists in exactly one place rather than needing to look at your inline caches and then figure out what to do again based on that. This is good for correctness, it is good for simplicity, it is good for avoiding missed optimizations that are only performed in one tier. Compared to what came before, it involves much more local reasoning because all of the guard conditions are very local to what you're looking at rather than depending on state being maintained in the metadata across the engine. And it's much lower global overhead. We effectively get type specialization for free because we already want to have inline caches tracking this so that we can have the benefits of performance in baseline, and then when it comes time to have an optimizing compilation, the metadata that we're tracking is precisely the metadata that we already needed, and so we're not paying extra for that, where Ion Builder was. Lower tiers don't end up having to pay for collect data they don't use. That's great. One disadvantage is that this does end up with more guards and hot code. So this is very similar to what Maxime said. There are cases where you are trading off peak performance for warm-up, and what we found is that in practice, on the real web, trading a little bit of peak performance for a lot of warm-up advantages and stability and reduced memory consumption is a great trade-off, and we are very happy that we made it. So a few other cool things that we've done. Once you have cache IR, we do this thing called trial inlining. So as I mentioned, we only actually lower things if the IC is monomorphic, and we want to have as many monomorphic ICs as possible. So you can have a case where you have a function that is being called in multiple places with different types. And if you just do if you just run this, then inside this function, we will have one IC chain that has two different ICs in it. And so if we didn't do any inlining, this would be polymorphic. To make it work, what we do is we start by having this version where we're doing two separate calls. And then partway through execution, we start doing our inlining. We make our tentative inlining decisions. And so we say, okay, in this case, I see that I have an IC with a single target, and I see that that target contains polymorphic ICs. We then create a separate private batch of ICs specific to that call site and rewrite the IR stub that was doing the call scripted to a call inlined. And because this is an IR, we just have to find places where we have a guard-specific function operation and a call scripted function operation, and then we can just clone the entire thing and replace the last instruction from call scripted to call inlined, and everything else works. So there may be different guards that we need depending on case, but that all gets optimized away and is orthogonal because we have a separate IR for this. And then when we execute this, this call site will only see a 32-bit integer addition, and this one will only see a string concatenation, and therefore we end up getting monomorphic ICs, which is pretty cool. So after we do trial inlining, we have private per call site ICs, and they're monomorphic. A couple of other fun tricks that I'll run through quickly. Again, because this is an IR, we can do a thing called stub folding, where if you have a bunch of stubs that have exactly the same IR, except they're guarding on a slightly different shape, then we can take that, recognize that mechanically, and smush it all down by just taking that code, replacing the guard shape operation with a guard multiple shapes operation, and changing nothing else. And so we only need to implement this small change, and we get this for anything that might be using shapes. Because it's an IR, it's very easy to hash it, and so we can do a bailout loop detection where we notice, where we can guarantee that we are never recompiling without having learned something new about this and monomorphically move towards a steady state modulo GC pressure. We think that the ideas that we're presenting in this paper are more interesting than the empirical results, but the empirical results are actually also pretty good. So again, calling back a little bit to the previous presentation, there are a couple of benchmarks that are really popular in JavaScript land, and one of them is speedometer, and it's the good one. And so you can see that when we moved from Ion Builder to Warp Builder, we got an improvement on speedometer. And the other is Jetstream, and it's the bad one. And so when we moved there, we took a known hit because we didn't care. And since then, we have put some work in that has actually moved our score up. But the really interesting thing was that just moving from the let's get maximum performance at all, maximum top-tier performance at the cost of everybody else design of Ion Builder to Warp Builder almost instantly gave us better performance on the benchmarks that we actually care about before we had even really put any optimization effort in. You know, this is SpiderMonkey poking its head out of the industry hole for, I guess, last time we did this was 2012. We're always happy to collaborate with people. We're hoping to do some more research opportunities, so we're working with some people at the University of Alberta on this paper. We have been collaborating with some people at Fastly on precompiling, or on doing this in a JIT-free environment using interpreted cache IR. If you have any ideas, please come talk to us, and we're open for questions.
Okay, we have plenty of time for questions. You come up to the microphone.
I wanted to ask the reasoning for the empirical results. So, like, does the subfolding or something specific to the Warp Builder like contributing to the improvement? Like, is it possible to implement the same technique in Ion Builder, or is that just easier in Warp Builder? So I'm kind of curious why this.
Right. So a lot of the improvement was because Ion Builder had originally been designed to optimize Octane, which was like the precursor to Jetstream and even worse. And so it was a lot of very small code base, you know, here's a very, very small hot loop. Can you make this as fast as possible? Whereas Speedometer is taking a bunch of actual real-world JavaScript frameworks and then doing sort of like, here's a basic app. And so because Ion Builder had a lot of, imposed a lot of overhead on colder code, as soon as you moved from something with a very hot profile to something with a flatter profile, those costs were no longer being hidden in code that never ran, and therefore the benefits of having good performance on everything rather than great performance on hot code and less good performance on colder code, that trade-off started to pay off in the direction of Warp Builder. It let us reduce memory consumption a lot because we had been tracking these big graphs of what every object could be pointing to and so on. And it let us get rid of a bunch of places where we had all of the baseline code needed to be tracking what types am I storing into objects to maintain that.
The hot and cold thing was like the layout problem. Like, do you place like hot code together, or is that just you mainly optimize the like hot paths by introducing a new type of the inline cache. So
So warp, like, we're a standard tiering JIT where the, you know, we only, once code has gotten hot enough, then we will tier up to the top level.
right.
So Warp Builder itself isn't necessarily going to improve cold code, but the fact that we're using Warp Builder rather than Ion Builder means that the colder code does not pay costs for Warp Builder, and therefore it ends up being faster, not because Warp Builder is doing anything, but because Warp Builder isn't requiring the cold code to track things. Does that answer your question? Sorry, I wasn't.
Yeah, it does. Thank you.
Just one more.
So I'm curious about what you said about reducing the warm-up start. So can you actually move it to an extreme and actually compile code ahead of time, or share code across other engines that are running simultaneously? And what's the impact on performance?
So we're currently we currently share our baseline ICs that have the same cache IR sequence across an entire runtime. So basically, a tab, there will just sort of be one, like a huge fraction of all IC stubs are a basic get prop that says, check that this is an object, check the shape, and then load the value from a particular slot. And so we only actually have one copy of that code, or maybe a couple for technical reasons, that get shared across an entire tab. We are looking at also collecting the list of those things and pre-compiling those and baking them into the binary, which would be a small improvement. We're not sure exactly what the scope of it is, because these are fairly fast to compile, but it does pay off. And yeah, we're working on moving more compilation earlier. This is a helpful way to have organized things to do that.
Okay, yeah. I was curious about the performance impact, but we'll talk it offline.
Okay. Sure, yeah, maybe ask me afterwards and I'll have a better answer.
Okay, thank you very much for a great talk, Matthew and Ian. Cool, that worked quick. Okay, our next talk is on diagnosing compiler performance issues. Take it away.
Hi, my name is Andrej Pečimut, and I also work with David Leopoldseter and Peter Tuma. This talk is about diagnosing performance issues in production JIT compilers. We implemented this approach for the GraalVM compiler, but it should be transferable to many other similar systems. First, consider the performance characteristics of an application running on the JVM. It's rather complicated, and this is due to several factors. First, we usually start executing a method in the interpreter. The interpreter collects profiles. When the method is invoked many times, it gets compiled by a tier 1 compiler that also produces instrumented code that collects profiles. And when the method is invoked even more times, it gets compiled by the tier 2 compiler that uses the profiles to do optimization decisions, and it should lead to basically the profiles allow the compiler to make better decisions, which leads to faster code usually. The tier 2 compiler is also allowed to do speculative optimizations, like it can speculate that an operation doesn't throw an exception, and when this speculation is violated, the code is discarded, we continue in the interpreter, then we collect more profiles, and maybe later the method gets recompiled with different profiles and different optimization decisions, and we get different performance. All right, so I tried to convince you that the system is rather complex, and a production dynamic compiler has several commits merged every day, and this combination leads to performance regressions. To avoid these regressions, we periodically measure a set of representative workloads. We have an example of such measurements on the slide. The x-axis is a revision of the compiler, and the y-axis are the results of the measurements, basically the time it takes to finish a repetition of the workload. We can clearly see in this case that there was a performance regression, and this is what the talk is about. We have some version of the compiler before and after the regression, and we want to answer what is the cause of the regression. The cause is often linked to an optimization decision, which means, for example, the compiler used to inline a particular method in some workload before the regression, and after that regression, it stopped inlining that particular method in a workload. So this is the kind of answer that compiler engineers expect to make the heuristics in the compiler more robust to these changes, for example, in the profiles. And it's not just about inlining. There are tens of different optimization passes in the compiler that perform optimization decisions. So how could we diagnose such a problem? The first idea that you might have is to look at the change code, look at the code level changes. However, we found that the committed code is often clearly unrelated to the true cause. This is due to the complexity of the system. Another option is we can look at the IR. We have an example of the IR on the slide. However, it usually contains thousands of IR nodes per compilation unit. So just by looking at the graphs and diffing the graphs, we cannot find the issue. Therefore, our approach is the following. The idea is simple. We capture and compare the compiler's behavior. So starting from the left, we have some workload on which we regressed, and we have a revision before and after the regression. What we do is we run the affected workload on both these revisions of the compiler. We attach a profiler to the VM, which will tell us what are the most frequently executed compilation units. Basically, what machine code the VM is executing most of the time. And we also ask the compiler to produce optimization logs, which is something that we crafted specially for this purpose. The optimization logs contain a tree for each compilation unit, and the tree describes the compiler's behavior, the optimization decisions in that compilation unit as a tree. Then we made a tool called profdiff that loads these logs and profiles, and for the frequently executed compilation units, it compares the trees semantically. The result is some textual report that shows the differences between the trees, and a compiler engineer can read these reports, and they should be able to figure out what is the issue. All right, so to illustrate how this works, how we collect the trees, how we compare them, I'll show an example workload that we'll try to optimize. And I'll show how we record the trees. So this is a very simple workload that takes, it's a method called for each neighbor that takes a 2D grid as an argument, a starting position in the grid, and some callback. And basically, it invokes the callback for each neighbor of the starting position. All right, so this is just the workload that we're trying to optimize, and I'll show how we record the trees for the optimization. Basically, this workload should be pretty much equivalent to the code that you can see on the right. The code on the left uses some, it allocates some objects, there's a for loop, and there are some method calls. The code on the right doesn't use this. So the compiler should be able to optimize these allocations, method calls, and the for loop away. And this is how we start, this is how we record the optimizations. At the beginning of the compilation, we build this tree that basically reflects the compilation unit that we're compiling and all the calls that are in the method. So we have root, which is the root of the compilation unit, and we have the calls to methods add, x, and y, and it says direct in front of them, because these are simple direct invocations, and we have a call to method accept, and it says indirect because there's dynamic dispatch. And I'll show 3 optimization passes: inlining, escape analysis, loop unrolling, and I'll show how we record all these optimizations, and I'll also show the intermediate code that represents what the compiler is doing in the middle. So first we simply inline the calls to these methods that are easily inlineable, like the call to the add method x and y and method add. We simply replace the calls with the body of the target methods, and in the tree on the right we record these optimizations, and you can see that for these 3 calls it says inlined because we inline these calls. Then comes escape analysis, and escape analysis is pretty much trying to put as much allocations on the stack instead of the heap, because this is more efficient. Escape analysis determines all the allocations that do not escape the inline scope. So an allocation could escape by saving and storing an object to a static field or passing an object to a method that was not inlined. In this case, escape analysis determines that all of these allocations that are highlighted on the left, they do not escape. We can place them on the stack, so we recorded that in the tree on the right. So we recorded the fact that we can place these allocations on the stack. Each of these has an individual node in the tree on the right. The middle shows that there's basically no way to force stack allocation in Java yet, so I borrowed a bit of C++ syntax here. And you can also see that the tree on the right, it reflects the optimizations that the compiler performed, the optimization decisions like stack allocation, and it also reflects the inlining decisions, and this all follows the structure of the inlined code. Then last optimization we want to do and record that in the tree is the for loop. The for loop does always only 4 iterations, so we can get rid of the loop by replacing it with 4 copies of its own body. We do that in the middle, and we record that fact that we did loop unrolling in the tree on the right, so it says loop unrolling line 11. As a side effect of the unrolling, we made 4 copies of the call to the accept method, so we have 4 nodes on the right side. All right, so this is the end of the baseline compilation. I promised that we could get rid of all these allocations and all the unnecessary method calls and the for loop, so we just did that, and we recorded that as the tree on the right. This tree on the right will be part of our optimization logs, then we can later diff with other logs. Now, let's consider some regression scenario. Suppose that there is a bug in the inliner, and we'll basically that will lead to a different compilation outcome. We will fail to optimize all this code, and we'll record it as a different tree, which we can later compare with the baseline compilation. So again, we'll go through 3 phases: inlining, escape analysis, and loop unrolling. So first, we inline the calls to methods x and y. We record it in the tree on the right. We do not inline the add method and suppose that this is the bug, that there's some bug in the compiler's heuristics, and it leads to the fact that we do not inline the method add. Then comes escape analysis. We can still place the allocation of the array on the stack, but we fail to get rid of the indexes, because these objects escape as arguments to the method add, which was now not inline. So we do not record anything in the tree. And also the add method would now be compiled separately as a separate compilation unit, but we can also see that the allocation escapes from that method as a return value. Therefore, we also have to place the allocation on the stack, on the heap. Finally, loop unrolling, we can still get rid of the for loop by replacing it with 4 copies of its own body. we record the fact in the tree on the right that we did the loop unrolling. Now as a side effect, we now have 4 copies of the call to the add method, and also 4 copies of the call to the xset method, so the tree on the right reflects that. All right, so this is the end of the regressed compilation where we had a bug in the inliner that led to a different compilation outcome. We could not place all the allocations on the stack, and we recorded that as a tree on the right. So let's put these trees side by side, from the baseline compilation where we could optimize everything as we wanted, and the tree from the regress compilation. Remember that these trees are part of the optimization logs, and if these compilation units are frequently executed according to our profiles, our tool will give us the differences. So this is the tool's output, and it clearly shows the differences between these 2 compilations. It says that there was a different inlining decision for the add method. It was inlined in the baseline compilation, but we failed to inline the method in the regress compilation. There were all these allocations that we could place on the stack in the baseline compilation, but we failed to do so in the regress compilation. And we also have these calls that were duplicated in the regress compilation as part of due to the loop unrolling. All right, so this is the tree that is the output of the tool, and it clearly shows the differences and also the parts of the compilation that were unchanged. There's one more thing. Consider the method add. Method add was inlined in the method for each neighbor, so it was compiled as part of the big compilation unit before the regression, but after the regression, we compiled method add separately as a dedicated compilation unit. So the compiler could have optimized this big compilation unit and this dedicated compilation unit differently in the 2 runs, so we would like to see the differences in optimization. Therefore, we have from the baseline compilation, we have this tree that describes all the optimizations in the big compilation unit, and from the regressed compilation, we have just this small tree that is just a single node that describes all the optimizations in the dedicated compilation unit. The tree is just a single node because in this case, there were no optimization decisions. To compare these, we simply create a subtree. We call that a compilation fragment, and we can compare these directly. And the result is the following. Basically, it says that before the regression, we could, in the inline method, we could place the allocation on the stack, but we failed to do this in the regress compilation where we had a dedicated compilation unit for the method. All right, so this is the end of the examples. The examples are rather simple, so you may wonder what the trees look like in practice. This is a tree that describes optimizations from some random benchmark that we use to track the performance of GraalVM. This describes all the optimizations and all the inlining decisions in a single compilation unit. We usually have something like 5 to 10 hot compilation units that we really care about in a run of the VM. So we also put the tool to a test with some real data. The Renaissance benchmark suite used to track the performance of the GraalVM compiler. And in this suite, there were 6 unstable workloads. So that means there were 6 benchmarks that were randomly faster or slower on each VM invocation. So whenever we invoke the VM, the workload would end up being randomly faster or slower. Therefore, we used our tool to diagnose these issues. We found the actual concrete optimization decisions that were responsible for the slowdowns in these workloads. And we could also confirm that the optimization decisions that we identified were really responsible for the slowdowns, and we could easily confirm that by running the VM with a VM option to override the optimization decisions. All of the optimization decisions that we found, all of the issues were related to inlining, So we had to just force the VM to inline or not inline a particular method in a workload. And we got speedups from 8 to 30% on each of these workloads. And one of these issues that we identified is already fixed in production. All of the tooling, all of the modifications to the Graal VM compiler are merged to the upstream repository. And thank you. This is the end of the presentation.
You got time for one question?
Sure. So there's a kind of maybe well-known technique where if you have, if you look at all the transformations that are done over the course of an optimization in order, then you can do a binary search on those and say, if I only do the first half of them and don't do the second half, then do I still see the regression or the bug or whatever, and narrow in on those. So there is an argument in some cases for, instead of having a tree-based approach, having a chronological list of all the things. Do you have a sense of to what extent representing this as a tree and doing a tree diff gained you an advantage versus just having a in-order list of what choices you had made?
Yes, thank you for the question. The first implementation that we had, it was also a tree, but it follows the structure of the compiler, and it was some kind of a chronological order. Basically, the tree just described the optimization phases that the compiler runs and all of the optimizations, but we found that pretty hard to read. So basically, the problem, as you saw, is inlining. So we really care about the structure of the inline code, because each time you invoke the VM, you might get different inlining decisions, and that will lead to different optimizations. So therefore, we often want to compare a sub-part of a compilation unit, which we call a compilation fragment, with a dedicated compilation unit in another run. So the trees make that really easy because the optimization decisions and basically follow the structure of the inline code in the tree. So to compare a part of the compilation unit with another compilation unit, we just have to take a subtree from our tree that we built.
Okay. Cool, thanks.
I think we've got time for one more question.
Did you have to modify the compiler to collect the information, or was it already done using some debugs and you just collected it?
Yes, basically I went through all the optimization phases in the compiler, and whenever the compiler performed some optimization, some transformation, I added some call to my method to log the optimization.
Okay, thank you.
Do you think you could use this on other compilers? So this seems like a completely general technique to sort of finding problems.
Yes, I mean, we could build something on top of this that would semi-automatically try what optimization differences could be responsible for the performance differences, like some tool to automatically run the workload and override some optimizations. The problem is that there's really no technique to do that in the compiler to generally override any optimization decision. And yeah, there are some other technical difficulties.
Cool. Okay, let's thank the speaker. Okay, so now the last talk in the session, which is going to be by Duncan, and it's going to be on Python VM using Cherry.
All right, thank you. Yes, and this work I did also with my colleague Dejis, who's in the crowd here, and Jeremy, who can't be here at the moment. So first, what is MicroPython? You all know what Python is. MicroPython is a bare bones interpreter. It's designed for embedded situations, so it's optimized for code size, but it has full syntax of Python 3.4. It doesn't have all the libraries built in, but all of the syntax is there. And it is, of course, written in C, like so many interpreters and VMs. The more interesting question is, what is Morello? What is Cherry? So Morello is the Cherry prototype architecture developed by ARM. It's an extension to the Neoverse processor implementing ARM v2 8.2a. So 64-bit ARM stuff. Cherry itself stands for Capability Hardware Enhanced RISC Instructions. This is a set of instruction set extensions that allow certain spatial memory safety guarantees. So I'll talk a bit more about that, but basically converting pointers into a more sort of type-safe, memory-safe thing. You can use two roughly different APIs with it. So the hybrid API allows you to use mostly capability oblivious code, but run it within the environment that understands these capabilities. It uses some implicit privileges in a global register. You can also use the PureCap API, where your code is compiled fully aware of capabilities, and every pointer winds up being a capability, and it uses the full protection features. Morello capabilities, implementation of Cherry capabilities, they're 129-bit fat pointers. So you've got your address, which is basically your standard pointer, but then you also have metadata. So you have bounds and, over which the capability is valid. Any memory access has to be authorized by a capability, and a capability can only authorize access over its bounds. So you can no longer have buffer overflow attacks, for instance, provided that you make sure your capability bounds are set properly, which is something your compiler can often do for stack allocations. You also have permissions, so you can mark a certain capability as read-only, for instance. You've got an object type field that allows you to sort of seal capabilities to prevent them from being directly used, but then unseal them later if you have adequate privileges. You've also got a provenance tag, and this might be the most important bit. This is 1 bit stored out of band, so you can't access it directly in memory. And it tracks whether a particular memory region contains an actual valid capability or just a sequence of bytes. There's a guarantee of monotonicity. So anytime you want to create a capability, you have to derive it from an existing capability by narrowing the bounds or permissions. If you try to increase the bounds or permissions or otherwise do something that violates the rules of deriving capabilities, it will clear the tag, and a capability with a cleared tag cannot be used for anything. It just winds up effectively being an integer. As I mentioned before, the object type allows you to seal capabilities. The most interesting case of this is the sentries, where you can take a function pointer and seal it so that the you can give access to this sentry, and it will allow you to call that function, but only at the particular entry point. It won't allow you to jump to an arbitrary point in the function, and it won't allow you to read any of the function's actual code. So this has obvious protection implications, improved defense against return-oriented programming and things like that. It's important to note we have single source provenance, so each capability has to be derived from exactly one other capability. If you have, so you can't combine two capabilities together and be like, well, they're adjacent in bounds, so I want one big capability that covers them both. Each capability can only be derived from one other. Some implications. Our pointers are now larger than our, integer word types, which is something that a lot of C programmers would, not expect in most cases. You also can't just cast through a pointer through a long. If you do, it will result in provenance loss. So the capability tag and metadata will be discarded. And when you try to dereference your pointer after casting it back, you'll wind up with a tag violation because you've lost that provenance. the specific type uint pointer t and int pointer t say it stores an integer, but as a capability, it actually preserves provenance. So you can use that particular integer type, but any other integer type is going to lose provenance. One implication of the fact that uint pointer t and int pointer t is a capability type is that you can't just tell the compiler necessarily to add two of the values together, because it doesn't know which provenance and metadata it should keep. So the compiler can't know whether you mean to add the sort of value of this capability to the whole first capability, or whether you want to keep the whole value of the second capability, and the whole provenance of the second capability, and just add the value of the first. We also don't have the same representable range that one would expect from the size of the uint pointer. So the uint pointer t only has the same representable range of integers as a long, despite being twice as wide in memory. But on the plus side, there are a lot of behaviors in C that are undefined and can lead to either memory corruption or, if you're lucky, a seg fault. Most of these wind up becoming replaced with a very predictable cherry protection fault that is guaranteed to be thrown whenever you use an out-of-bounds access or an access without valid permissions or with a cleared tag. So some changes that were required to build MicroPython with the under this pure cap system. We had to change assembly somewhat. So where inline assembly was used to implement non-local returns, we had to change the registers so that the full capability registers were stored rather than just the integer registers to make sure that the stack was properly restored. We had to remove areas where uint pointer t was used where there weren't actually pointers being stored. Because, like I said before, if you just try and add them together, the compiler will complain about provenance. Ultimately, you want to use traditional integers in as many places as possible, and only use the uint pointer t where you actually might store a pointer. So there were a couple of places where we had to keep uint pointer t, but for the most part, we swapped to explicit integer types, int 64t, whatever. But another interesting thing we had to change was there was a function that is involved in converting floating points to integers. MicroPython represents integers less than, I think, 2 to the 31 with a certain unboxed representation and with a low bit tag to make sure that it's seen as different from a pointer. And so the function to say whether or not it can be stored as a small integer relied on the size of a pointer to determine how many bits it had available, which is, of course, incorrect, because you can only use 64 of the bits to store the actual integer value. The rest is metadata. So we had to change that. We also had to create a new built-in Python type to hold the capability. There are places where you can pass a pointer from Python code through the libraries into your Python code, manipulate it, and then send it back to, into a native area. And we need to change that to a capability. We need to be able to wrap a capability, or else, again, we have provenance loss. In order to realize the advantages, the compiler can automatically set bounds on stack allocations in a nice way, but we need to tell our heap allocator to set explicit bounds on its the pointers that it allocates, because otherwise heap pointers grant access to the entire heap area, and that's not desirable. So we also need to rederive the wider bounds when within our free or realloc in order to manipulate the stack data. So we have to be careful with the way we implement the free and realloc. We can't just assume, because we've now narrowed the bounds when we allocated, that we can't just assume that we can use that pointer to access other data. And in particular, when you in place reallocate some memory, you need to return a pointer with wider bounds, which means you sort of need to rederive it from the existing heap pointer. This also means that even in places where we have guaranteed in-place reallocation, so the code is used in argument to tell the allocator to fail if it can't reallocate in place, if it would have to move. Often there, it will just check the return value for null and then discard it, or just success or failure. But because, again, the capability bounds are so important, we need to actually save those bounds back in, so that there are places where code needs to be modified. Some advantages of all this, we exposed a few dodgy buffer accesses in the actual original code and upstreamed fixes to the non-Cherry, the main repository for MicroPython. Some of these had to do with the failure to account for the padding in a structure when allocating memory. So one was a classic read beyond end bug in a string. And another was an incorrect rounding for buffer length. So, if you're trying to take 3/4 of something, but you do the integer division before the multiplication, you're going to wind up with truncation issues. This formula there can wind up as much as 2 bytes too short. And so, fixing the order of that. It's little things that are very easy to go unnoticed when you're allowed to access 1 or 2 bytes beyond the end in the vast majority of situations, and nothing bad will happen, but there's still the potential that bad things could happen. So it's better to tighten this all up with this Cherry paradigm. Here's an example of a mitigated vulnerability. So on the left, you can see, and this is the original unprotected hybrid code. If we allocate 2 byte arrays on the stack, and then we can use UC types to take the address of one of them and create a new byte array at that address and tell it it's 2 to the 14 bytes long. But the original byte array was only 1 byte. So this is clearly unsafe, the fact that we can then access arbitrary offset, and in fact we can, as you see there, corrupt the value of the other byte array just by writing to the correct offset. This is clearly undesirable, but it can't really be fixed in the native paradigm without adding some sense of bounds to the pointers. It just gets complicated. But because in Cherry we have the metadata built into the pointers, if we try to do the same thing, although it will let you create the byte array and tell it that it's much longer than it actually is, when you actually try to access the illegitimate offset, you'll wind up with a capability bounds violation because you never extended the capability bounds. You can't. It's the monotonicity. And so that will always be a violation, and you can't bleed from one heap object into the other. As for tests, we managed to get the vast majority of tests working just as they did on non-Cherry systems. You might notice one test was failed in our PureCat build that wasn't in other builds. That has to do with a particular library dependency for the actual MicroPython interpreter that doesn't fully support all features in its Cherry port yet. But I think actually, as of now, we've gotten a fix, and that should be a nice 0 at this point. Performance is a valid question. A lot of times, that's the issue people potentially see with Cherry. It's great to have more security, but what's the cost? So after a few rudimentary optimizations, we managed to get the following performance. You'll notice our total time is between 1.5 and 2 times that of the hybrid version, the non-capability aware version. And that might seem high, but there are a couple places that likely comes from. First off, the Morello architecture's capability instructions are, it's a prototype architecture. So the hardware could well improve. In particular, there's a known issue with the branch predictor in PureCap code on Morello. and that's expected to come down quite a bit. We've also got some other optimizations that we can probably do in our code. For instance, the elide certain software bounds checks now that we have these hardware bounds in place. But ultimately, if you want to hear more about the performance stuff, you can come to my talk at VMIL tomorrow morning, first thing, where I go into a bit more detail about the performance of all this. So as far as future work goes, one of the big sort of holy grails of Cherry is compartmentalization. So we're currently doing work underway to create a compartmentalization scheme for the MicroPython interpreter that will prevent extension modules that are written in C from interfering with VM internals, and prevent native libraries loaded through the foreign function interface from interfering with VM internals. So these will allow you to use third-party code in a somewhat safer way, prevent some potential exploits for poorly designed or malicious third-party libraries. Like I said, we can probably try and remove some now redundant software bounds checks and things. This will require a nicer handler for the SIGPROT, because currently we just sort of throw an OS error. The last sort of thing that we're looking at is MicroPython is designed really for embedded systems. And while we don't, Murillo is currently a server-grade processor, but there are Cherry processors in the works that would be targeting embedded, so creating a freestanding implementation of the Cherry interpreter is an interesting place to go there. Thank you very much.
Okay, we've got time for a few questions. So I'll start. So in a lot of representations in runtimes, right, they have 31-bit integers or 63-bit integers or whatever. But now we've got there's the extra tag bit. Could you see ways of using that to alter the representation if you're using a Cherry?
Absolutely. So I mean, that's not really removing software checks, but it sort of falls under that category of taking advantage of the extra information and extra security that Cherry gives us to improve things. So yeah, I absolutely think that we could move from taking one bit away from integers to just relying on the tag bit. There are a couple of issues you'd want to distinguish between a capability that has had its tag cleared because it's been manipulated invalidly from a real integer. If you can change types that way, that might cause problems, so it would require a bit more investigation, but it is something that we're hopeful about.
So how do you see Cherry and capabilities being accepted or integrated into more runtimes?
Can you speak up? I couldn't quite hear that.
So how do you see Cherry and capabilities in general being integrated into more runtimes? Do you think they will modify the implementation, or eventually you will fall into a hybrid mode where the runtime runs inside a sandbox that is managed by Cherry?
Well, ultimately, in order to take full advantage of Cherry, it is necessary to modify some of the code. The code necessary to be modified just to get it to run on a Cherry system, for instance, under the hybrid ABI, is minimal. But in order to take full advantage of the security guarantees, there are certain, like I laid out, source level changes. I don't expect those to necessarily change, but as new software is developed and developed with better principles, you can wind up with less areas where you need to change things, because ultimately most of the changes you need to make come from assumptions about undefined behavior that never really should have been made by the original programmers, but were anyway.
Thanks.
Okay, time for one more question if we have. Okay, let's go for lunch, right? Could the speakers of the next session introduce themselves to?
let's get started. So I hope you had a nice lunch. So we'll have this session is gonna have 4 great papers about profiling, tuning, and tracing. And the first speaker is Orion. He's gonna tell us about the multifaceted memory analysis of Java benchmarks. So Orion, take it away.
Hello, everybody. My name is Orion Papadakis. Is it okay? Okay. Hello, everybody. My name is Orion Papadakis. I'm a research associate in the University of Manchester. Before that, I was doing my PhD, again in the University of Manchester with Christos Kotsalidis, and part of this PhD is the work I'm going to present you today. First of all, I would like to briefly discuss with you our motivation, the research tools we used in order to conduct our study, the characterization methodology, and our results and our conclusions. First of all, this is a characterization paper. Consequently, it does not follow, let's say, the traditional narrative that we find bottleneck in performance, and we invent a mechanism in order to improve performance. However, it relies on specific research questions. First of all, do we know enough about the memory behavior of the benchmarks that we use? For example, is the Da Capo benchmark suite, which has been released in 2006. And of course, for this benchmarking suite, we know a lot of stuff because a lot of studies have focused on the memory behavior. It has been used, a lot of applications have been used in, to evaluate optimizations, so we know a lot. However, we have a new benchmark suite, the Renaissance, which is called Renaissance, which has been released in 2019. And so far, there's no any memory study for all the applications of this suite. And the second question, which derives actually by the first one, is how can we effectively characterize and study the memory behavior of a Java application? So one might think, okay, this is a topic that we already know a lot of stuff. For example, if a VM researcher or practitioner would like to study the memory behavior of an application, of a Java application, has a lot of choices regarding the profilers and the tools that can use. Most of those tools provide a lot of metrics regarding object allocations, threads, garbage collection. However, all those metrics converge to the fact that all are high-level metrics regarding the behavior of the application, on the application level. And another question that arises is that sufficient in order to characterize the memory behavior of an application? If we study the interesting, let's say, case of Sunflower benchmark from Da Capo, we observe the following. If we use and try to characterize this application using high-level metrics, for example, the object allocation, the amount of object allocation, the object allocation rate, the object access rate, we conclude that this application is memory intensive because it does a lot of object allocations, that stuff. However, if we carefully consider low-level metrics, such as the LLC misses per kilo instructions, and metrics related to cache hierarchy, we reach to the conclusion that this application does not put significant pressure to those subsystems. Consequently, we don't know exactly. We reach to a different conclusion than the first. So this case shows the necessity for multiple profiling, let's say, facets that derive by different layers of the stack. For our study, we use Machine VM, which is a metacircular research VM for Java applications. Metacircular means that it is written also in Java. And we use that VM because it is easy to expand, to write tools on this. And also, it provides some tools that are very useful, such as the NUMA profiler and the PerfUtil. In brief, NUMA profiler is a typical Java application profiler that tracks object allocations, object accesses, and has some other NUMA capabilities which are out of the scope of this work. A notable an important feature of NUMA profiler is that it keeps track of object accesses and also can classify an object access whether if it is shared or thread local. On the other hand, PerfUtil is a profiler that binds the perf functionality of Linux kernel, and therefore it is able to provide metrics such as CPU cycles, hardware instructions, metrics related to cache hierarchy, and that stuff. So we propose a characterization methodology which has two steps. The first step is to try to characterize each application. We study 30 Da Capo and Renaissance applications. So to try and characterize each application according to only high-level metrics. In this case, we take the allocation rate and the access rate. And in case an application has an allocation rate greater to geomean, we say that it is intensive in terms of object allocations. And similarly with the object accesses. If it has both, you can see the benchmark in the intersection. Also, in the paper, we provide a lot of numbers related to other metrics as well, and you can see them in the paper. And with this characterization, we find that the already known trends for Da Capo are confirmed. Yeah, anyway. The second step of our characterization, we try to classify its application with only low-level metrics. And for this, we use the L2 MPKI and LLC MPKI's misses per kilo instructions, which is a metric that can be used in order to assess the pressure an application puts on the L2 and LLC subsystems. Consequently, the pressure that puts in LLC and main memory. Again, with the same heuristic, we classify our applications. And in the figure, you can see which of those are LLC intensive, which of those are memory intensive, and which are both. Finally, we take the two previous characterizations, and we merge them, and finally, we can see in this figure, we can see all possible categories that an application can fit. Yeah, and this is actually the final characterization our paper proposes. If we focus on some notable cases, the first one, on the one hand, is Sunflow and Philosophers. Using only high-level metrics, we observe that we conclude that those applications are memory intensive because they allocate and access a lot of objects in a high rate. However, if we focus on low-level metrics, we see that this is not happening. And on the other hand, if we focus on DOTI, FJK means, and Scala bench 7, we see the opposite, that in terms of object allocations and object accesses, those benchmarks might be considered as not memory intensive. However, if we focus on LLC and main memory, we see that those applications put significant pressure to those subsystems. Consequently, we believe that such a multifaceted characterization is able to provide a more complete image about the memory behavior of an application, a more complete characterization, and this is its strength. Before concluding, we have to consider the following. As we already know, we might reach to a different conclusion if we choose a specific iteration or another VM or a specific garbage collector. Consequently, we need to have confidence whether our results are actually transferable to other VMs. So to evaluate somehow the impact of Maxim VM on our results. And in order to do that, we conduct the following experiment. We compare the results from Maxim VM with results from OpenJDK 8 and OpenJDK 11. OpenJDK 8, and because in OpenJDK we don't have a profiler that is able to, like perfutil, that gives low-level metrics. We use the perfstat tool of Linux, and we compare. We do the same characterization steps with Maxim VM and the OpenJDK. And the outcome of this experiment is that 71 and 81% of the applications falls to the same characterization, to the same category. 71 is for the LLC pressure, and 81 is for the main memory pressure. Consequently, those results show that indeed our VM has an impact on the results and the characterizations that we see. However, it gives us confidence regarding the trends, and give us confidence regarding those results are, in their majority, transferable to other VMs as well. And of course, those cases that are more sensitive to those factors, the factor of VM, garbage collector, and that stuff, for those cases, we raise the awareness of the VM researcher or VM practitioner that in case they use those applications, they need to perform an ad hoc evaluation in order to draw safer conclusions. So, to summarize, our work shows the benefits of multifaceted profiling. It provides a characterization study regarding the memory behavior of 30 da capo and Renaissance applications. And of course, as you can see in the paper, you can find a lot of numbers. Some of them are discussed, some other are there for future reference, and we believe this can be quite useful to the research community. Thank you very much.
Let's have a speaker. So we have some types of questions.
So you said that like 71 to 81% matched up. But the specifics of your methodology are basically that you're drawing a line at the median, and things that are above the geomean count in one direction and below the geomean count in the other, which means that if you have a variety of benchmarks that are like kind of close to the geomean, which doesn't seem unreasonable, then relatively small changes in not even like major changes in performance, but just slight changes in which ones are slightly faster or use slightly more memory on one VM versus another will significantly change the characterization because you've got a binary characterization. Did you look at the specific applications that you found as sensitive and verify that there's like a big difference in behavior, or is it just small differences that are turning up as significant because you're drawing that binary characterization line?
Yeah. First of all, in order to be fair in this comparison, in this experiment, we're, let's say, blind. So we draw the line, and we said if it is above the line, it gets this characterization. If it's below the line, it gets the other characterization. After that, of course, we saw each application in detail. In the paper, we discuss some cases that we believe this behavior is justified. However, it wasn't possible in order to find an explanation for all cases. But in most of the cases, especially those that fell in the same characterization, if you see the numbers, you will understand that the difference is not that close, so you can confidently say that it is in the same trend. So that was...
Any other question?
So some years ago, Amir D1 and students working with him worked on this thing they called vertical profiling, to take profiles at multiple levels through a program. So you have your hardware events and then more sort of language level events and so forth, and relate them. I was wondering if you would run across that, or maybe it would be something that would shed light on ways you could go in the future. So they call it vertical profiling or temporal vertical profiling?
Yeah, our methodology is quite similar to this vertical profiling, but the main, let's say, motivation for our work is that we have new benchmark suites, so we need to study them, and that was one of the gaps, let's say, we tried to address with this paper. And also, for example, for the capo application that we can see a lot of papers having characterization for them regarding memory, we didn't see any taking under consideration both high-level and low-level metrics.
Okay, thank you.
Hello, thank you for the presentation. Okay, so you say that conclusions might differ across iterations, VMs, GCs. I also wonder how you compared Maxine VM and OpenJDK. Like, did you use the same garbage collector? I assume that there is, it's hard to actually compare this two.
Yeah, this actually, we described this methodology in the paper, but I didn't want to spend the time with details. That's why I didn't mention. Maxine VM uses a semi-space garbage collector. So for OpenJDK, we use the serial collector in order to be as close as possible. And in OpenJDK 11, to be honest, right now, I don't remember the configuration, but we describe it in detail in the paper. Also, a difference is that Maxine VM does not support escape analysis and compressed pointers that the OpenJDK does. So that was another configuration that we took under consideration. But all those details, of course, we provide them in the paper.
Okay, thank you.
All right, let's sing the speaker again.
Thank you.
All right, so now we are going to have Claire continue on the topic of GC, but this time about how to trace GCs. on a different VM.
Hello, I'm Claire. I'm an undergraduate at ANU, and today I'll be giving a talk on improving garbage collection observability with performance tracing. This is joint work with Steve Blackburn of Google and ANU and Zhixian Kai of ANU. So let's start things off with a fun fact, or maybe not so fun. Debugging garbage collectors is really hard. Luckily for us, we have a bunch of tools to help, and we can group these approaches into kind of a few main debugging approaches. So the first type is sampling, and generally this looks like some quasi-periodic interrupts where we observe snapshots of the program state. And so this might be like looking at some call stack samples and then identifying hop methods and their calling context. The second main approach is counting, and this is really an aggregate method. So it might be looking at, say, the number of times an allocator slow path gets called, or the proportion of a heap that's live after a collection. The final type is logging, and generally what happens is we pick a metric set, and then we just dump a bunch of information about these metrics to some log files. So what's the problem? Well, it turns out all of these methods have quite a lot of limitations that are particularly problematic in the context of GC debugging. So the issues with sampling come from its inherent statistical approach. Sampling suffers from a lot of sampling bias. Because we're taking like these periodic interrupts and then looking at what the program state looks like then, we get dominated by an average case. And so it's really difficult to capture tail performance. It also means that if we really wanted to try and capture these tail events, we'd probably have to take a huge amount of samples. And even then, we might not really be able to see anything. Sampling also only gives you statistic correlations between events, and so we can't actually draw proper conclusions on causal links. And for GC, this is quite problematic because work is constantly being dynamically generated. You know, say you do an object graph traversal and you look at some nodes, you might discover more nodes that you have to look at. And so we want to be able to trace things back to root causes. The main issues with counting are just that it lacks detail in general. We're collapsing a distribution down into an aggregate number, and we also lose a lot of temporal info. So, you know, it's, for example, a lot less helpful to know that 15 GCs happen than exactly when each one started and ended. The final one, which is logging, has some problems caused by the need to pick a metric. So because it's generally just very impractical to try and log everything, we need to have a good idea of where the root cause of our performance problem might be, because then we can pick some metrics. And this often involves having quite intimate knowledge of our code base. It's also quite inflexible because every time we want to change a metric or look at something new, we need to modify our code base. And normally your log files are quite unstructured, so then we might have to write some parsers as well. And this might be an example of a log file. So what's the solution? Well, there is actually one debugging approach called tracing, which is quite common in general systems debugging, but remains largely unharnessed in GC debugging. We're going to make the case today that it is very powerful and flexible and really nicely complements the dominant methods that we just talked about. So the key idea with tracing is that we're capturing a dynamic trace of a program's execution. And this is done through these things called trace points. Trace points can look like non-inline function calls and returns, or things that we statically define into our code. And they're either active or inactive, and that's something that you toggle at runtime. Trace points can also take arguments, which will be important later. So here's an example of a trace point. So the probe call in some Rust code. And when they're inactive, they're instrumented as no-ops, which means they have basically no overhead. This is really important because it allows us to compile a set of trace points into key parts of our code base, and we don't have to really worry about performance implications. To actually activate a trace point, you write some tracing logic that attaches to it. And that's how you determine what data actually gets recorded. And then when we actually encounter an active trace point, a bunch of information gets packaged into a trace entry, and then you, I guess in the kernel side, the tracing logic is compiled to some bytecode, which then performs your user-defined tasks. And what happens there is your trace entries basically get processed in temporal order. So because all of your tracing logic is actually programmed at runtime, tracing decouples the actual trace points from the tracing logic. So we can reuse the same trace point to analyze behavior against metrics that we get to choose at runtime. So for example, up here, the same trace point is used here to measure the distribution of your work packet sizes. And then again here by swapping out some of your tracing logic to measure the total number of work packets. And then again here for a distribution of the root packet sizes. And all of these metrics were chosen after compilation. Because of this kind of design, tracing doesn't suffer from a lot of the problems that logging, sampling, and counting suffer from. So unlike sampling, tracing attaches context to events. And this means that we get to pick the level of abstraction that we can debug at. Tracing also, because it records kind of every single event that happens, it's really easy to capture rare events and then trace through these temporally to really clearly see causal links. Unlike logging, we also don't need to know a fixed metric set beforehand. All we need to do is have a set of very useful trace points and then just write some tracing logic to attach to those and pick whatever metrics we want later. Another note is that tracing outputs are quite structured, and so we don't have to instrument parsers, which is nice. In our work, we use MMTK, Memory Management Toolkit. This is a framework for building collectors, and it allows us to combine these low overhead trace points with a modular GC design. This is super advantageous because it means that all of the advantages of tracing really readily translate to all of the supported language bindings and collectors. But I will also note that a similar sort of approach should benefit any sort of collector implementation. So before we discuss the debugging approach a bit more concretely, I want to give some background on how the collectors in MMTK work. So collection work is done by a bunch of GC worker threads that execute work packets, which are basically just like packets of lots of work items. So these work items get grouped into packets by work type, and then these packets get bucketed by preconditions. So one key feature of the design is that these work packets are self-contained. So they normally have like a pointer to some code that will tell you how do you process this packet and what preconditions do we need. And then these work buckets get executed serially. So as an example, you have two worker threads here, and the different colors are like different buckets. So they might execute some work packets and then produce some more work packets dynamically into your local pools. And then they'll just keep grabbing from the global pool. When they run out, they'll grab from the local pool. And when they run out of that bucket, the bucket closes and a new one opens. With that kind of work packet design in mind, we can now identify a lot of critical points in the MMTK codebase. And these are the ones that we've pulled out. So the first one, collection start and end, lets us look at the stop the world collection time. The second pair of trace points lets us look at the time we spend in the allocator slow path, and they fire about every like 64 KB of allocation. The third set, bucket opening, just records when the bucket opens, and because these buckets execute serially in a fixed order, then we can also know how much time we spent in each bucket. This fourth set of trace points records things at the granularity of work packets. So we can look at things like the work packet type and how much time we spent in the work packet. And this last one is a bit different to the previous four in that it's a really important special case. So the process edges function is the one that completes the transitive closure over the object graph. And this set of trace points gives us information about that. So things like the number of edges we visited and the packet size. In total, this was 14 lines of Rust code, which brings us to our first claim. Tracing is inexpensive. In a software engineering point of view, we wrote 14 lines of code, but also from a performance point of view. So on the board here, these are some of our overhead numbers. I'm not going to go into detail, but I'm happy to come back to them. The main thing I want to highlight is that there was essentially no overhead when the trace points are inactive. So we can compile these things into our code, leave them off, and then not worry about that affecting our performance. Today we're going to talk about one of the case studies we did, and this was using tracing to examine the scalability of the transitive closure stage of garbage collection. This is something that we're really interested in because the object graph trace typically dominates our collection time, and so understanding points of poor scalability will help us improve the overall collector performance and scalability. Just a note on methodology, we used OpenJDK 11 with MMTK and the DiCapo benchmarks from the 2023 Chopin Dev branch, and we had 2 different architectures. So when we were looking at scalability, we picked out 4 different metrics, and these ones were scalability of the transitive closure. So this just looks at against like against a one-threaded application, how much quicker is your transitive closure getting when you double the amount of threads. And in order to measure this, we use the bucket open trace points. The second metric is the distribution of work packet sizes. And in order to measure this, we use the process edges trace point. This is something that's important to understand because the actual work packet size distribution can very much change how well things scale. So, if you have really large packets, then you're much better amortizing fixed costs, things like global synchronization and packet fetches. But if you have much smaller packets, then they're a lot easier to distribute among your threads. This third metric is quite similar, so we're looking at the root packets now, which are the ones that prime the closure. And the motivation is very similar to why we want to look at general work packets. And the final one is an explicit measure of load balancing. So generally, if we have scalability issues, they come in the flavor of like load balancing or some form of contention. And in this case, we're looking at how is work distributed among our threads through time. And so we can actually look at, are threads getting starved out? Are things being load balanced nicely? In this talk, we're just going to focus on these 2 for time, but we do have results for the other 2 in the paper. So if we look at closure scalability first, these 2 plots are the same plot, but with different things colored. So the lines on the plots are different benchmarks from the Capo suite. The x-axis is the number of threads, and the y-axis is the factor of speed up that we're getting. And I guess the red dotted line as well is perfect scalability. So the first thing we might notice here, if you can look at the really faded lines, is that scalability is quite workload sensitive. What I've done here is pulled out 2 that didn't scale very well, and we're going to dig deeper into these because a lot of the time workloads that don't scale well can tell you a lot about potential areas for improvement in your collectors. So next we'll look at work distribution through time, and we've got the 2 that didn't scale very well, FOP and LU search, and Tomcat is up the top just as an example of good load balancing. And here tracing makes it extremely clear visually that we have a load balancing problem in these 2 poorly performing benchmarks. So let's zoom in a bit. This here is just looking at FOP, same picture as before. The 2 arrows indicate when buckets are being opened, and we can do that using our bucket opening trace point. And we can see that we've basically got one thread executing a bunch of work packets in some sort of linked list situation. Doesn't look parallelizable, and it's all in one bucket. And so we annotate that, and it's finalization. So by using tracing, it's now abundantly clear that the source of the poor scalability in this benchmark is serial execution of finalization. Next, we can look at LU search, and we're going to zoom in on that little slice in red there, because, yeah, I guess just to give some context, what we can see here is we've got load balancing problems as well, and there seems to be 3 threads that just keep working, probably on some sort of linked list situation again. And so we'll just look at one of them and then figure out if it's kind of the same problem for all 3 threads. So if we zoom in on that slice there, we notice a really long list of work packets. And using the process edges trace point, we can annotate these packets with their size. So we know actually each packet is the exact same size. They all have 25 items in them. We also can run this over a bunch of collections and notice that this happens every single collection cycle. And so we hypothesize that there's some sort of unparallelizable long linked list structure happening. At this point, tracing has helped us narrow down a problem that we probably normally wouldn't even notice, down to like an issue with some sort of linked list structure. And doing a quick type dump tells us that every single packet here corresponds to a search query file, which LU search failed to close. So basically, we've identified an application bug. And in fact, after we put the bug fix in, the scalability issue appears to have resolved itself. There are 2 points here that I want to highlight. The first one is just how flexible this tracing framework is. So, for example, we used the same process edges trace point to look at the distribution of work packet sizes, and then we used it again to look at the distribution of root packet sizes, and then we used it again to look at load balancing. And all of this we did on a running binary without recompiling. So I guess the point here is that it's super flexible in that we can examine a series of different problems without even knowing beforehand what we actually want to interrogate. The second point here is how it amplifies subtle performance issues. So things like the subtle application bug in LU search and the serial finalization issue in FOP probably would have gone unnoticed otherwise, but in tracing, it was just so visually clear what was going on. To wrap things up, GC debugging is just notoriously tricky, and all GC developers really need to rely on a collection of powerful tools. But the issue that we have right now is that a lot of collectors lack support for tracing, and instead we rely on things like sampling and logging, which simply are just not quite sufficient. Our work here shows that performance tracing really nicely complements the existing debugging approaches, providing low overhead observability, flexibility, and amplification of subtle issues in ways that the dominant state of the art can't. Thank you.
Any questions?
I always connect tracing with large trace files. So how much data do you collect? Is it a problem? Is the amount of data that you collect a problem, or was it no problem at all?
So what we use is an existing tracing framework called eBPF, and it essentially provides like a lot of code already for handling things like histograms and stuff. So actually storing those is almost nothing. So the data itself that we produce is not a problem.
And a follow-up question, could you somehow use similar approaches that you used for monitoring garbage collectors for normal user applications too? So sampling, like method calls or whatever. Could you just transfer it to normal programs?
Yeah, I think that like similar tracing approaches could be just generally very helpful in all sorts of systems debugging. I guess the advantage that we had here was a very modular collector design. And so that means that you put a set of trace points in, and then you're getting observability on a bunch of things at once. So, if you want to translate this idea to something else, it might involve a little bit more instrumentation.
Okay, thank you.
Thanks.
So you mentioned eBPF. Why did you choose eBPF? Won't this force you to constantly switch between the user level and kernel level to do, on any trace point, you actually do a transition, context switching, right?
Yeah, so I guess, actually, maybe for a bit of context. So eBPF is a tracing framework, and the idea is like you write these BPF programs and you target like a sandboxed in kernel, and then that responds to user space events. So the main like overhead that you get there is the context switch, right? And in our case, we picked eBPF just because of how flexible it is. And we did a lot of evaluation, which I have here, and it's also in the paper, on the actual overheads. So if we go back to this slide here, so this slide here is the actual like performance overheads that we had. So the TP columns are like unattached trace points, so that's just the cost of compiling these things. OB is like the open bucket trace point, and P is process edges. And we can see that, like, for example, for the bucket, for the open bucket trace points, like, we're looking at like fairly negligible performance impact. And even with process edges, you know, you might have, say, a collector overhead of about 12%. And in a lot of contexts, when you're debugging, it's not like negligible, but it's small enough that we consider it okay.
What were the inspirations of this work? Where did you get the ideas?
I guess the main inspiration was just that debugging a lot of like GC things within the group was very, very tricky, and you're lacking a lot of observability. You know, generally we're looking at like taking samples, doing like a bunch of ad hoc re-engineering and whatnot. And then someone in the group had done some work, I think maybe with Google, that used this like eBPF tracing. And we thought, oh, this is like really cool. We could apply this to our GC stuff and hopefully get rid of all of the annoying ad hoc engineering that we're doing.
All right, let's thank the speaker again. So now we have a talk by Humphrey, and he's going to tell us that maybe we shouldn't trust our profilers.
Hello, I'm Humphrey. This is our presentation on the paper we did, which is Don't Trust Your Profiler, an empirical study on accuracy and precision of Java profilers. I did this work with Octav, Sophie, and Stefan, and myself, obviously. So let's get started. Why don't we trust profilers? In our work, we have to make use of benchmarks quite a lot, and we're interested in how the performance of those benchmarks actually breaks down. What method do you spend the most amount of time in? And so we ran a profiler. This is for the Delta Blue benchmark, which is quite well known. And that's what we got back, and it's just telling you there that 11% of the time was spent in dictionary.getBucket, and then so on for the rest of the methods. Why we were suspicious is because we have a knowledge of the code, we actually suspect vector.forEach should be the most important method, the method that takes up the most amount of time. So instead of just believing the profiler, we actually ran it again. This is what we got. As you can see, the first thing is dictionary.getBucket does not appear in the second run at all. Its percentage of runtime is so low, it's below the top 5. Something else you might notice is vector4each is now suddenly the most important method on the second run. So who do you believe? And that was the inspiration for this paper. So what were some of our research questions? Do profilers have consistent self-precision? That is, if you run a profiler multiple times, do you get the same result? Do multiple profilers agree? If we ran different profilers against each other on the same benchmark, is the result similar? And finally, are profilers more precise when safe bias is removed? Previous work has identified safe point bias as a problem in Java profilers, and now profilers now take into consideration in their design safe point bias to help reduce it, and we want to know, has profilers got better since then? What will we actually show? We'll show the average precision of 6 Java profilers, all samplers. We will show the worst case scenarios where there is actually disagreement from run to run. and the disagreement between the different Java profilers we tested. And finally, we'll show the average overhead of our Java profilers. So what is a profiler? A profiler is a tool that helps you understand what the computer was doing when the program was executed. It collects lots of information. It can vary from profiler to profiler. You can have CPU, GPU, and memory metrics, for example. Profilers are not just a niche tool used by a few developers. There's some quite famous examples. AMD has CodeXL and UProf for their GPUs and CPUs. Intel has vTune, which allows you to profile lots and lots of languages on Intel hardware, and very recently, now on some features available on AMD processors. There's Valgrind, which is a well-known profiler for memory debugging and memory leak detection. And then there's also Amazon Code Guru, for example, which uses machine learning to try and find expensive and slow pieces of code. Because we're only testing sampling profilers, we're only going to go into actually how a sampler works. CPU sampling is the process of periodically interrupting the CPU to see what the current state of the hardware is. The types of things you may collect may be stack traces, instruction points, or memory usages. After that, you should have enough samples to sort of build an image of what did the program do during the execution. These outputs are then sort of turned into something more meaningful. Almost all profilers give you some sort of console output like we saw at the beginning, where you just get a list of the methods and the percentage runtime. There's also flame graphs, which sort of try to visualize stack traces, where each block is a method, and then the peaks and the mountains are the actual trace of all the method calls. There's also a hierarchical view where you can get the most important methods at the top, and then it gives you the percentage and the amount of time it took. Problems with profilers. There has been some previous work on Java profilers. The main paper that influenced this work was evaluating accuracy of Java profilers. They investigated the accuracy of 4 Java profilers, and their evaluation showed that there was a disagreement between them. This is their figure 4. It's very difficult to see. They had, for here, this is a Jython benchmark, and out of their 4 profilers, one of them, YourKit, decided that it was 35% of the runtime, while the others decided it was 22%. Not decided, but discovered. And they found lots of examples where profilers would just disagree with each other. What's the possible reasons for this? They identified safe point bias. It's not required to know what safe point bias is for our paper, but it's the Java garbage collection has safe points, and this actually restricts where stacks can be sampled. And therefore, the program there isn't an equal chance that the program can be sampled and at all points, which therefore breaks the point of sampling, where it should be an equal amount of probability across the program. What's the differences between our 2 papers? They tested 4 profilers, we tested 6. We do share 2 similar profilers, JProfile and YourKit, because they're actually the maintained ones, and the other 2 they tested are no longer maintained. They used the Decapo benchmark suite, whereas we will use the RFastJet suite. There's also a big problem of time. Theirs is over 13 years old, and when they identified safe point bias, incorporating strategies to reduce safe point bias was not in profilers' designs at the time. So we want to know, 13 years on, has the situation got any better? Is safe point bias, has the precision issues caused by safe point bias got any better as well? There are some other problems with profilers. Overhead, obviously, the act of interrupting the CPU will incur overhead. Samplers generally have much less overhead than instrumentation, but they still cause some. There's also the overhead observer effect problem. Whether it be probes or the sampling, this added overhead is going to incur a change in the program's execution. Small amounts, large amounts of overhead can cause a different optimization choice by the compiler, and therefore the program is different from if it was run without a profiler attached. These were our 6 chosen profilers. Async, Honest Profiler, and Java Flight Recorder. We know, because they're open design, or they've told us, that their design incorporates strategies to reduce safe point bias, and therefore they should have a minimized effect by it. JProfile and YourKit are commercial products, and we don't have access to their code, so we don't know if they've tried anything to reduce it, but it is assumed they do. And Perf is a Linux tool that supports Java profiling, and that will be at the machine level, so it shouldn't have too much problems. And to be clear, all the profiles we tested were CPU samplers and not instrumentation, or we used them in sampling mode. So, do Java's profilers have consistent self-position was our first research question. What we actually mean by that is we're interested in the precision of the profiler. Precision to us is how close the measurements are. Evaluating the accuracy of profilers is very hard, thanks in no small part to the JVM's non-determinism. It's impractical to know what the perfect profile would be, the exact amount of percentage that the method should have or doesn't. And therefore, we were more interested in how consistent the profilers were with reproducing a similar result from run to run. So we won't be focusing exactly on how correct the report is, but simply how close it is to the previous. The benchmark suite we're using is the Are We Fast Yet suite. We chose the suite since it contains relatively well-known benchmarks. They also encapsulate common program behaviors. There's 9 micro benchmarks and 4 slightly macro benchmarks. There's also the column for hot method execution in iteration. These are methods that are executed during every iteration, and they have a high chance of being JIT compiled, which would mean that they have a good chance of turning up in the profiles. So what is actually an experiment? A run of 300 iterations for each benchmark. We then repeat that 30 times for each profiler. What this actually gives us is 30 runs of a profiler with itself, so we can compare a profiler for any given benchmark 30 times. We will also then take the mean of those 30 results and then use that for the cross comparison of the different profilers. Why did we do so many runs? The length and the number of the runs should help the program reach peak performance and have a stable behavior. Also, using the medium should help minimize the effect of the JVM's non-determinism for the cross-comparison. We also think this is a very fair way of testing the profilers. In most common use cases with profilers, you would probably run it once on a benchmark and not for that many iterations, and then take that one result as the results. So what was our results? The first graph here is plotting the differences in percentage of runtime we found for all the methods for a given profiler across all the benchmarks. We took all the methods found by the profiler and calculated the differences in percentage of runtime from across the 30 results. What this effectively gives us is the margin of error for each method the profiler finds. So what are some of the conclusions we found from this graph? The average precision is quite good. No profiler seems to have a persistent problem with self-precision. We did find that there were that all of them reached at least a 15% difference with at least one method, and also we found some outliers which were quite far out, and we will now go to show actually how misleading these outliers can be. So this is the worst case we found. This is the Delta Blue benchmark, specifically for the Java Flight Recorder, but we found that all the profilers had a problem with Delta Blue benchmark. On the x-axis is the percentage of runtime, and the y is all the methods that were identified in the 30 runs, and it was the top 10 hottest methods, but obviously there's more because there was 30 runs. The red lines show each time a method was identified as the first hottest in at least one of the runs, and the error bars show the range of that percentage for that method. As you can see, there's 8 methods that were identified as first hottest in at least one of these runs. You can also see methods like plan has a very large range of 5% to 29%. This is very large. With this example, if you ran the profiler for just once and took just one of the profilers, that one profile as the answer, you were going to be misled. There is a high probability that most of these are incorrect, and therefore one given run of the profiler will give you an incorrect profile and lead you to do an incorrect optimization choice and make the program worse. Second example is average case. While there is no change in the first hottest method, there are some methods with quite large ranges. And for example, if you were not able to optimize the first hottest method for whatever reason, picking the next important is going to be quite a challenge. You can see with get a recurse here that the range is really, really far. And you would have a problem choosing what method to optimize here. So how do the profilers compare to each other? This is a graph trying to compare all the different profilers for the first hottest. A 1 would mean that all 6 profilers found the same method, and a 6 obviously means that 6 profilers found 6 methods for the first hottest. We found that there was more disagreement than agreement. Delta Blue and Richards was the worst, with 5 methods found, which means only 2 of our profilers actually agreed with each other on what the most important method should be for that benchmark. 2 of the best benchmarks we've found was Permute and Mandelbrot, where all 6 profilers identified the same method. It must be noted, though, that these benchmarks consist of only really 2 methods, so it was actually quite easy for the profilers to agree on that one. We did the same again, but instead of doing the first hottest, we did the top 5, so what were all the methods found in the top 5 across our 6 profilers. It's much worse. Delta Blue, for example, has 28 methods were identified between our 6 profilers for the top 5. And none of the profilers were below actual average. So our conclusion from this is that if you were attempting to collect accurate and precise profiler data by using multiple profilers, you may just end up with more confusion than actual answers. And also we can conclude that because there's such disagreement, at least one of these profilers or more must be incorrect, as there can't be multiple first hottest methods. Overhead, we plotted the median overhead for all 14 benchmarks for the profilers. It's very good. They're all quite low, which is in agreement with most of their marketing as being low overhead profilers. We also found no correlation between overhead and self-precision. JProfiler, which is the highest in overhead, was not also the highest or lowest in self-precision, and neither was Honest Profiler, the lowest in overhead, the best in precision or the worst in precision. It must be noted, though, that JProfiler has the worst overhead of 5%, and for some larger systems, 5% overhead might not be actually acceptable and could lead to some biased results. An observation, we also found an example of the compiler being non-deterministic. With this graph, we're plotting the percentage of runtime over the median runtime for that iteration. We found for this, which is async, or for the Queen's benchmark, that a change in percentage of runtime does occur. And we've noticed between the 108 milliseconds, there was a sudden change in the amount of percentage runtime. The top one, which is Queen's.getRow column, which is blue, goes up from 60% to 70% in runtime after a certain period of time. Our explanation for this bimodal distribution of points is there's an equal chance that the compiler makes one or another optimization choice, and is likely an example of the compiler being non-deterministic. Going forward in the summary, we have begun to investigate Java instrumentation as well, beyond the paper, with some early experimenting using Visual VM. We took the CD benchmark from ReFastJet, and we compared the profile before and after turning the compiler optimizations on and off. We also did this with the async profiler, which must be noted is a sampler, so that was a sample in the top one's instrumentation. The profile, as you can see with Visual VM, remains mostly unchanged whether the optimizations are on or off, which is actually incorrect. You would expect that if the compiler is optimizing, that there will be a change in what methods are the hottest, and at least the percentage. And we can confirm this with async clearly has a big change in what methods are important and what are not when the compiler goes from optimized to unoptimized. Our conclusions from this is presence of probes caused the program to be de-optimized. This is a very, very similar optimization observation made in the paper, the observer effect of profiling on dynamic Java, where they counted the amount of inlining and found that it was the presence of instrumentation meant that inlining remained unchanged. So to summarize, the good, we found that the average precision of our six Java profiles was quite good. We found with our 14 benchmarks that only one had caused problems with self-position for our profilers. And we found that the average overhead for all of our 6 profiles is low. The bad, we did find cases where profilers can change its reports significantly from run to run, leading to misleading profiles. We found on average that profilers are in more disagreement with each other than agreement, and therefore at least some of them must be inaccurate. And finally, the reduction of SafePoint bias has not fixed the problem with Java profilers' inaccuracy, and therefore profilers should still not be trusted to be correct. Thank you. That is the end of the presentation.
So we have time for a couple of questions.
So just one quick observation first, so one of the original developers of Valgrind, Julian Seward, works on our team at Mozilla and is constantly in a fruitless quest to convince people that actually it's Valgrind, named after the entrance to Valhalla, not Valgrind. And he's never been successful inside Mozilla either, but I just thought I'd mention it. The second question I had was, to what extent are you confident that, especially in cases where there's a specific benchmark where profilers see a bunch of different hot functions, that it is in fact a problem with the profiler and not just that this benchmark itself, that they are accurately reflecting the reality of differences? And in particular, I'm wondering about inlining decisions and whether that would have a significant impact in this case.
Yeah, we think it's going to be program specific why they're disagreeing. We did afterwards quickly do the exact same thing, but we used the DiCapo benchmark suite, and we found that there was also another benchmark in there that had real problems with self-position with our profilers. But yeah, we think it is program specific, and it could be that these programs contain something that profilers are all making assumptions on, which is causing them to make problems.
So is it possible that the actual ground truth answer is that if you had a magical perfect profiler, from run to run of Delta Blue, different functions would show up, and the profilers are accurately reporting a non-determinacy in Delta Blue itself? Have you ruled that out?
No, my answer to that is I'm not going to claim that they're perfect or they're not imperfect, but clearly there is something that is causing profilers to have a problem, whether that be with the program or with the profilers itself.
Yeah, there's a problem there. I'm just unsure, or questioning how we can determine which bucket it's in.
Was the sampling frequency modifiable for the 6 profilers?
Yes, and we kept them all exactly at the same frequency.
Okay, because I thought like if you have different sampling frequencies, that should
Yes.
probably would see something different.
You'll see something different, but no, we kept all the profilers at the same, and it was 10, I think it was 10 microseconds or milliseconds, I can't quite remember, but yes, all of them were the same and constant.
Okay, yeah, thank you for that info.
If I may just follow up on that, did you try varying the actual sampling frequencies on all the benchmarks, and did that have any effect on trying to?
We did try that with one profiler, but then used a very large variety of sampling frequencies, and we didn't notice anything different. When the sampling frequency was like 1 second and the benchmark only ran for 10 seconds, we noticed that the profiler was terrible, the profile was terrible, but once we actually got to a certain point, it stayed pretty consistent regardless of the frequency.
All right, let's thank the speaker again. All right, and for the last talk of this session, we'll have Marina that is going to show us how to tune our JVMs without actually controlling the memory footprint, or actually the memory limit that we set.
Do you see anything? To transfer?
Just show the slides.
Yeah. Do you see them? Oh. That's the end of it. Now you all know that I'm looking for a job. Okay, let's figure it out. I think let's do this. Okay. Perfect. Okay, hello everyone. I will present a paper called Heap size adjustment with CPU control, which was done. That's even better. Good job. Okay, so this work was done in collaboration between several universities, but also industry, Oracle. My name is Marina Shimchenko, and there was another PhD student working on this project equally, Sanas Tavakolime, who is unfortunately, she couldn't come. I also would like to thank Google and ICM for Women for sponsoring my trip here. Now, when formalities are behind us, let me tell you a little bit about heap sizes. Okay, so I hope you all know that when you run a Java program, you also need to set the maximum memory size, or rather, your Java needs to know how much memory you're using, otherwise it's not gonna function. And it is a super important parameter. So this research that I link down here, it's also our closest related work. Among other things, they looked into correlation between execution time and memory. And what they found is this parabola-like dependency. So if you have not enough memory and very frequent GCs, it's not good for your performance. But if you have too much memory and infrequent GCs, it's not good for your performance either. So hopefully, we want to stay somewhere in the middle here. However, setting up a memory a heap size is a struggle. There are a couple of things you can do about it. You can go with the automatic approach, and your GVM will give you 25% of the available RAM on your machine. You can imagine that it's definitely too much for a hello world program. At the same time, your program can crash if it's not enough. And your alternative is to set up memory heap size manually. So this little study, they looked into different GitHub repositories to see what method people use the most when they set up a heap size, and it turns out that they go with the powers of 2. What they also found is that it's very common for people to make mistakes. For example, in almost 3% cases, instead of 8,192 megabytes, because of a simple typo, programmers gave their programs more than 8 times less memory. It just showcases that as end users, we are not very good at setting up this parameter. And no wonder, there are no guidelines. Okay, but maybe, if you spend an eternity and actually find your perfect heap size, maybe it's gonna, you can keep it forever. Well, unfortunately, not really, because the heap size varies also with your hardware. So we did this tiny experiment where we ran 4 benchmarks, Tomcat, Sprint, Batik, and Luindex on 5 different machines, and here I sorted them by the size in terms of their cores and how many threads they use, from the smallest one to the biggest one. And let's look at the numbers. For example, for Tomcat, you can see a very clear pattern. So the memory just grows with the number of cores and threads. If we look at Sprint, for example, it's kind of a similar pattern. So the heap size grows, but you can also see that we need as much memory for the 4th machine as for the 1st. Okay, it already breaks the pattern, but let's go on. Batik, well, you can see that for the 2nd machine, you need twice as much memory than for the biggest machines. And then after the 2nd one, it stays relatively the same, and the same goes for Luindex. So here, you have multiple different applications. They have absolutely, not consistent pattern of how they change heap size with the hardware. So it's not even possible for you to predict it. Okay, that's not good. What do we propose? We propose to go from setting up memory, how it is now, to setting up CPU, GC CPU overhead. So GC CPU overhead, it's pretty much the resources of your CPU that you're willing to spend on your garbage collection. Why is it even possible to go from memory to CPU? Well, there is a link between the two, and this link is GC. So let me try to give you an intuition behind it with this simple infographic. So right now, we're setting up memory, right? So more memory you have, less GC you need to do, and the other way around with less memory. But GC, in turn, it's actually your CPU, right? So more GC you do, more CPU resources you need to spend doing GC. So we can actually control either memory or CPU. Why is it good? Why is it better to set up GC CPU overhead? You can imagine a black box Java program that you need to run as a service. You have absolutely no idea how much memory it uses. You didn't develop it, but yet Java requires you to set up a maximum memory capacity. Well, that's not going to work. However, with CPU, it's easier for you to reason how much is actually reasonable for GC to spend, right? And another example would be this program with varying memory usage or varying allocation rate. So for example, let's say that in the beginning it uses a lot of memory, and then of course you have to set up your memory quite high, right? But then the rest, all of this, it's a waste of memory. It's definitely too much memory. So you're gonna end up on the right side of this parabola dependency, right? We'd rather have something like this, and I'll give you an indication how we can actually achieve this with the CPU control. So let's look at it how it was before. So before we have fixed memory, And then because, allocation rate varies, GC will vary too. And because GC translates to CPU, then your CPU will vary as well. So both the white and the green lines, they go together. Now let's say we actually fix CPU. What's going to happen with GC and memory? Let's say we have this much memory. I know it's a little bit confusing to have them all on the same scale, but bear with me. Let's say we have this much memory, and this is the current CPU, GC CPU overhead. How do I calculate it? Using this super, super simple formula, time that you spent on GC divided by the time that you spent on application. This is your current GC CPU overhead. And let's say, so here, we definitely underperform. The target is here. We want it to be here. So what we can do to go there is to adjust the memory. So in this case, we can decrease the memory to increase the pressure on CPU. Oi, but what happened? We overshoot. That's okay. On the next cycle, we can adjust it again, and hopefully, eventually, we will be together with a fixed CPU rate. And now, one thing that you can see is that memory varies instead. So before it was CPU that was varying, and now it's memory. Why now? You might have a question if it's a new idea. Well, it's actually not, but it was done in a different context. So before, we dealt mostly with stop-the-world collectors. And your stop-the-world collectors, it means that you run your GC while application stops completely. This is your stop-the-world pause, right? In this particular setting, we want to finish GC as fast as possible. So there is absolutely no reason to divide CPU resources between application and GC threads. Otherwise, if you prolong this GC cycle, it just affects your throughput. But this is not the context that we're dealing with now. Now, fully concurrent collectors emerged, and one of these collectors being the GC, for example. In fully concurrent collectors, you have GC threads running in parallel with the application, meaning that GC is not on a critical path. And if you don't like listening to my voice, you can also read this. So GC is not on a critical path. Therefore, we can actually play with the frequency, play with the duration, and not affect performance. And by performance, in fully concurrent collectors, I actually mean latency. Okay, so we did some experiments. We used the Sandy Bridge machine, 32 cores. You can read the stats. We used 2 benchmarks, and we implemented it in a generational ZGC. Let's look at the results. Let me show you super complicated graphs that everybody loves. So here you can see, this is vanilla ZGC, right? So vanilla ZGC, it's basically ZGC without changes. This is how it was before. Here you can see the heap capacity, or the maximum memory size or heap size was set to 32 gigabytes, which is, we just followed this methodology of giving it the power of 2. You can also see the time in blue before GC and memory in orange after GC. So pretty much your program doesn't really need a lot of memory, right? But yet at some point the program used the whole capacity. You gave it 32 gigabytes, it used 32 gigabytes. Okay, now let's look at it how it's now with our implementation. So this is our implementation with GC CPU overhead equals 1%. And let me just point to a couple of differences in the 2 graphs. So the first one being that suddenly the green line is not straight anymore. It adapts, so your memory varies, right? In the beginning, we start with a really tiny heap size, and then because there is a lot of pressure on GC, we have to increase the memory until the point where we actually can satisfy the target of 1%. Another thing that you barely see, but let me tell you. So here we have maximum of 800 megabytes of memory, while before we had 32 gigabytes. So here we use a lot less. But because we use a lot less memory, we have to run GC way more frequently. So that's why you have this a lot of blue lines here. Perfect. Now, we actually in the paper evaluated a couple of different GC overheads. First of all, because we wanted just to showcase that it works. And second of all, we were thinking about maybe we can find a good range that we can recommend to the users to make it even simpler for them to set up a GC CPU overhead. So we looked at 5, 10, 15, and 20%. There is nothing that prevents you to go above this. We didn't do it in the paper because ZGC, again, it's a low latency collector. So we think that there is absolutely no point to run it with more than 20% because it might affect latency. But again, you can do it. We didn't. Now, we looked at multiple parameters like time, memory. We also looked into energy and latency, of course. And energy results you can find in the paper. Latency, I'll just briefly mention. Let's first look at the execution time. Here, we normalize everything to configurations where we set heap size manually following powers of 2. And you can see here that, okay, at first, if you don't give enough space to your GC, performance drops, and then we even gain a little bit performance, then we gain a little bit more, and then we start slowing down the gains. So here, it's almost like the parabola that I showed you in the beginning. So we basically concluded that if you optimize for execution time, at least for our benchmarks on our system, a good range seemed to be from 10 to 20%. Memory just follows a very nice pattern. It just goes down, 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 down. And it makes sense because more resources you give to your GC, more often you can clean your memory, therefore less memory you need to use. And here, if you optimize for memory, you can go with really high GC CPU overheads. So if you optimize for execution time, it seems that this range is good. It is very similar to energy, because for ZGC specifically, there is a very high correlation between execution time and energy. Now, latency. Latency is actually the most important for ZGC and latency-oriented collectors. We didn't find any statistical significant results that could prove that latency got hurt. We actually found positive patterns, but latency measurements in the capo vary so much that it's very hard to prove anything. So you can read the paper, we just basically conclude that, you know, it seems okay, but statistically, unfortunately, we cannot prove anything by now. Okay, so in conclusions, we believe that GC CPU overhead is more intuitive to set up. And a good thing about it is that it's not going to vary with hardware, right? You can just transfer the same percentage to your other configurations on other machines. We also showcased the possible implementation of this technique in the context of a fully concurrent collector. And what's even more important, that we found a preliminary acceptable range where performance metrics do not drop. And by performance metrics, I mean latency. Okay, and now back to the beginning. Questions? And I'm looking for a job.
Do we have any questions?
So with a generational GC, where there's like a choice over which part of the collector runs, is there some way you could use this kind of technique there? Because it's sort of like, which part of a collector runs seems sort of, that's trained by like different sizes.
Yeah, so what we do, you can think about different generations as different cycles. So every time a collection runs, we just measure how much time you spent on your GC, how much time you spent on your application, and if it's below or above the target, we adjust the memory. So it doesn't really matter. You can totally implement it in a non-generational world. It's the same principle.
Thank you.
Hi, thank you. The optimal optimal range that you found, is that not dependent on the memory allocation profile of the application in question?
So that's the beauty of it. If you set up memory size, you have to deal with allocation rate, right? And different patterns of how your application behaves. With CPU rate, the only thing you care about is just how much resources you're willing to spend on your GC, and then memory will adapt. So depending on your allocation rate, we will just adapt. The adoption rate will be not maybe as fast as you like it to be. So for example, if there are a lot of changes in allocation rate along the application, we might be always a little bit off from the target. But if your allocation stabilizes at some point, we will get quite close to the actual memory usage of your application.
Okay. Do I have time for one more question? You also took a look at different hardware and their implication on the memory size. Did you look at different hardware with different percentage of GC targeting as well?
Well, in the paper, there is only one type of hardware. However, we did look at multiple hardwares, and in order to integrate it in OpenJDK, where we aim to integrate it, we will need to do more. An indication that we need to wrap it up. Okay, so yes, we need to do more experiments with different hardwares and also different operating systems.
Speakers of the next session should find Stefan to set up the
Okay. I apologize for the inconvenience. I swear everything worked before. So, hello everyone. Thank you for the introduction. My name is David Kozak, and as was mentioned in this presentation, I'm going to talk about comparing rapid type analysis with points-to analysis in GraalVM native image, which is a joint work with Vojin Jovanovic, Kudrut Stancu, Christian Wimmer, and Tomáš Vojnár. In our paper, we focused on the problem of call graph construction for ahead-of-time compilers, which, among other use cases, is used to detect program elements that may be used on at least one path during the execution of the program and therefore have to be compiled and included in the binary. We call such elements reachable. The key difficulty when constructing call graphs are virtual methods, because for each virtual method, it is necessary to detect all possible callees in a way that is sound, meaning no real callee is missed, but at the same time, a reasonable amount of precision has to be maintained, because otherwise unnecessary methods are included in the binary. In this example, we could, for example, prune the method m in the class C based on the knowledge that it hasn't been instantiated in the application. In particular, we based our, or rather we work on GraalVM native image, which is an ahead-of-time compiler for Java that works under the closed word assumption, meaning that all the code or all program elements that may be needed at runtime has to be available already during compile time, which poses restrictions on some dynamic features of the language, such as reflection or dynamic class loading, that has to be explicitly configured. A native image produces standalone binaries that contain the application along with all their dependencies and runtime components. Native image uses a combination of points-to analysis, class initialization and build time, and heap snapshotting to produce self-contained and fastly starting binaries. The analysis in native image starts from a set of entry points that gradually extends, and each class that is marked as reachable can potentially be initialized at build time. And if it is initialized, then all the objects that are created during the execution of the initializer and that may be used later on during the execution of the binary have to be serialized and included during the snapshot phase. And the snapshot poses or reforms another input into the analysis because types that have not been seen in the code but are part of the allocated object graphs have to be considered as instantiated as well when running the analysis. Unfortunately, using points-to analysis in every build can be quite time-consuming. For instance, analyzing Spring Pet Clinic, which is a popular demo application of the Spring framework, can take up to 160 seconds. It might not sound like a lot for a static analysis method, but it is important to consider that this analysis is run during every build. So every time any developer wants to compile something using native image, this amount of time has to be invested into it. Therefore, we were looking for another alternative, cheaper analysis that would provide similar results with similar precision, but take less time. And the criteria we considered were, of course, scalability, then reasonable precision, because one must consider that we cannot simply include everything and mark everything as reachable, because it would increase the threshold, not the threshold, but the workload on the compilation phase afterwards. So any savings in the analysis could be outweighed by a more expensive compilation afterwards. On top of that, the analysis method has to properly interact with all features of native image, such as heap snapshotting. And lastly, we were also aiming for a method that could be incremental, so that the results from previous compilation can be reused in the subsequent runs. There is a plethora of methods of call graph construction, ranging from simple ones, such as unique name analysis, which considers only the name of the method when determining the callees, or class hierarchy analysis, which also uses the subtyping rules or class hierarchy rules, or rapid type analysis, which combines the class hierarchy along with the information about which types have been instantiated. And lastly, control flow analysis, which is very similar to what we have at the moment and what we call points-to analysis. After careful examination, we decided to implement a prototype using rapid type analysis, which we believe offers a good trade-off between precision and scalability. To give you an intuition into how rapid type analysis work, we will formalize it using 3 equations that compute 2 sets, R and I. R stands for reachable methods, and I for instantiated types. The first rule is very straightforward. It simply says that the main method, or in fact any set of entry points, is already included into R, and it starts the computation. The second rule is more complex, so we will go through it step by step. For each reachable virtual invoke in each reachable method, we take its type E, or rather we take the static type of the expression E on which the method is invoked, and we traverse all instantiated subtypes of the type. In this case, the declaring type is A, which is instantiated, and therefore we consider the method F as reachable. Its subtype B is not instantiated, so we will not consider its implementation of F. And its subtype C, again, is instantiated, and therefore we will consider it. The third rule is again quite straightforward. It simply says that in each reachable method, we have to mark each instantiated type as instantiated. Rapid type analysis has already been studied in the past, so let us now clearly distinguish what is the state of the art and what is the contribution of this paper. First of all, we designed an extension of rapid type analysis that is suited for the context of native image, meaning it can interact with heap snapshotting and it provides all the necessary information for the compilation phase afterwards. And therefore, it can work as a replacement or rather alternative mode for the points to analysis, which is used at the moment. Then we extended the basic algorithm to be parallel and incremental. The incrementality was achieved using concept of method summaries, which I will discuss more in the future. And lastly, we performed an experimental evaluation comparing rapid type analysis with points to analysis in the context of GraalVM native image. Let me now describe the core algorithm of RTA, including our extensions. It starts with a set of root methods that we mark reachable, and then for each reachable method, we parse it into its intermediate representation from which the summary can be extracted. Afterwards, the summary is processed and the state of the analysis is updated using a set of register methods that are called for each interesting element. Once a given method is made reachable, the decision is never reverted, which means that eventually a fixed point has to be reached and the analysis terminates. The core idea is now presented in pseudocode or the slide. I would like to draw your attention to the lines 4 and 5, because each register method actually starts with an atomic check that succeeds only on the first time, which ensures that even if multiple threads try to perform the same operation, only one of them succeeds, and it ensures that there is no reduced work. And on the slide 5, we can see that the actual work, or rather any bigger piece of work, is not done immediately, but rather scheduled as a separate task, which ensures that the analysis essentially works as a very parallel application that runs in a thread pool. Let me now proceed to the summaries. These summaries are rather straightforward. They consider the following information, from which I would like to highlight, for example, directly invoked method, virtually invoked methods, and instantiated types. And they can be easily extracted by a linear pass over the intermediate representation. Let me now proceed to the more tricky part of RTA, which is resolving virtual methods. First of all, the method itself is registered as invoked on its declaring type. The reason for that will be explained on the next slide. And then the actual subtyping, or rather all the instantiated subtypes are processed, and the method M is resolved on them using the resolve method actually performs virtual method dispatch based on the specification of Java. The other side of coin is registering new type as instantiated. Again, all the methods I mentioned start with the atomic check, which prevent from the reduced work. Then the type hierarchy is traversed upwards, and the type T is registered as instantiated in all its supertypes. Then the supertypes hierarchy is traversed again, but this time we are looking for all methods that are registered as virtually invoked in all the supertypes. But now please take attention to the line 7, because the resolution always starts from the type T, not from the supertype. So coming to the example on the right, Suppose the type C has been marked as instantiated, and it already has method f registered as virtually invoked. We will therefore perform the resolution of the method f on the type C, which will result in f, and we will mark it, we register it for further processing. Then we traverse the hierarchy upwards. In this case, we are looking both for instantiated and non-instantiated types. So we are truly traversing all supertypes of the type. And suppose type B has method G registered as virtually invoked. We will again perform the resolution via the type C, which will give us the implementation in B. So we will register it as invoked. Then we go to the supertype A. And here it gets a little bit more interesting, because when we resolve its method f using the type C, of course we will get the one coming from the type C. And therefore we will not mark the one coming from the type A, which would be imprecise, unnecessary in this case, because there is no way the method f on type A can be instantiated in this case. Let us now run the analysis on a simple example. Suppose we start from the method main, which instantiates type hello and A, virtually calls method foo, and directly calls method lock. When we see the direct invoke of method lock, we can immediately register as invoked, because it is direct, of course. And when processing the virtual invoke foo, we have to consider all instantiated subtypes of the type hello, which in this case is only hello itself. Therefore, we resolve the method into hello.foo. When processing method lock, we only mark type B as instantiated, and then we proceed to the method foo, which accepts an interface type I as a parameter. And in this case, we have to consider all instantiated subtypes of the interface I, which in this case is both A and B. And therefore, we end up marking both A.bar and B.bar as possibly invoked and have to process them as well, which is a slight imprecision compared to points to analysis, which would determine the callees more precisely in this case. But at the same time, it would also need to create more complex internal representation to actually perform the analysis compared to a few simple summaries. Let me now proceed to the incremental part. The summaries contain mainly classes, methods, and fields, which are not so difficult to serialize, because for classes, we can simply use the fully qualified name. For methods, we can use a combination of the class name, method name, and signature. And for fields, we can use, again, class and name. Unfortunately, there are some constraints that have to be considered. First of all, not all method names are stable in Java, especially the generated classes that are created for lambdas, for example, are unstable. Their name changes from one compilation to another, which poses a problem. And lambdas are not the only example of this behavior. Then, at the moment, we only support so-called trivial embedded constants, meaning primitives or well-known types, such as Java lang string, because we know that traversing, let's say, the transitive closure of all the objects starting from string will always give us the same set of instantiated types. So it's not necessary to consider them in the summary. Unfortunately, the incremental part has a significant problem when it comes to side effects during parsing, because unfortunately, parsing a method in GraalVM native image is not a pure function. It modifies a lot of state, and it can also even mark more methods as reachable, which is rather unfortunate, but at the same time, it is not an artifact of the analysis itself, but rather of the compilation environment, and might be eventually lifted during the effort of making the whole native image more deterministic. And the second issue is that summaries contain quite often non-trivial constants, meaning other types, and this restriction might possibly be lifted in the future. I have some ideas about that there was just not enough time to implement them. Let me now proceed to the experimental evaluation. We've performed experiments using the standard suites Renaissance and DaCapo, and apart from that, we've also analyzed several microservice applications from the most popular Java frameworks, Micronaut, PetClinic, and Quarkus. And you can note, for example, that for Spring PetClinic, we've managed to reduce the analysis time by 64%, and the total time by 35%, of course at the cost of increasing the binary slightly and making more methods reachable. Similarly, we've reduced the analysis time for most microservices, but at the same time, if you take a look at the first line, simple Hello World application, the analysis time and the total time increased. And the result for that is that for smaller applications, the imprecision of RTA and the extra work that has to be performed for those methods that are marked as reachable only for rapid type analysis actually outweighs the benefits of simpler analysis. Then we've also experimented with different number of cores to inspect the scalability of the analysis. And now I would like to draw your attention to the scenario with 1 or 4 threads for PTA and RTA, because in those scenarios, RTA performed even better, which suggests that it might be a good candidate in environments with restricted number of threads, such as GitHub Actions or some continuous integration pipelines. To conclude the presentation, we designed an extension of rapid type analysis for the context of GraalVM native image. We extended the proposed algorithm to be parallel and incremental, which we achieved using the concept of method summaries. We've performed extensive evaluation, and for example, for Spring Pet Clinic, we reduced the we reduced the analysis time by 64%. And as the next step, we would like to work more on the incremental part and also on a combination of points to analysis with rapid type analysis, which should possibly outperform both alone. That's all from my side. Thank you for your attention.
Do we have questions? So while you warm up, maybe the obvious question, how would a combination of the two look like?
Well, we haven't really published it yet, so I'm not sure how much I can talk about it. But let's say that in certain parts, when the amount of type in points to analysis exceeds a certain threshold, it doesn't really make that much sense to track it more precisely. I would stop at that because we are actually actively writing another paper where we describe this.
All right. Any other questions for David?
I'll make the other obvious question, which is, what's the work on making this incremental?
Can you repeat, please?
So one of the next steps would be incremental support.
Well, as I mentioned, there are 2 issues with incrementality. First of all, the side effects, which is rather a lot of engineering work. And the second part would be actually to include non-trivial constants or non-trivial embedded constants into the summaries, which could be possibly done by either traversing the subgraphs of those constants and simply including all the instantiated types in those objects into the summary itself, or alternatively, but that would require more engineering work, to actually track the decisions when it comes to inlining field accesses and kind of determine where this constant came from. So instead of including the subgraph into the summary, you could say that this summary contains a constant that should be available from this static field in a given class after its initialization. And you can then replay the same thing in the next compilation.
Thank you.
All right. Let's thank David one more time. Our next speaker is Juan, and he is going to talk about unified shared memory, understanding the implications of it on managed heaps.
I missed the configuration again. Before, huh? Yeah. Let's see. No, it's good. Okay, hello everyone. My name is Juan. I'm from the University of Manchester. This work is a collaboration with Intel. We did this project for a few years. And it's also based on one of our students back then, Florin. Florin did the master's student and then initiated this work. And when we took it further and tried to generalize it. So what is about? What is all this about? So what we focus is in Java. Okay, we focus on Java, but could be any other managed runtime programming language, and GPU FPGA programmability. So we are talking about in a heterogeneous environment, okay, with accelerators. So what do we do? Well, to try to bypass some issues, I'm going to explain what those issues are in a bit. What we did was to allocate the Java heap in unified memory in such a way that the Java virtual machine has the knowledge of pointers being moved or data transfer being transferred to the actual GPU. And the GPU has the knowledge of the CPU claiming that memory back. Why do we do this? Well, I'm going to tell you now. So I'm going to start by the motivation first, and then I'm going to talk about some background. I'm not going to assume GPU programming, so I'm going to tell you basic terms to understand the rest of the presentation. And then I'm going to focus on the main technique that we discussed in the paper, and the evaluation, of course. So we focus on heap data, okay? There are other alternatives, especially for GPU programming, in which data is off heap. We focus on heap data. Why is that? Because we don't want to expose another API to the user to learn this API, and that requires more changes, essentially. So we want to make it as easy as possible for the programmer. What happens with on-heap data is that, I will expand in a bit later, but essentially we need to pre-allocate data on the GPU, we need to do the transfer, we need to run the kernel and claim that data back. But what if the GPU is running with data that the GC might need, right? In that case, we get a crash, we get a seg fault. This is more common than you might think. For example, frameworks like GCL has it, Aparapi is an AMD product, they have it, and Tornado VM also has this problem. So what people usually do, or developers do off heap. But no, I want to stay on heap. Can we do something better? Well, another reason is that to avoid these crashes, what we do, especially in the case of Tornado as well, in Aparapi as well, they lock the GC. So run on the GPU, the GC is locked, and then I'm happy because the GC cannot do anything else. But this is, for many customers, this is kind of, no, I don't want to do that, because you never know the amount of time that the GPU is running. Could be a couple of seconds, could be a couple of months, right? Right, so what do? We do unified memory. That's a special type of memory that the CPU and the GPU can see together. It's actually a virtual address space that those systems have in common. And we prototype in the context of Maxim VM, and we use two programming models underneath. We use CUDA, which is a programming model and a programming environment developed by NVIDIA for NVIDIA GPUs that work only for NVIDIA GPUs, discrete GPUs, I mean, GPUs are not, that don't share memory. And then for the integrated GPU, we did it in the context of Intel Level 0. Intel Level 0 is a new API packaged under the One API umbrella. I don't know how familiar you are with these terms, but in a sense, it's a very low-level API, quite close to the driver, to manage heterogeneous execution, to allocate memory on the GPU, launch kernels, add events, et cetera, et cetera. So let's talk about some background. I think in this room, many of you know Maxim VM was a project initiated by Sun Microsystems back then, and then Oracle Labs took it. And if you're curious, so the actual JIT compiler of Maxim VM became Graal later on. And we, in Manchester, University of Manchester, we actually maintain and extend it. I think Orionas gave a talk before about this as well. So the one thing to notice is that the Maxim VM uses a very simple garbage collector. It's called semi-space GC. Basically, the space is divided into two, and every time there is a GC, it's a full GC moving pointers of data from one space to another. In that case, in our view, for our study, this is the worst case scenario, okay? So what I'm gonna see is actually the worst case scenario for the GPU execution. So let's talk about the GPU part. So as I say, unified memory is a single virtual address space that has the same view for all CPUs and GPUs in the system, right? So you can claim any memory from any device, any GPU or any CPU. That doesn't mean that it's using the same memory. It might be or it might not be, depending on the device. So to give you an overview, if you use a discrete GPU, the one on the right-hand side, the discrete GPU has their own memory, and it's actually good to use it because the bandwidth is very high. It's usually 10 times higher than the CPU memory bandwidth. And if you are working with integrated GPUs, that means that the GPU resides inside the CPU, you are going to use the same system memory. So how is the unified memory working here? So let's imagine that you have a discrete GPU, and you have data already allocated on the CPU. So when you have unified memory, the first thing to do is that the GPU wants to access a page on the GPU that says, this page is not present in my GPU memory. So page fault, that's part of the driver work. And then the GPU will allocate a new page or new pages on the GPU. It will unmap the old pages on the CPU and will do data migration. So data will be migrated from the CPU to the GPU automatically. This is part of the driver work. And then we'll free the old pages on the CPU. You can imagine the same process claiming back. So if this GPU is running, but the CPU claims back this memory, the process is the same, but reverse order, right? Right, what happens if you have integrated GPUs? Well, the thing that you transfer data is gone because it's using the same memory, actually. And that's why we study these two systems and see the impact on these two systems. You might have page fault, of course, but there is no actual memory or page migration. Okay, with that out of the way, what we did was, okay, let's allocate the Java heap. So Java heap is a map operation in Maxim VM with the equivalent call for Maxim VM. So before jumping into that, I'm gonna tell you one more thing about how is the GPU workflow if you are programming with Java, okay, from the Java perspective. So as I mentioned earlier, you allocate your data, you have your new data structure, new float, arrays, doubles, whatever. Then you have to pre-allocate, this is actually the developer's work, pre-allocate the buffers on the GPU, send data, launch your kernel, be lucky that the GC doesn't kick in, and then get the data back, okay? Unless the data is off heap, of course, it's something different. When we have unified memory, you do your new allocation, you directly launch your kernels, and the GPU driver will take off migration if necessary, and then you claim your data back. So the workflow is simplified, right? So let's do that. We simplify, we say, wherever this mmap operation in Maxim VM, we have the equivalent call for CUDA or Intel level 0. Well, it's not that simple, I wish. There are a few issues with this. First of all, so Maxim VM, the VM, okay, allocates the Java heap at bootstrap. And this part, the application code is not even seen, right? They are kind of disjoint. Even though it's the same process, it's kind of disjoint. Furthermore, the user application, because are accessing the same heap area and can launch kernels using data on that area, might need, or actually have to, share pointers with the VM, because this is disjoint. What kind of pointers are we talking about? Well, the VM needs to access the platform pointer, the device pointer, the command queue. Those are data structures specific for GPUs, right? But essentially, it's like, you know, it's a pointer that you can send, okay, send this request to the GPU, add this event to the GPU, etc. And those exact events need to be consumed from the client. So this needs to be shared. The second issue, though, is that, well, we talk about a shared resource. And because it's shared, you might have into troubles regarding race conditions. So again, we have to lock the GC. Although we now lock for different reasons, just to keep consistency. Not because it's a seg fault, but we have to do that. So I'm going to expand quite a lot on the first issue. The second issue, what we did was to extend the garbage collector on Maxim VM and include a synchronization point within the VM. So the user doesn't have to worry about these kind of things. Obviously, this has a cost, and I will expand later on this. But what do we do about the first part about sharing all these pointers? Well, we come up with this XPU interface. We call it XPU. It's a fancy name. It could be GPU, FPGA, whatever you want to call it, accelerator, AI accelerator, etc. This interface is common between the VM itself at the bootstrap and the user application. So the user application can consume these values. Give me the driver pointer for heap 0, give me the device pointer for heap 0, give me the context for heap 0, and so on and so forth. Depending on the programming model that you use, if you use CUDA, you don't need all of it, because CUDA, because it's a specific only for NVIDIA GPUs, you might not need, for example, the device pointer, because it's already one, you got it. Unless you have many devices, of course. Or the command queue. The equivalent for CUDA is called the streams. But anyway, those are implementation details. But level 0 is more generalized programming model, as well as OpenCL. And in those cases, you need all of it. Right, so I'm going to give you an example in the case of level 0 because it's more generalized, okay, it's generic. This is the kind of the workflow of an application written with Maxim VM and this unified memory. So offline, what the user does is to send those kernels. We already assume that the kernels are built. And the kernels are in SPV format. I'm not going to go into the details of the SPV, but it's a portable intermediate representation, right? It's like a standard IR for GPUs, FPGAs, etc. You can get the SPV through, for example, LLVM. Okay, there's a path called LLVM SPV, and you can get that code. And that's the function that runs on the GPU. So the user does that, and then the user in the application code get access to the device pointer, the context, the command list, because you need those to launch the kernel. And you need exactly those pointers, right? So that's how we do it. Right. And what we did after these two implementations, we have one implementation for CUDA, one implementation for Intel Level 0, we analyzed different cases and scenarios. And we divide into 3. And we try to kind of get the worst and the best and something in between, right? Actually, there are 2 of the worst and something in between. But we come up with this, it's called allocate always. What does it mean is we're going to evaluate this application running multiple times, sending data back and forth between the GPU and the GC might kick in or not. In the allocate always, what we do is we do the new of our data structures, new float array or double array, whatever it is, and then we call the GPU to run the kernel. What happens is that because it's the first time that the data is there, the GPU, when it's going to run, is going to force page migration. And that's the case that we want to trigger. The second case, and it's the main purpose of this paper is, what if in between I call the GC? That's what we call allocate once. So we only allocate once, but in between runs, I'm going to go to the GPU, and then when I go back, instead of claiming data, I'm going to call the GC immediately. Okay, that works, but has some penalties. We will discuss it later. And as I say, this is because we run several times. So we are continuously running. And the last case is the allocation once with no GC. We put this because this is the usual case when you program GPUs and FPGAs. So you have your data, and you just run once, and then you move on. And in this case, it will trigger page migration, but because we want to measure in peak performance, you are not going to see the effects of page migration, right? But it's still there, it's in the first iteration. So what do we do? Let's try to analyze this. And the first question is, well, I have this unified memory in place for the GPU programming part, but did I break something on the CPU? Let's try to measure it. So what we did was to run on pure CPUs. There is nothing on acceleration here, and try to see if there is any benefit or any penalty. So we ran Renaissance benchmarks and Da Capo for the 2 systems, a discrete GPU and an integrated GPU. The key message here, as takeaway, level 0 with integrated GPUs usually performs slightly better. That's because there is no page migration. And in the case of CUDA, there are some cases of penalty. For example, the ACA that you also saw in Oriona's paper, actually when Oriona was writing the thesis. And this is because of a non-uniform distributed pattern in memory. And that, for some reason, that's implementation detail on the driver side, in my opinion. It goes, speed ups go down. Ideally, it should be 1, should be the same as baseline, okay? Key message, if we take the actual average of those, it's close to the baseline. So you can say there is no significant penalty, right? Indeed, as we discuss later, in the case of integrated GPUs, it's actually beneficial. Okay, what about GPUs? It's a complex graph, but let's try to summarize the key points. So we run with a different set of benchmarks, okay? Those are quite data transfer intensive, if you like, okay? Something in between, kind of mixed data transfer with a bit of compute, and then compute intensive on the right-hand side. And there are the 3 modes that we discussed, right? So let's start with the obvious one, the red, which is the I allocate once, and I run on the GPU. We see that there are some speedups. The baseline now is pure GPU programming, as you will do in any other GPU program whatsoever, even in C++, right? We took it in Java, but which is, I allocate my buffer and send everything, I compute, and I get back. So we see some benefits, but those benefits is because we don't claim data back after it runs, right? Otherwise, it will trigger page migration, and it should be exactly the same as baseline. But since we don't claim it back, it's there. Then for the rest, it should be, we see, it should be exactly the same as the baseline, but page migration has a cost, okay? You can trigger a page fault from any thread, and on the GPU, you don't run 10 threads, you don't run 20 threads, you run usually a few thousand threads on the GPU. So imagine a few thousand threads triggering page fault. It's gonna be a bit of penalty, and that's what we see there. That's in the case of discrete GPUs, and if we move to the integrated GPUs, we see a slightly different story here. In general, there is no penalty here, which is good. And in some cases, like allocation, continuous allocation and migration, this is beneficial when we use shared memory. I did some experiments myself as well. Even in C++, we can reproduce this thing. Using shared memory on integrated GPUs has actually beneficial here. And in the case of some slowdown that we see is because in the baseline, we use device memory. That's how you should use it, because device memory can give you higher bandwidth. But in shared memory systems, it's actually shared memory, right? And that's why we see some slowdowns. But in general, we don't see penalties here. Then what we measure is the system.gc call. So essentially, I know you're running on the GPU, but I'm gonna force myself system.gc. Is any penalty? Well, for CUDA, which is the one on the left, we see a penalty of up to 2x, 2.1x, and that depends on your heap size, right? The larger your heap, the more penalty you have because you have to migrate more data. That makes sense. So there's no workaround. Well, actually, yes, there's some workaround. We didn't use it. You can do prefetch. So you can do kind of tricks on the GPU side to do, prefetch this amount of pages, for example, and you can increase some speed up. And that's actually convenient. It's actually in the guidelines of NVIDIA. But we measured the worst case scenario. If we took the same baseline for the integrated GPUs, the one on the right, we actually don't see any penalty. There are some variations, but keep in mind this driver inside, although we run multiple times, we measure multiple times the driver inside that keeps these page faults, etc. I wouldn't claim this beneficial or it's a slowdown. I would say it's the same as baseline. So we run same speed as baseline, essentially, which is good. Right. So what we try to do then is to move this forward and analyze, okay, it seems like for integrated GPUs this makes sense, this strategy makes sense. So what we do is to contact the level 0 community and level 0 spec to see how this could be integrated. Well, it's not that simple because you need to share files, actually. We did a kind of a trick with the equivalent to malloc, let's say, but Java in reality uses share files. Anyway, we claimed this to the spec, we actually put an issue to the spec in order this to be done, and we are working with that. I'm going to close here the presentation. Feel free to ask me later if you have questions. But in conclusions, what I show you is a technique in which both the CPU and the GPU can work together, and more importantly, they can manage on-heap data without segfaults and without crashes, at the cost of performance in some devices. For example, dedicated GPUs, like NVIDIA GPUs. And we introduced this XPU interface in order to talk to each other. And we also include the synchronization point at the GC level for doing everything automatically and keep consistency. With that, I conclude my presentation, and thank you. Questions? Yeah, go ahead.
Who got a question for one? So a simple warm-up question. Can I just run my stupid Java code on the GPU? Probably not.
You mean offloading Java?
Yeah, I mean, how much care do I have to take to write perfectly GPU code to get any benefit?
Right, so yeah, a couple of things. So this work is not about offloading, yes?
Yeah, yeah.
That's Tornado, for example. So we offload, in the case of Tornado, a subset of Java. Makes sense for data para applications, big data workloads, this kind of stuff. Even in Java, you can get benefits. Now, even if it's big data or data para applications, you have to have a big amount of data in order to get benefit. Don't go to a GPU with less like 100 threads, but at least 1,000 threads.
Do I have to turn all my data into arrays, or can I use my objects?
Well, in the case of Tornado, there are some data structures that you can use, primitive arrays, for example, and some data structures, like some objects. The objects that Tornado has knows the layout. Same with Aparapi as well. Okay. That's in general. Aparapi can offload some POJOs, like plain object arrays. That kind of things will work. And Tornado can as well with the parse escape analysis in Graal. But in general, I would say in general, no, because that has some trade-offs. Right. For example, introducing unnecessary control flow, this kind of stuff on GPUs. That they work really, really different on than CPU systems. GPUs are more for like high throughput systems, while CPUs are for low latency systems. So if you know these limitations, I'm pretty sure you can represent your data structures with simpler ways. Although, yeah, that's a trade-off we're trying to achieve. Yeah, right. Good question.
So just a quick question. You said the limitation on existing systems is that they have to lock the GC during the point at which you're going to share. That's true even in your system, right? Because you have a semi-system, and it's because the reason is because you have a semi-space collector.
I wouldn't say it's because of semi-space collector. Well, as soon as the GC can move pointers, you have that. It doesn't matter if it's semi-space, right?
Well,
like, makes sense?
In principle, it seems like there's no reason why you couldn't have a flag set on an object that says, hey,
exactly.
Move me if you have a non-semi-space collector,
exactly.
right? If you have
we discussed exactly that in the paper. Yes, you're right.
Okay.
Yeah.
So it's really ultimately it's the fact that the GC can move objects, and in the case of Maxime, because it has a semi-space collector, it has to move objects.
Sorry, I didn't want to claim that it's because of the semi-space. I say that Maxime uses semi-space, so we kind of analyze the worst case scenario, in my view. I'm not an expert on GC, by the way, but that's my view here.
Okay.
Just to be clear.
Yeah, it wasn't. I was confused by this like statement that you have to lock the GC, and I was like, do you?
Yeah, as soon as the GC can move pointers, and those pointers are used by the GPU, yes, you have to lock it. Otherwise, you might get, unless the GC, the heap is huge, you might get segfaults. And indeed, you get segfaults in Tornado and Aparapi if you don't do that.
So when you're faulting because you're having an access from a page in GPU memory and in CPU sufficiently close.
Well, I should explain. So usually you have a backup data, if you like. You have your CPU array, CPU memory, and your backup on the GPU. They don't talk. It's not the same one. Right? You migrate data, but the GPU is expected to put data on the same place that you had before. But the problem is that the one you had before doesn't exist. It's on the wild. Does it make sense? Because it was moved by GC.
Right, okay. This is about like the automatic migration of...
The automatic migration, both systems know, my data was moved. I have to move as well. They can work together, so you get rid of the problem.
The seg faults don't happen in automatic migrations.
Don't happen.
All right.
Yeah, exactly. Yeah.
Okay, one last quick question.
So it's a very quick question. So what happens if you apply this technique to such kind of like a big large language models like Llama or GPT or such kind of? So.
Sorry, I didn't get the question. Sorry, can you repeat, please?
So I would like to know the applicability of your technique to the large language models like Llama or another kind, Robot or another kind of stuff.
Can you rephrase it?
So,
let's take it.
Let's take it offline.
Okay.
Yeah. No, sorry. The thing is, it's a bit hard to hear from
okay.
Because I was there and was here.
Okay, let's talk.
Yeah, let's talk later. Yeah.
Thank you.
Yes.
Chris, thanks. So our next speaker is Christos, and his talk is titled Beyond RSS Towards Intelligent Dynamic Memory Management.
So, hello everyone. I am Christos. I am a PhD student at the National Technical University of Athens in Greece. And today I have the pleasure to talk to you about our ongoing work on improving dynamic memory management. But first, let me elaborate on the three title segments to clarify our paper's theme as much as possible. I shall focus on the concepts and points of practical interest and refrain from technical details. If it sparks your curiosity, please feel free to check the full text. Let's start with dynamic memory management. Of course, we are referring to the malloc family of functions. Programs need to allocate memory during runtime, the simplest example being a growing array. They request it from malloc, stating the exact number of bytes needed. When they are done working with it, they free previously allocated memory via a second request, and the allocators satisfy such request through managing a region called the heap. In practice, we may have multiple heaps, but the first principles remain the same. So allocators live in virtual memory. When and where it will get mapped is beyond their control. What is in their control are the virtual addresses of allocated objects, the sizes of those objects. Over-allocation may happen for alignment or other purposes, and internal data structures used for bookkeeping. Again, when and to what extent an allocator's actions bubble up to the physical realm depends on the behavior of the program. That is, its patterns with respect to allocation and deallocation, as well as memory accesses and the state of the host system. If it's not clear by now, we are talking about operating systems that have paging like Linux. So malloc is not invoked only in the context of manual memory management, where programmers are responsible for calling it. There are runtimes such as Python and Rust that do invoke it under the hood, and while they may reserve memory in large chunks and manage it internally, the ubiquity of the malloc family cannot be downplayed that much. This ubiquity has attracted tons of research, balancing the trade-off between response time, consumed memory, dealing with concurrent execution, hardening the heap against exploitation attacks. These questions have long been investigated by allocator designers. Today, however, I want to draw your attention exclusively to the topic of memory consumption, because dynamic memory managers must obviously manage memory well, and if the nature of their work is virtual and the transmutation of their actions to real costs so complex, how can we know what good memory management looks like? And most importantly, are there any clues out there that hint towards the need for better allocators in terms of memory consumption? So it's time to talk about fragmentation. Fragmentation is historically the term for referring to bad memory management. Fragmented memory is available, but not in contiguous form. One reason to pursue contiguity today is huge page allocation, since TLB misses have been identified as a major performance bottleneck and the default granularity of 4 kilobytes pages as its cause. So allocating larger pages drastically decreases the probability of TLB misses. A recent paper studying physical memory contiguity in Meta's data centers yielded a surprising insight. Searching for as little as 2 megabytes of contiguous memory has a 23% chance of failing, and increasing this size to 32 megabytes corresponds to a 60% chance of failure, while finding gigabyte scale regions is practically impossible. From a pragmatic point of view, then, physical memory is the metric of interest. Contiguous physical memory is of the essence in modern massively shared systems, and yet it is extremely scarce. Who should we consider responsible? The paper goes on to identify unmovable allocations as the culprit, that is, virtual pages pinned to specific physical addresses that cannot be moved around by the kernel. These are different than the unmovable allocations performed by malloc, which are pinned only in the virtual sense. We posit, however, that such scarcity could to a large extent be caused by malloc, since absence of physical contiguity equals overpopulation by mapped virtual pages. Allocator performance with respect to memory consumption is inversely proportional to the total number of pages that it reserves from the OS. In an ideal world, where for each workload the minimum number of pages was reserved, systems would have considerably more leeway for optimization via huge page allocation, compaction, etc. So to summarize our motivation, fragmentation is a real problem. It is born in the individual workload level through allocator actions on virtual memory. It has the potential to affect whole systems through complex interactions beyond the allocator's control. And our research question is, what does fragmentation look like as viewed by the eyes of malloc? Our paper's title urges us to search beyond RSS for the answer. Virtual space inhabiting creatures like malloc may only be assisted with a virtual space inhabiting definition of fragmentation. Let's quickly go through the term's history. We start with the seminal survey on the subject 30 years ago. The authors admit that fragmentation is poorly defined and that mainly has to do with its dependence on future program behavior. 3 years later, fragmentation is not only considered defined, with 4 definitions proposed and 2 evaluated, but also solved. The authors do restrain themselves in virtual memory this time. They use trace-based simulation to make the future known. And the basic components of all proposed definitions are ratios of heap size to memory requested by the application across time. Then, the authors of the horde allocator picked one of the 4 definitions proposed in the 98 paper and measured it also in a trace-based manner. Paradoxically, despite it being thought solved, fragmentation could be excessive and harm performance as well. The same process was followed in 2002, where the effects of tailoring allocation to workload-specific behavior were deemed unclear. The creator of JE malloc was the first to bring us full circle on the question of fragmentation definitions, and also the first to note that RSS numbers are not to be trusted, since they are sensitive to an allocator's own implementation. He also resorted to trace-based analysis focusing on virtual memory, bypassing, however, the requested amounts and measuring heap size only. Finally, recent experiments on Google's fleet deemed existing fragmentation definitions inadequate and proposed a new one. Note that the authors interpreted memory requested by the application as mapped memory, thus unconsciously breaking the tradition of focusing on virtual space. By the way, feel free to search the internet for blog posts allegedly dealing with fragmentation, and you will notice, I'm sorry for this, you will see a habit of misjudging RSS fluctuations as indicators of increased or decreased fragmentation. What are we to make of all this? First, trace-based methods focusing on virtual memory are the way to go. Second, a single definition on that substrate must be found. Third, a link between said definition and RSS must be made, since RSS is what practitioners care about. Fourth, we are not there yet. To reach that point, we must focus on the facts. Fragmentation is completely defined by the interaction between a workload and an allocator. No malloc implementation could optimally handle all possible workloads. To chase that optimality, allocators should adapt to each workload and predict its future behavior. Most allocators today do not support such adaptiveness. Recent works, however, have taken this direction. Last but not least, the resulting fragmentation is not always important in the sense of it impacting RSS. The simplest example is a workload that never accesses allocated memory, thus never triggering paging. Allocator selection would not matter then. In other words, workloads demonstrate varying degrees of sensitivity to fragmentation. And it is this sensitivity that our paper introduces and investigates. Its value is multifaceted. The simplest one is workload characterization. A rather strange fact of allocator design is that no standardized benchmark exists. We attribute this to a lack of systematic methods for answering the question, would this be a good benchmark for malloc? Another interesting direction would be using what we propose as a basis for learning workload-specific policies for cases known to be sensitive. We now enter the presentation's last part, where we make our methodology explicit. An elegant way to capture workload allocator interaction is two-dimensional rectangle packing. This formulation has been used in the context of ML compilation, where all future requests are known. We claim that its benefits can be extended to the general dynamic case. The packing space has virtual addresses on one axis and time on the other. This figure holds a packing for a simple request series as served by some hypothetical allocator. White rectangles are live objects. Colored areas amount to sources in red, to sources of fragmentation, either in the form of gaps between objects. In red, we see external fragmentation, or of overallocated sizes, in purple or internal fragmentation. Our final metric of fragmentation divides the sum of colored areas to the total area of live objects. Using these tools, we made trace-based experiments across many real workloads, measured each pair's memory footprint and fragmentation, and did correlation-based hypothesis testing on the resulting data. If our rationale is correct, then we expect to see workloads exhibiting positive correlation between peak RSS and either internal, external, or both fragmentation types. This bar graph summarizes our result. Each pair of bars denotes a separate workload, with the left bar marking external and the right internal fragmentation. Bar heights denote Spearman correlation strength. The null hypothesis states that no correlation exists between peak RSS and fragmentation. Red bars confirm this null hypothesis, and all the other colors negate it in varying levels of confidence, the lowest being 99%. Only in two cases does neither type of fragmentation correlate with memory footprint. The rest validate the intuition built up to this point. Purple bars, however, stand for interesting exceptions of negative correlation. This being a work in progress, we have not had time to investigate them. All in all, we have argued that fragmentation persists as a problem and its roots are to be found in virtual memory. We have proposed bin packing as an adequate representation of capturing workload allocator interaction and measuring fragmentation, leading us to the notion of sensitivity. This notion could pave the way for informed dynamic memory management benchmark suits, as well as custom allocators targeting sensitive workloads. The theoretical limits of such custom strategies have been investigated in a related paper of ours. We consider, all in all, demystifying fragmentation as a necessary first step towards a complete theory and practice of dynamic memory management, which would unlock further overall system performance improvements. With that, I would like to thank you for your attention, and I'm happy to address any questions.
Do we have any questions? Okay, maybe, yeah.
So one thing I've noticed about this that continues to confuse me, allocators generally are grabbing space from the operating system in units of pages. So I don't quite understand why you never round up the last page, because that is wasted space. Nobody else is going to use it.
About the top of each page, if it stays unallocated, you mean?
Right. That should be considered part of the fragmentation, at least intuitively to me.
But if we wanted to, yeah, the specific allocator didn't do it, but we could allocate an object on the top of that page, which would be contiguous with another page on top of it, right? It's not a fixed size gap at the top of the page. It's unbounded, I suppose, since virtual space can be mapped in non-contiguous physical space.
Maybe we're talking at cross purposes. I'm just saying, you know, there's going to be a virtual map, and if there are 10 pages there and I haven't used the last bit of the last page, it's still, you know, that's wasted space. So I don't know why you cut off the accounting at the end of the last object instead of the end of the last page. But
the question is about the definition of fragmentation,
yes,
right? As how we define it.
I grasp that. It's not intuitive to me. We can talk more later.
Good.
Yeah,
Okay.
let's take that offline in the interest of time. Thank you very much.
Thank you.
JT? There. So next speaker is JT, and his talk is titled Towards Safe HPC, Productivity and Performance via Rust Interfaces for Distributed C++ Actor Library.
No? Okay. No, I can't see it though. Sorry. It was working earlier. Have you got it now? No? Yeah. Here, I can do that.
Yes, I'm seeing something.
Okay, that will work.
When you present, I'll swap, or would it be swap now?
You swap it now, yeah.
I swap.
Okay. Sorry about that. Okay, so yeah, this work I did as part of my master's research, and I'm happy to be able to present it on behalf of all the authors listed there. So the motivation for this work, right? So in the HPC space, there's a lot of people who are not computer scientists and also computer scientists that you know, maybe could do with not spending as much time dealing with seg faults and all the lovely parts of C and C++. So our idea kind of is to allow those people, domain scientists and, you know, programmers, I have trouble with seg faults, cut down on debug time and prevent sort of more costly runtime errors. And so Rust is a programming language that's been adopted in lots of domains now, and there's lots of nice, like, multi-threaded, sort of performance-focused libraries written for Rust. But there's been a lot less exploration of Rust for sort of distributed memory HPC libraries. And so the goal of this is kind of to develop safe Rust interfaces for HPC distributed memory actors library. And I'll talk a little bit more about what that might mean. And so the background of this is there's a previous work by the Habanero Research Group at Georgia Tech, previously Rice. The HClib actor library is a high-performance computing distributed, built on top of PGAS, OpenSHMEM library, intended to provide an actor-based, so like active messaging between different PEs, abstraction for you to write your applications, and it's delivered performance improvements of greater than 20 times. So it's worked really well in C and C++, and the purpose of this research was to kind of see, you know, let's kind of wrap it, rewrite some of it in Rust, and see if we can get the same thing while providing safety, memory safety. Just a recap on Rust and kind of what the Rust programming language is all about. So it wants to provide memory safety, but with escape hatches, and I'll talk about what that means. So by default, Rust only compiles code that it can verify to be memory safe. So it prevents things like use after free and accessing uninitialized memory. And it also enforces single ownership, so it likes to have an idea of who owns an object. So you can have references, but there's no kind of free-for-all with you can have multiple pointers and they're all kind of the same. Sometimes, though, the Rust compiler can be too strict, so it can keep programmers from writing code that you can look at it and maybe it takes you a minute, but you can verify that it's safe, right? And so the automated tools sometimes can't cover all the cases. So the escape hatch, so to speak, is that you can disable these checks by wrapping stuff in unsafe. And so basically that tells the compiler, don't worry, don't verify this, I'm good with it. And so the advantage of unsafe is twofold. One, if you completely avoid unsafe, which is possible for a lot of applications, you can be pretty sure, assuming the standard library and everything is written correctly, but that's a pretty good assumption, you can be sure that your application will be memory safe. And then it also marks regions of your code that if you do run into a memory bug, right, if you're using unsafe, that's probably the first place you want to start, right? Those kind of outline the assumptions, right? This is where you're kind of making an assumption about something that might not be safe. So we've tackled a couple of problems in this research in the paper, and the big one I want to draw attention to is, so we kind of had to deal with circular references and inheritance, which are a big thing in many C++ applications. HClib is no different. It's pretty natural to do that kind of thing in C++. Rust doesn't support inheritance, at least between structs. So you can't have a type that's the same type or has a super type. There's no kind of concept of that. And then circular references are not nearly as trivial. They're not safe when you're using Rust's sort of normal reference type, and then you can kind of get away with it if you use stuff like ref cells. But that often leads to memory leaks, and there's all sorts of fun stories. If you look up Leakpocalypse about how that created big problems. Rust likes its ownership to be organized into trees. So, you have an owner of this and that owns that, but there's no kind of cycle of there's actually two owners of this object. So this is an example of one of the applications that we worked on, and this is basically, we've taken the C++ application and taken it directly and put it in Rust. So you'll notice there's unsafe on, what is that line? I can't read it from over here, but 23 or 4 down there at the bottom on the left. There's unsafe statements there, and there's unsafe statements on the right, which are our message handlers. And that's because basically this is dealing with raw pointers and some kind of strange to Rust initialization patterns that we just basically copied over from C++ and rewrote in Rust. So what is the solution? Some good old software engineering principles, a lot of dependency inversion kind of things, and restructuring of the application. So kind of the general idea that we came to is a lot of times you have to give up some encapsulation that might be present in the C and C++. In order to kind of untangle the structure of the application and get it into a form that Rust will be happier with. So what we wound up doing is for a user to make a selector, which, quick note, a selector is an actor with multiple mailboxes. We kind of use them interchangeably when we talk about it, but that's sort of some historical stuff with the project. So basically you specify the handlers that you want to use, and you have to specify a packet type, what the messages are that you're going to be sending back and forth. And when you do that, you get for free the create method, and that takes your kind of state manipulation and wraps it in and does some technically unsafe stuff in the background that we've verified is safe. But the point is that the application developer doesn't have to write unsafe, and you get the actor management without having to worry about that. So this is the refined version. So you can see this is what you would write if you wanted to do index gather using the newer version of the library, and there's no unsafe present in this, which is really nice. So we've managed to kind of factor all of that out. Some other problems we discussed in the paper that I'll just touch on briefly that are also kind of interesting. So conveyors is the underlying, it's a message aggregation library for PGAS systems, and that's kind of what we use as sort of the bottom layer that we dealt with of sending messages back and forth. There was kind of some interesting work there with kind of wrapping that, what types can be safely sort of copied and then sent across different PE boundaries. And then also, so HClib has a finished construct. So the model dates back to X10 and HClib, and now it's in the actor HClib. And basically, that kind of controls when finishes, or when async tasks have to end by. And it was really important that we kind of model that correctly so that you can have, you can assert memory safety even though there's kind of some async behavior going on. And what we did with that is kind of analogous to the standard thread scope, which is fairly recently stabilized into Rust. But it's pretty much the exact same idea, just with this async instead of actual threads. And because this is, for HPC, it's really important. One of the main goals of the project was not to increase the runtimes too much. And so here's 4 of our mini application benchmarks that we ran, and you could see for the most part, so the blue and purple are UPC and SHMEM respectively, and then gray is conveyors. Red is selector, which wraps conveyors and does the actor model things, and then the Rust version is the yellow on the far right. So for the most part, except for random permutation, it's pretty much right in line with the C++. And then for random permutation, there's a little bit of a spike on the 2048, and that's kind of one of the next steps for this project is further research on whether that is going to continue to scale or that's just kind of a quirk anyway. And then, so another thing we wanted to measure as kind of our productivity evaluation is right, we wanted to see, how much unsafe we're cutting down on. That's kind of the idea, right? We want to remove as much unsafe as possible. We did not get rid of all of it. I'll talk about why. But you can see on all 4 of these benchmarks, there's a pretty significant cut down on the % of lines that wind up being unsafe. So what's left unsafe? Most unsafe code left is just due to external C libraries that we haven't wrapped, and that's definitely an opportunity for future work. Like there were some libc specific things that we needed just to kind of keep in line with the C++, and also SPMAT for sparse matrix manipulation. We just basically FFI'd those directly into Rust. And then there's also a little quirk of there's some dependencies on where an actor basically is self-modifying itself while it's doing message processing. And that creates some unsafe stuff too that probably needs to be remedied. So in summary, we've basically used Rust to develop HPC applications, or develop this library for helping people create HPC applications in Rust. We prioritize safety and kind of converting the C++ and emphasizing safety. And it's sort of a proof of concept to express these parallel PGAS actor programs in Rust. And early evaluation, which showed that performance overhead is not too great. And also, the great thing about Rust, and the hope is that this will help people catch bugs and sort of increase productivity in the HPC domain. So, any questions?
Thank you very much. Do we have questions for JT? Okay, let me start with an easy one. How do the HPC people react to actors?
That's a good question. I think, like, the sponsors of our project, I think have been pretty happy with it. We have been kind of collaborating with people not at Georgia Tech, so I think generally pretty happy. I've talked to people more about, okay, hey, we already have the actors, here's the Rust side of things. But yeah, I think, I like it, and as a programmer, not just as the researcher. That's kind of why I got into this project. I looked at it, I was like, 1, it's Rust, and I like Rust is cool, and 2, it is a nice API, I think. But yeah, I wish I could speak more like, oh, this person says it's great, but.
Okay, then another simple question. How do they react to Rust? I mean, Are they still using Fortran mostly?
Not the people I've been talking to, but that is definitely a thing. So there was a previous effort in this to basically kind of to try to do the same thing with JavaScript. And JavaScript, maybe, I've thought about this a couple of times. Sometimes it keeps me up at night. Rust is kind of famous for having a high learning curve. So if you're trying to get people who are not used to writing Rust, like domain scientists, to write Rust, that can be a problem. But the JavaScript was, there was too much overhead in certain places. So Rust is kind of maybe the happy medium between something easy like JavaScript and something that has a lot of bugs, like, or can present a lot of memory issues like C and C++. But yeah, hopefully they like it. I like Rust.
Right, and we have a question.
So just like a very quick question.
Yeah.
This is supposed to like slot in as an alternative to other PGAS languages like Chapel, or is this like a layer atop what you would build with Chapel?
I think the first is more apt. I haven't worked on Chapel, but yeah, there's other people in our group. The habanero group also works on Chapel, so they're kind of parallel.
All right, let's thank JT again.
Thank you.
Our next speaker is Julian, and he is having a talk titled Generating Java Interfaces for Accessing Foreign Objects in GraalVM.
Thank you for the introduction. I would like to present my master thesis project, Generating Java Interfaces for Foreign Objects in GraalVM. But before I can explain what that actually means, I would first like to take a detour into GraalVM, which we heard a couple times today already. But I would like to focus on the feature that allows you to combine multiple programming language in one process, in one project. Specifically for this talk, I would like to focus on the interaction between Java and Python, but most of what I will talk about can also apply to other languages. So as a motivating example, I will start with a simple Python function, which does nothing but print out a string. And now we want to call this from Java. How do we do that? There is a lot of boilerplate code, which is not ideal. I will go through it quickly. First, you have to create a new context. Then you have to evaluate the code, which I wrote above. And then you have to, once again, pull it out of the context and then use getMember to reach the function and execute it. This is a rather generic way of accessing a Python code, and there's a lot of things that go wrong. For example, when creating the context, there are a lot of possible options which you only know about if you are diving deep into the documentation. The next thing is that you are heavily relying on strings to execute your code. And if you get anything wrong, the Java compiler will not tell you that something happened, and only at runtime it will crash. Of course, there's a solution to this, which is abstraction. So we can make an interface which has all the correct types and all the correct names, which hides all of this generic code. And my goal is to automate this process from having a Python function or code in general and generating interfaces from it. How do I do that? I have some Python code, and my goal is to extract various metadata, for example, for functions, constructors, fields, and class inheritance. I can do this. I tried to do this with my own type extractor, but quickly realized there's already a project that does that for me, which is MyPy. Unfortunately, the part of the MyPy API that allows you to extract type metadata is largely undocumented, so we had to fight with that a bit. But in the end, we got everything we needed and could proceed with it. From this metadata, we then simply generated Java interfaces, which was a fairly straightforward process, but it also had some issues which I'm going to explain now. The trivial case is that you can simply take everything from Python and simply write it into Java syntax without much of a change. So you can take the log function I showed before and simply make the Java interface from it. And this will work for Java without complaints. However, if you have a function which is called void, which is perfectly fine Python code, but if you translate it into Java, you will have some issues. For example, the compiler will complain you can't use void as an identifier. There are obviously the keywords which don't work, but for example, the underscore also doesn't work because it's a reserved identifier. However, there is a simple solution for this. Usually, if we do this by hand, we simply append an underscore to it, and everything works. The next issue we encountered is that Python sometimes simply doesn't have any type annotations. So we can't figure out what it actually wants. So if the Python developer didn't provide us with any, we just have to assume the next best thing, which in our case is the most general type, which is object. There are also other concerns. For example, if we are generating interfaces, we can't instantiate new objects with the Java keyword new. So instead, we have to take the Python constructors and itself generate Java functions from it. These functions act as a constructor, so you don't need the new keyword, but beneath the surface, it does call the correct functions to instantiate the Python class. Another thing which is interesting about Python is that it supports multiple inheritance. Usually in Java, we don't have that, but interfaces do, which is also one of the reasons why we chose to implement interfaces and not just straight-up classes. The next problem we encountered is inheritance. In Python, you can add any attribute you want to a parameter, even if the inheritance doesn't make any sense. For example, here the dog inherits from animal. However, the parameter from pet is more general than the animal pet. So here we can't really do anything about making it the most general type. There are also some more transformation I have to apply, but they unfortunately didn't make it in my work in progress paper. But among these is generics, which is also very difficult to implement because the Python typevars are very different from the Java typevars. And it also affects operator overloading because in Java, generics are type erased to object, which causes conflicts. Unions is something that Java doesn't support at all, but I managed to create a wrapper which simplifies, or rather ensures some type safety of those unions. And my project is intended to be included in the Graal Python project and distributed in the near future. And we are also looking into adding support for more than just Python. And for example, we already have a working prototype for TypeScript and WebAssembly. Thank you very much.
Do we have any questions?
So you mentioned earlier that you translate the init things in Python into methods that aren't constructors, but just functions that return the value. And I was wondering, it looks like it might be connected to the later decision around interfaces, but what's the reason you didn't translate them into just actual Java constructors, which are equivalent, roughly?
Yeah, another issue why we can't just do that is because in Python, constructors are also values, so it isn't always clear which constructor we should call. That's also a reason why we can't just use the concrete type.
Okay, I also have a...
Just a very quick and technical question. Shouldn't this Java constructor, like translated Java constructor, be actually static? Because for me, it doesn't really make sense to create an object, to call constructor on it to create another object.
So when you use my generated types, I have a global object which has all these presumably constructors and other global fields from Python on it. So you don't have to create a new object just to create a new object.
Okay, thank you very much.
In the spirit of very pedantic questions, in a few cases you had the print thing and this type signature said it returned a string. Is that actually the case, or was it supposed to be taking a string and returning void? For log, I think.
Oh, yeah. It should return a void, yes.
Okay.
Thank you.
Okay, one last quick question from me. Did you notice any problems with the truffle interop itself? So Python and Java are their own languages, right? And if you would have a bridge just between them, that might be different than going through the truffle interop that you're using, since that's kind of its own little language, which is kind of the smallest common denominator between the languages?
Of course, there were some implementation issues, but on architectural level, there were none at all. So it was generic to the point where you can use any underlying technology, and even the languages between truffles, for example, JavaScript and Python, were similar enough, so you can just swap it out.
Okay, thank you very much. Like, thanks, Julian, once again. You got any last remarks?
Yes, I do. Yes, I do. First, I want to thank our session chairs, Stefan, Rodrigo, Matthew. We have posters in the room next door, room 1. Runs 5:30 to 7:30. For those of you who have let Rodrigo know, we have dinner at 8 at a restaurant about a little less than a mile away, for those of you who don't talk metric. Do you want to say more about that? All right. So you're saying meet downstairs at 7:40, 20 minutes to 8. Right, okay. And thank you for setting that up. All right, thank you very much, everyone.
Can I steal 2 more minutes? So first of all, I want to thank, of course, Elliot as a PC chair. Thank you very much. He already thanked all the PC once again. So again, thank you for the PC, but of course also for all the speaker here and everybody here today. And in good tradition, we already planned the next MPLR. The next MPLR will co-locate not with Splash, but with eCube in Vienna, especially for the people from Linz at the short travel. So please submit your papers, have them ready. We don't have the call for papers out yet, that will come. The PC chair is going to be Christoph Kirsch. You may know him from Selfie. He is at the University of Salzburg and in Prague, I believe. Yeah, and he will put together the next program committee and program. So please submit, please prepare your papers, and hopefully see you all in Vienna.